Okay, so doing some 2SAT right now. So we've got Tarjan's strongly connected components algorithm already implemented. Did it before I started streaming. And here, basically, we've just got the strongly connected components. We have a way of taking some SAT formula, which can just be specified as, a bunch of pairs with some kind of numbers unique for each true or false value. Of course, the negative values are false and the positive would be true generally, or you could do it vice versa. And there's already a function which is going to take these pairs for the clauses and adapt them into a graph. So basically, where you can do this because of a simple property in SAT, namely that if your clauses are x or y, then this will imply that you have either x, negative x implies y, or, well, we should say and, negative y implies x. So, because of course one of these two has to be true for any x or y in the formula. Obviously, there has to be x or y. So if not x, then y has to be true, and if not y, then x has to be true. And as for the case where both x and y is true, well, it's left open, and again, it'll be sufficient to create a graph like this. And this is well known for solving a 2SAT problem. So that's basically the justification for this. And so we're going to get started with actually doing the strongly connected components after we've created the successor graph. So the reason I call it sucks is for successor. I mean, obviously, it's going to be based on this code here. It's just going to be a vector which is in a map. And so this is effectively adjacency lists, but we're going to use a map. So we're going to allow the indexes here, like these indexes as they're specified, to be arbitrary numbers. Typically, they would be, of course, compact and, so 1 to n and no holes in there. And, you don't need to worry about labeling. But just for a simple, flexible labeling, there's no reason not to just use a map. Yeah, it'd be a little bit slower, perhaps using the hash tables and such, rather than just using a pure matrix adjacency list type of data structure. Well, actually, you would use an array of arrays. But I mean, again, this is not a matrix. That's a different way you could represent it, is the alternative way. But using a map is actually pretty convenient. So I like it, because then I don't have to deal with label issues. Of course, if your code needs to be extremely fast, you might just relabel and deal with it on those terms. So anyways, using lots of C++, for eaches and lambdas and doing stuff. And in here, Tarjan's strongly connected component. I mean, we can just go right over to Wikipedia and just grab that algorithm. So there's even, might as well put a comment with the link to it. So this is just a famous, well-known efficient formula. All it's doing is a depth first search, effectively, but it does make some, manage a stack and some data structure that's, kind of keep track of some things here. Yeah, in fact, we don't even need this one here, so we just delete that. So again, there's a way to make this more efficient by combining the 2SAT into the strongly connected components algorithm. In fact, that's the best way to do things, is to actually combine it, because you can short circuit, so it doesn't have to do a full depth first search when there's some non-satisfiable formula given. It can just immediately, when it detects a strongly connected component with x and not x, then of course it can say it's not satisfied, and it doesn't have to do the rest of the depth first search. So that can, for a very large graph, be very significant on time savings. And then, yeah, essentially this may not be the most efficient because of the heavy use of C++ in here, but we're going to just leave it up to the compiler to optimize this and make it. It should be extremely efficient if the compiler knows how to optimize such code. So otherwise it's basically just boilerplate code. Does it work? Well, we're going to find out. So the way we find out is by going to, let's see, TOSAT. Now, it might be interesting to implement GraphViz in here too. Actually, I've implemented all this in Python first. So we're going to do the TOSAT just the standard way before we get into assembly language and self-modifying code and all this type of stuff. So it's already done in Python as a modeling. So now we're actually doing an assembly and C++ solution to stuff that was modeled in Python for convenience, because you don't want to mess with assembly language when you're doing something really tricky. Necessarily, if there's a faster way to develop it. Otherwise, if the fastest is working with assembly, then you can go that route too. I mean, it doesn't matter. It's just Python, if something crashes, you're in a better situation than actually having processes crash on your system constantly. Could destabilize the system. Running Windows here, so you never know, right? So, okay. So, what we can do is we can get these strongly connected components, and the one thing we will need to know is which node is in which component and such. Now, the way it returns this is a map that's going to have the root of the component, that's the integer, is the key, and then all the components, including the root, as the vector of integers. And so what we can do is merely go through all the components. Again, as I say, this is not necessarily the most efficient thing to do. So we're just going to use a typical STL here. And we can just go through the components by going from begin to end of each component. Now that's going to need a nice lambda function here. We'll see what we're going to capture in there. We're obviously going to get a standard pair for the map of integer and a vector of integers. So we'll take that pair P, let's call it, and we can do a for each on this. And now we're going to do some checking with this. The first thing we need to check is that no x and not x are in the same component. So to do this, actually, we could just use another map which does the inverted operation. So right now we have the root going to a vector of which nodes are in the component. But what we need to know is the opposite direction. If you go from a node, which component is it in? So we can just create another map for that. This time it goes into int, because in each node will be the key, and of course it can only be in one component. Otherwise, a given root component can contain multiple nodes. So this is pretty straightforward. Call it reverse SCC. I mean, it doesn't matter what we call it here. Of course, we're going to want to capture that, even by copy, by reference. It's just merely an efficiency issue here because, again, it's an object. So do something with this now. We've got the different components. We're going through them. Actually, another point is we don't need necessarily to do it like this. Actually, let's not do it like this because we're getting too much information. What we could do is just construct a temporary unordered set. So like here, we can just say unordered set, which is like the key part of the map. The key part of the map should be, it's a hash table effectively, but we're going to need an include here. Unordered set. So using a lot of different C++ classes, but that's the convenience of C++. Is we just get all this. So of ints. Now, if we used an unordered set instead of a vector to begin with, it would actually make this much easier. The problem is we could check if it's in the vector, but we're going to end up with an n squared algorithm, and we don't want an n squared. We want a O of n algorithm. So yes, this is creating more memory tension than you really need to by not just returning it to begin with. But we can always combine these ideas. It's very efficient to just add to the end of a vector, although it should be about equally as efficient to just construct this as an unordered set to begin with. Yeah, so, and we need to look at certain mistakes that are made, and we're going to correct stuff. So obviously this being a map is a bad idea because we want these in reverse topological order, and we're going to fix that. So I mean, these are just like little things, but we're going to fix it, and we're going to test it with some example formulas, and we're going to make sure this works. So, where do we go from here? Well, the place we go from here is that we're going to actually take this unordered set and just start populating it. So we'll just call it U, and now we can just say we need another for each. And what we can do is go through what's going to be the second pair, the vector. So we go through the vector. And yeah, this is pretty heavy on the C++ usage. And yeah, we could use iterators. We could do all sorts of other things. I just like this because it is kind of neat to be able to do almost like what you can do in C# or other languages with C++. So okay, now we need a function here. Another lambda comes into play. And now, so we put the U out here because it's going to just be tracking stuff. All right, so in here, we're going to just get an int. Let's just call it W or V. I mean, it doesn't matter. N for node, the typical variable names. And now we can immediately say, well, since we know we're going to need U, we'll just capture it. And we can say U insert V. So we inserted that into the current component set, and now we can immediately do a check and say you find minus v not equal to u end. Okay, and when this occurs, well, now we have a problem because we're going to need to get out of the function. We're done, actually. We're ready to return, but not just from this inner function, but we want to return from the whole thing. This is an unsatisfiable equation. So the way we can deal with this is just perhaps by setting a flag. So we could just say, you know, unsat equals false. But when this is detected, we can just say, you know, unsat equals true. And we should make that a bool. So if unsat is true, we'll just return here. And we'll allow this to, you know, try to short circuit this in some other way. In fact, this is one reason not to use a for each, and one reason to use an iterator, is it does make it a little bit awkward setting this in here. Plus we have to, you know, capture it. So there we go. It's captured now. So what we've done is we've seen that it found a strongly connected component that contains both the true and the false of the same variable for that part of the Boolean equation. So obviously that means that it has to be true and false at the same time. And that's why we're using this positive and negative encoding scheme, because it makes it very easy to do this check. So we first insert it. Actually, we don't even need to do that first. If we want, we could even think, okay, maybe it'll be a little more efficient to do it after. It doesn't really matter because we're looking for negative v, because we already know that v is going to be in there. So, and now if it adds v or negative v first, it doesn't matter because it'll always check the reciprocal value at some point. And it's pretty difficult to avoid having to check both the one way and the other. Unfortunately, you're going to have to do 2 checks for every value. Not a big deal, though. So Okay, now we've done that, but now we actually want to start building the actual final result. So we're assuming we're in reverse topological order. And actually, as I said, we're not really in reverse topological order. If we make a map here, it's just not going to work. One thing we could do is just to return a vector of vectors. So that would actually be the most straightforward thing, is just to return a vector of vectors. Uh, These are being found in reverse topological order. We're good. With nothing to do if we have it in reverse topological order. We can just go through it here. And actually, the beauty of the way the algorithm for 2SAT works is that when we get to this point, all we need to do is just like here where we're checking if they're in the same component. Well, now we just check if they're in the solution. So we can just make a vector. Maybe that's going to be inefficient, actually, right? So, because you're thinking, well, the problem is we're going to have to decide, is, v or minus v already in the solution? And basically, the way the dependency graph works, if it's already there, you just ignore, and you just keep putting stuff in there as long as the opposite value is not already in there. So let's just use unordered set again. And this will be our solution of integers. So we've got our solution defined here. And now we can just say if, and we use the find. It's the same exact idea. It's just a little different here. So if minus v is in the solution, which of course we need to code out like this, not equal to solution end. So if it's not the end of the iterator, it means it's in there. It did find it. And of course we need to capture this too. It's an endless story of captures if we want to use this kind of for each style here. So now if it's not equal, then we actually have found a new part of our solution. So it's not found its opposite value in there. And so we can immediately just say solution insert v. This should be sufficient. I guess we don't even need this extra line here with all the braces. We can just make this a one-liner. This should be sufficient. Now, you might say, well, how are we going to get out of these loops? If it's unsatisfiable, don't we just want to stop right here and now? And actually, that's a huge problem. So again, we're going to end up enumerating the whole thing. So one thing we could do about this, the first thing is, if it's unsatisfiable and we do return, then of course we're not going to want later solutions to be inserted. We're going to want this solutions to stay empty. One thing is to not care. One idea is just to return something at the end. Now, do we want to convert this unordered set to a vector? These are all like little programming details. Probably it depends on your context. I guess for right now, we'll just return an unordered set. The only thing is if we wanted them sorted, and there could be some justification for that. So actually, I think we will. We'll just do this. We'll do this the nice way, and we'll just do a standard sort or qsort. Can we do qsort here? Yeah. Actually, qsort won't work. That's going to take an actual array. Since we're using iterators here, though, we'll just let the STL deal with everything for us. So we can just say standard sort, but we're going to need a vector already. So let's call it solv, so solution vector, and we just create a vector of ints, and we can we're going to need to, of course, insert into it correctly. We can't just do that. So we can just say solv.insert, and we just say the begin and the end. So we insert the entirety. Okay, this doesn't work. Where did I go wrong with the flavors for inserting? Okay, not insert. We don't want insert. We want I forget which there should be a way to do this in one statement. Of course, I want to do this elegantly. I don't want to have any extra code here. Obviously, push would push a single item. Well, I guess we should use insert. We'll use insert, and we can just say where is going to be at the beginning of this one. So yeah, that's how to do it. So we just say solv.begin, because that's where we want to start inserting. We really don't care about the order right now, because we're going to call standard sort here. Now, this is going to also not give us necessarily what we want, because generally when you have a solution, you want positive and negative to no longer matter. You want the absolute value for the sort. So to do this correctly, we're going to need a predicate here. And so that predicate is going to, of course, take two different values, x and y, and it would just decide based on the absolute value. Usually it would just say x is less than y. It would sort in ascending order. But in this case, we want to know that the absolute value of x is less than the absolute value of y, and that's basically it. So yet another lambda here. We can maybe say int x, int y, and we can return that the abs of x is less than abs y. We want these integer absolute values, just there's no reason to use floating points here, and it's exactly what we have here. So this should, ideally, this should work, and now we can return solv. So that's our solution. And so we are trying to do this very elegantly, get a very nice solution that's in appropriately sorted order, the way that anybody who, if you coded this out in Python, you would probably get something very similar, of course with a lot less code, but again, that's the point here. So now one thing we can do to just get this working quickly without dealing with this whole case, again, returning here is fine. We could always just keep returning, but we still might have solutions already for unsat. So if unsat, we could even just return of an empty vector like that. I mean, that would be one option. It already takes care of that case. We could also just erase all the elements, but almost, if you're going to check for it, why bother erasing elements? It's going to automatically clean everything up just with this statement here. Actually, we can do even better here, because we could just return solv, and that's actually quite nice. So the only thing is then, maybe we don't want to do any more work once we have unsat is true. So if unsat, just return from here. We could even do it out here, but it's probably going to call the constructor of this unordered set. Even if we put it out there, it's really up to the compiler to be clever here. I don't always want to assume it's going to be too clever. In a debug build, it definitely won't be clever. In a release build, maybe it can optimize out all this type of stuff. Again, probably you don't want to use for each here for this exact reason. So what we can do now is, as I said, this actually needs to be in reverse topological order or it won't work. So we're already calling toSat. The other problem is, obviously this isn't going to be very helpful either if we aren't going to print it out. So we do, of course, want to make a printout here. Simple way to do that is like this. So we make a vector of integers, and we just assign it here. And there's our solution vector, and we can use for each even, just go to the beginning to the end. And we want to see that we actually get a solution to, this is a very silly boolean equation, but it should have no solutions actually, and so we should get unsat and it should just work. And we'll do some more interesting ones. That's just a start. So again, overuse of for each here for sure, but okay. I think we can, well, we can print this to the console. I'd actually like to print it to the debug window, but that's probably, we're not going to be writing C++. We're going to use some kind of Windows. I'm not sure if there's a standard template library, generic way to write tracing messages. Otherwise, we have to write it to the console. Unfortunately, I'm not sure that's going to show up on the stream, because I'm streaming Visual Studio, but the little console window pops up. It would be much nicer to write the result in here, actually. And let me think about this for a second. Or it would be nice if it would save the same console window and I could put that over in the stream somewhere. This needs to be thought about. I should fix that, though. Immediately. I'm going to fix that. We're going to find out a nice way to see the results here as they come out. Actually, printf, I guess, isn't very C++ like, so C out. Okay, we can fix this. Yeah, it's in standard. Oops. Standard C out. Maybe we should just use the namespace and stop writing std everywhere. V space, I suppose, and we can just make this in V. Of course, we might want to put a new line at the end here and not a space. And then we need to know which one's the last one. They have these little details. Actually, we'll fix them. All these details, they're nice to have solved in the 100% best way. So always putting a space and not putting a new line. Again, these are little things, but we'll figure out a way to solve that as well. Again, probably for each is not a particularly nice thing to use here. Using an iterator, it's much easier to solve that. Okay, last issue. We go here. We're going to say, okay, we're not going to store the root components in a map. We're not going to do this because we lose our topological sort. And for 2SAT, we want a topological sort. So we want a vector of vectors so that they're in a specific order as they come through here. So instead of assigning the strongly connected component V here like this, we're actually going to have to redo this. So what we do is instead we make a vector here. Vec, which lack of a better name. And then what we'll do is we will push onto that vector all the nodes that were detected in the component. Again, this algorithm comes straight from Tarjan. We're just kind of tweaking it for our purposes here. And okay, so we don't need those parentheses there, of course. And now we can just say sccs dot push back a vector, and we should be able to return it. And I think we're good now. I think we're going to get actually the beginning of a working algorithm here. In fact, if we're lucky, it's just going to print unsat, and it's going to work here. So there we go. Now, of course, it's going to change stuff to be doing it like this. Yeah, I have a comment here with some test code. In fact, it should still work. Oh, that was wrong. That actually is still right. This is the map coming with the way we're using the dictionary to do all the nodes here. So that's how things are flowing. So we do this. Let's see. We have our vectors now, and we know that this is not going to be the correct way to iterate it. Of course, it's not going to have an int here anymore. It's actually going to just iterate raw vectors. And now we don't have a root node anymore, and we don't even care, because we're just going to be iterating it. We don't really need the root node for anything here. Again, we're using unordered sets in here. That definitely helps. And well, we don't get anything printed out, which actually is kind of good, I suppose, in a way. So another thing we can do right here is we can actually just maybe fix this. So if solv.size is 0, then we can see out unsatisfiable. with a new line. Else, let's stop using all this for each stuff because we like new lines here, and we're not going to know if it's the last one or not. We could check, the last element because we know that all the elements are going to be unique in here. Again, they came from an unsorted set. We could just check. In fact, I guess if we really want to use this, this is how you do it. You kind of use a question mark, colon, and L. And our condition is going to be that the convenient thing is sol v. It has a last property, which will give us the last value. Not sure how efficient this would be if the compiler knew how to optimize this, but it probably doesn't. So a back, right? So if the back item is not v, space, otherwise new line. Oh, that doesn't work either, huh? Because we can't. This is not a string, I guess. Yeah, it's traits. Okay. That would be nice if that would work, right? That would be nice. Is there like a standard space? You see, I have to go into STL and start looking at what's defined in here. I don't think so. Yeah, new line is kind of special. There's end S for end stream. Something that would give us a space. There's a way to do this, actually. Yeah. And now this is a good question. Just how do we do this? Again, we could write our own class to do this, but that's pretty annoying to do it that way. I guess we would have to use that because we have to convert the string with the space in it into a stream, basically. And we could, I don't think it's worth it. I think it's easier to just, yeah. It's easier to use even an if then else statement or what have you. It is a good question. Is there an elegant way to do this? Can we cast this to... No. Forget about that. Because it takes an argument list. Yeah, okay, so... Well, we're going to go into the details here. Here's the details of it. Yeah. I don't think... Yeah, obviously we can't just instantiate it that easily. As far as I know, we may have to define a function to do something like this. This is basic, and I don't know off the top of my head the trick for this. I wish I did, actually. All right, well, what I'm going to do then is just write an if-then-else statement and not dwell on something silly like trying to find a one-liner for putting a space versus a new line. It really doesn't make sense. I can just say solution v back not equal to v, then we write it this way with a space, else we write it with a new line. and we don't waste any characters at all. It's very efficient and kind of clever. And what we should get now is unsatisfiable. It works. So now we need to test more cases. So I have more cases here, and I'm just going to drop them in from out of nowhere. But actually, the place I got them was on Stack Exchange, where they're doing code golf. So doing code golf, they give some nice examples for solving 2SAT. Of course, the code golf required not only a nice, compact way of doing it, but they required that the code golf used an efficient algorithm. So no 2 to the n algorithms. You have to use some kind of graph algorithm that's going to look for the strongly connected components or something like that. There's some other algorithms that are very similar to this. So, okay, this equation has no satisfiable clauses. You can see because it's not 1 and not 2, or 1 and 2, or there's just too many clauses here, and it can't satisfy all 4 of these. It's because it's basically the exhaustive space. There's 2 variables, and every combination is specified here. Well, you can't obviously have both 1 or 2 and not 1 or not 2 at the same time without having 1 or not 2, or not 1 and not 2. But those are also clauses, so I mean, it's a perfect, simple example where you have everything there. So here's example number 2. This is going to have 4 variables. So we just define it as test formula 2. 4 variables, and I have it in Python, so whatever. Just change out the parentheses for braces. And we're going to test that this one works. Now, since we're starting to generalize this, to make this even nicer, what we can do is not just solve formula 1, but we could actually make a vector of these vectors. We can just keep going here. So like now we have a vector of vectors of pairs, and this will be like test formulae here. So this one can be like test formula 1, test formula 2, if I can spell that right, and there we go. Now we can actually now enumerate our test formula by doing yet another for each here. If you don't like for each, then yeah, I mean, I don't necessarily like it. I just think sometimes the code is actually less than writing out the iterators for stuff. So put the begin in there, test formulae dot end, and we're going to put a lambda in here, which is going to actually include all of this code now. So we pop this out, and there we go. So now we actually have like a way of going through all of the different test formula, and now this will be test formula, not 1 or 2, it'll be just test formula. So now we can go through each test formula and just write out if it's satisfiable or is it unsatisfiable. If it's satisfiable, it'll actually write out a boolean formula, and that's kind of what we want to see. Well, it'll write out the values of the boolean formula that's satisfied. So, okay, that's why when we compile, let's hope it does now. Yes. Okay, it got unsatisfiable. Now that unsatisfiable here is unsatisfiable, is it right? Now I don't think that's right. No, it does have a solution. So now we actually go into debugging. So now we want to know what is going on. Why is this unsatisfiable? This clearly is satisfiable. The first thing we want to check are the components. Now, actually drawing this in into GraphViz and looking at the graph would be really helpful right now. If you know, I mean, because I happen to know the strongly connected components, but a picture is worth 1,000 words. If we could see this in GraphViz, clearly that would be the best way to debug this instantly without, you know, having some previous knowledge. So definitely this is time to go to GraphViz here. But what I can do is just put a breakpoint on this point right here. So we're going to want to look with the debugger what is going on here. Not the first equation that's unsatisfiable, but the second equation. So SCC's size 2, we see 2, -1, 3, -4. That's great. And we see 1, -2, 4, -3. That, on the other hand, is also, these are not, shouldn't be causing unsatisfiability. We don't see any 2 and -2. We don't see any value and its complement in the same set here. So it's a good question. Why would it be causing unsatisfiability? Unsatisfied false here. So okay, we can put another breakpoint right in here and just find out who's doing this here. So we have well, the breakpoint's at the beginning of the line here. So -1, 3, -4, 1. And that's probably happening here. No. So where did things go wrong here? Aha. This is backwards. The solution should be if they're equal. If it's not in the solution, if its complement's not in the solution, we add. So obviously I did that wrong. And again, this is why you troubleshoot and you debug, because you want to know what's going on. So that was actually just not that it was unsatisfiable flag being set, but actually it was just an empty solution. And we get a correct solution now. We get -1, 2, 3, -4. That is the correct solution. I imagine if I put in the last two formulas that I have, this one's going to have 3 solutions. And we'll go through how to enumerate solutions of a 2-sat equation, because that can also be interesting. So this is test formula number 3. This one has not just one solution, but multiple solutions. And here it's specified. I'm going to put in test formula 4. Again, these are all from this code gulf on Stack Overflow. So here is going to have 60 variables and 99 clauses, and probably a billion solutions even. I've tried to count them, but counting is in P# complete, and we're not interested in solving that necessarily, because P# complete is supposedly harder than NP complete. So this could be on complexity of 2 to the power of, 60. Ooh, barely solvable with normal hardware. Now, probably it's not, but again, we don't want to necessarily mess with such a problem. So here I can just change the Python parentheses. We'll change the left parenthesis to a squiggly brace, done. And we'll change the right parenthesis to a right squiggly brace, and we're done. And now we should be able to add these two test formula, number 3 and 4. Okay. And then we should be able to test all of it and see that it works. And actually, the one thing, I want this console window to show up here. I guess I can just add it right now. Can I do it as a window capture? Yeah, okay, I guess I'll just add it as a window capture. The problem is I don't know how to make it automatically. Yeah, automatic, huh? Okay, well, if it's going to automatically do it. Okay, so here's the console. And that is nice, because what we're getting is stuff that looks like solutions. And again, there's 3 solutions to this third equation. There were no solutions, 1 solution, 3 solutions, and too many to print out all of them solutions. It'd be nice to know how many there are and actually confirm that. Again, if we want to go after the P# complete stuff, we can. So now let's redo this again. So we've actually now got a 2-sat solver. And now we want to get all the solutions, even if there's too many. We'll just keep printing them forever, but they'll all be different solutions. The big question, how do we do that? Well, this we can do using a clever trick. So when you're dealing with 2-sat like this, there is a very neat trick that you can do. And so again, we've already used this trick. We've done the X or Y, allows you to imply that either not X implies Y or not Y, and not Y implies X. So we can build a graph with this, and we know that the strongly connected components will tell us if they're in the same component, it's not satisfiable. Otherwise, the reverse topological order, assigning any whose inverse or flipped values have not yet been assigned, like we do here, will give us a solution. But again, there's a lot of topological sorts, and the number of topological sorts is even more than the number of solutions, because there could be topological sorts which don't change the solution. And counting topological sorts also is P-sharp complete. So first off, this algorithm here, Tarjan's, is of course OM plus n, the number of edges and the number of nodes. Number of edges could be n squared, so some people will just say it's O of m, because m is usually more than the number of nodes. It doesn't have to be, not guaranteed. Again, these graphs don't have to be connected or anything, they're just directed graphs, that's all. The complexity here is going to be the same. Again, and we use efficient data structures. This is reasonably efficient, maybe not perfectly efficient or memory efficient, and we can combine this two-sat algorithm into Tarjan's and make it really, really fast and efficient if we had a real use for it. But anyways, what we want to do is make another function called like all two-sat. So we can just start printing solutions even. Maybe we can just make it void, and we'll just say, you know, all two-sat. And we're going to take the clauses that we take here. So the clauses are just pairs of integers, as we've seen how that is done. And then we're going to need basically something more to do this, because we're going to use a trick. As I said, the trick we're going to use is every time we find a solution, we're simply going to add another clause. And by adding a clause to our existing two-sat solution, we will actually basically be quote-unquote banning the last solution. So basically this is how you're going to do it. You get a single solution for two-sat, which, as I say, it's in reverse topological order, and you don't know which reverse topological ordering you're going to get. It's based on the strongly connected components traversal, where we're getting the successors here. So it depends on the order we go through these successors, but every order of successor might not even give you a unique solution. So we can't just enumerate topological sorts. That won't work. We could try to build a dependency graph, and there's all sorts of like little ideas here, but reusing the code, the very easiest thing to do is to just ban a clause by putting a new clause. So we put a new clause, and that solution will be basically looking like this. So we're going to add YY for all Y in the solution, except for one, and then we're going to add negative X, negative X. So by adding all these clauses into the solution, you've basically forced that at least one of the bits has to flip. So we're adding a bunch of clauses, actually, not just a single clause, because if you think about it, the single clause that you want to ban is, you know, something, or something, or something, or something, or something. You need to basically say that the flip side of any of those are there. But we can't add, like, for example, this has 8 different variables, but we can't add a clause with 8 variables. We're doing two-sat. That would be sat. We're not doing sat. So we can add 8 clauses, basically specifying each variable being set one way, and then one being set forced to be the opposite. So we toggle one bit of the solution. And by doing this, we can actually enumerate solutions. And it's a clever way of doing the solution enumeration. It's not horribly inefficient, because again, this is an O of m plus n algorithm. There might be some better ways of doing it. There's some research papers we can look into, actually, regarding this. I think it's Feder who has a paper on it. But his paper is about network flow, and it's pretty tough to extract his enumeration method. Right now I don't know a better enumeration method. It's an interesting question though. So okay, we've got now a kind of a strategy for doing this. And so let's do it. Let's actually print all the solutions, because that's kind of the completion of a task like this. So the first thing we do is we get one solution. Now, how do we get one solution? Well, we just use our code that we already have here. So what we can do is call toSat on clauses. Again, test formula is clauses effectively. There's no real difference. It is in the again, papers will call it a formula. We can just call it clauses. Doesn't matter. So, okay, so we get a solution, a vector. So solvi is equal to that solution. So now we have one solution, maybe. Maybe it's a solution, maybe it's not. And things are about to get tricky. First thing we're going to say is that we know if we toggle any bit of that solution, we might get another solution, or we'll get unsat. So the problem is if we toggle one bit, and we get another solution, maybe we need to toggle another bit, and we know there can be 2 to the n solutions. So the easiest thing to do is to make a stack immediately and just say, okay, we know that we're going to have like some kind of recursive algorithm or something going on here. Maybe we don't want to do it recursively. Maybe because, again, the depth could be like, you know, I don't know, an issue. Probably not. I mean, 60 variables, whatever, but we can do it with a stack. That's perfectly fine. We have it already included. So we're going to make a stack. Now this stack is going to contain a solution and an index. That index will be the bit that we're currently toggling. So our solution is, of course, a vector. So we'll make it a pair. We'll say, okay, we've got a pair. We've got a vector, which is our solution vector, and we've got some integer index into that solution vector that we also want to store in our stack. So we'll call our stack S. That's the nice usual name for a stack. Okay, now we're going to need to say while S dot, what is it, is empty. Wait, empty, I think empty returns a bool. Yeah, empty does not empty it, it returns a bool. Clear empty is the other. A little bit of confusion sometimes with that. But so while it's not empty, and now we can start actually doing something with this. So while the stack is not empty, we're going to take our solution and indexes, and we're going to just start doing something. Now, if you're not used to taking recursive algorithms and going to stacks, this is kind of instructive. We could do it both ways. We could do the recursive variant of this, but this is going to be pretty elegant because we're just going to use a very efficient and simple stack. And you're going to see this is going to yield a very, very nice solution to this problem. So we can actually just pop off our stack this pair. This pair, we'll call it P for a pair. I mean, we're going to need to extract out what's in there. But, okay, it's going to be equal to S top. Again, you have to, some languages like Python, where I did this before. In fact, I'm looking at my Python reference solution. I coded this all first in Python, but I realized that it could be more interesting to do it in C++ in assembly language, which we're getting to next. We're going to finish with the C++, and we're going to go straight into assembly language. And that is going to be where we're going to start using self-modifying code. We actually will even do this as a virtual machine. We're going to just go all out. We're going to do every detail perfectly correct, showing how to really get not only a deep understanding of this problem in the basic case, but how we can start using self-modifying code. We can simulate it with a virtual machine, and then we can actually go right into handwritten assembly language. And we're going to write self-modifying code that implements a directed graph algorithm. It should be really, really kind of a fun, instructive thing to do. So, okay, let's actually get this working though, because we can actually use when we go to the self-modifying code, we can just pass a lambda here. Standard function, and we can instead of calling toSat here, we could do that right now. We could just make a standard function, and we could say instead of toSat, I can call any toSat, whether it's self-modifying code, whatever it is. It doesn't have to be this toSat function. We need just a function we can call that gives us a solution or no solution. And that's what we have now. We have either it returns an empty set for unsatisfiable, or it returns a non-empty set when it's satisfiable. Okay, let's do this because this is where the fun begins. One thing is we may want to print the solution here, otherwise we're just kind of going through them. But we're going to want a for loop here. So we're going to want to go basically through all the indexes for the current entry in the stack. So what we can do is say for, again, this is a little less C++-like not to use the iterator, or we can use an iterator. It doesn't matter. We can use the index to offset the iterator. But basically, I would equal p dot second, which is that integer, and I is going to be less than the size of the vector, and that's p dot first dot size. Again, we can rewrite this to be a little bit more C++-like, more efficient. But basically, we're going to start with the index that we have, and we're going to go to the end of the vector. And now we're going to actually get another solution. So we're going to say, okay, I want another solution. We're going to call it the inner solution. So solution inner. And that's going to be toSat of clauses, but not really clauses, right? We want to actually force it to be a different solution than any that we've already got. We're toggling bits and we need something new. So, okay, now we're going to make like another vector of clauses. And we'll call it like clauses inner as well. So what we can do is immediately insert into this vector all the outer clauses. Let's do that with insert. And what we can do is just put the beginning of this, that's where we want to insert it. Obviously, that's the only place that it can be inserted. It's empty. And then we can just say clauses.begin all the way to clauses.end. And that's how you insert or copy basically into this new vector. Spell it right here. Okay, and so now we've inserted those clauses, but now we need to insert, like in this example with 8 variables, we need to insert 8 clauses. Since, as I said, we can't insert a clause with 8 variables, but we can insert 8 clauses with 2 variables, all which say either, y and y, or y, or and not x and not x. And basically the way we can just do that is the index is going to tell us what x is, and everything else is going to be part of y. Now, you're probably wondering a little bit about this. This sounds kind of sketchy. We want to toggle the bits. So that's why we have... actually, we should start with... let's just start with this. Toggle bits with minus x minus x. Now, you might wonder why I want to add some other clauses. Actually, we don't really need to start adding any clauses yet. We start with minus x minus x. The problem is that minus x solution could come up again later. So we'll get duplicate solutions, and we don't want that. And so to avoid duplicate solutions, what we can do is we can actually go from the rest of where I is, the rest of the indexes, and block out solutions so that they don't happen again. And that's actually rather, sorry, not till the end. From the beginning to where we are now, we say that they have to be the same. So it can only be flipping bits after I. It's got all the flexibility to choose any bits it wants after I. It has to flip. The ith index bit, it flips. The ones before are fixed. We won't get any duplicate solutions. We end up with a perfect toSat solver. It's going to give us all the solutions. So this is kind of a bonus task right here. But it's kind of fun to actually see that we can efficiently and elegantly do this. So that's why I'm doing the bonus task. So let's do it. Let's actually add the minus x minus x. So what's minus x? Well, p dot first sub I. So that actually, this is why we could just use an iterator here, and probably I should just change this, but we can just add this. And now what I said is we want to actually block some solutions as well. Okay, yeah. So we're going to actually add it like this, the correct way. Don't want to take any shortcuts here. This is how we need to do it. Standard pair, it's a pair. And actually I said minus x and I'm not even putting, okay, so there we go. We have this is our minus x. And now we want to go through and we can even take a look at this, but the printing code I have here should probably be a function now. So let's take the printing code and just make a function out of it. So like print toSet, I guess. Might as well put it up here. So I can reuse it without for a declaration. Print toSet. And what's it going to take? Well, it's going to take a solution. And what's a solution? Well, it's this vector right here. So now we're going to be able to just print any solutions. In Python, you can use something like a generator. There's ways of doing that in C++ too, but of course that's multi-threaded asynchronous programming, and we don't necessarily want to go there right now. There's not necessarily a reason to go there, beyond that if you only want to take a certain number of solutions, but even then we could do it a different way. You don't need to use a generator and enumerate that way. So, okay, we've got our printing code now generalized. We can delete it from here. In fact, we don't even need to store this. We can actually just, like for example here, we could say print toSet of this, and like really quite clever, quite efficient. So there we go. Now, we call print toSet and we're done, right? So, I'm really getting ahead of myself here. So now remember, we don't know if this is going to be a empty solution or not. So actually, we've still got a few. We're not totally done, but we're very, very close. So if the size is not equal to 0, it means we did find a new solution. So we should say the stack needs to be, we'll use a push. Stack push. What do we want to push? Well, a vector and an integer. And what's our vector and integer? Well, our vector is the new solution. So again, we're never going to add more than 8 clauses because we're going to just let go of these clauses just as soon as we generated them, right? We do have to, unfortunately, do some memory copying there. And again, we are calling strongly connected components again, not using some kind of clever reverse topological sorting enumeration. But as I've said, you'd have to do some kind of dependency analysis there, not necessarily using the original reverse topological order. It would get a bit tricky. I would like to look into that. That sounds really interesting, but I'm not sure off the top of my head how you would get that to work. So anyways, let's just add the solution here. Of course, it's a vector of int solution in, and now we're going to add, okay, we need to take, what's our index? Well, our index is I, right? So I plus 1, I believe is the right index here. Yeah. And we're going to also need to initialize the stack. It's obviously empty and it'll never execute our code. So what we can do is the same thing. If there is a solution, it's not unsat, so the solution size is not equal to 0, then we just push onto the stack the first solution that we got, and with index of 0. And this is like a base case, and that's all there is to it. So we use our base solution, and we use the 0th index. And if there's no solutions, it actually won't print anything. Maybe we should print something if we don't like that. Okay. If we don't like that, then we should do something like else cout no solutions, right? So again, if we take out the code that we currently have here, which is calling, again, this print toSet of toSet, now we're going to actually call just all toSet. And instead of getting sat or unsat, sat with a single formula or unsat. Now we're going to get either no solutions printed out, same as unsatisfiable, or we're going to get all of the solutions to the formula. And it should be quite nice. So the only thing we don't do still is print out our solution. So our solution's going to be here, right? So the solution's going to be printable right here. So that's the tricky thing, is where to do it. Well, the most elegant thing to do is do it right after you pop it off the stack. So we can say print to sat, and what is it going to be? P dot first. Our vector is our solution vector. With a little bit of luck here, we've got this. All right, or with a little bit of duplicate solutions. Actually, is this visible? No. Yeah, it is. Yeah, it's got the wrong window here, doesn't it? It's got my Python window. Let's see. Let's see about fixing that. Put a different window here. Yeah, that's not the one I wanted. I want the Visual Studio one. Oh, it switched up on me here. So, okay, so we can just close this one, I guess. Oh, console. This one's console. Okay, bear with me. I actually don't know. Oh, there it is. Remove. Okay. Yeah, I'm sure I want to remove it. Okay, so what you can see is it's finding solutions here. But actually, oh no. That huge formula has way too many. But if we just get rid of the huge formula and comment that out, because it's going to be distracting for this. Wait a second. What's all that about? Okay, so now if I run it, oh, I see. Yeah, how do I change the window here? Huh. I want it to like automatically figure out what I want to do. I guess it doesn't want to. Okay. It really doesn't want to do. Oh, okay. Here's how I do it. Okay. Visual Studio Debug Console. Ah. Okay, I have a defect here because it should be figuring this out. There it is. I don't know, yeah, it didn't. So anyways, what you see is the same solution again and again and again and again and again. So kind of a problematic situation. Something's going wrong here actually, because it's the original solution, so it must not be getting our clause. Okay, there's definitely just a simple bug here. This is going to be easy to fix. So we're going through this all to sat stuff here, and this is oh, you see I put clauses here. Yeah, okay, that's a much nicer explanation for what's going on here. Let's try it again with local Windows debugger. Did that show up? No, it keeps wanting to. Yeah, I wish it says automatic, but it doesn't want to be automatic. Okay, so now we can see we got no solutions. We got our one solution that we wanted. Now we got a ton of solutions. There's 3 solutions. These are all valid solutions, but they're duplicates. 3 solutions, but how many times is it finding each one? Well, there's a reason it's finding these duplicate solutions. It toggles -1. And it finds this solution where it toggles -3 and 7 as well. But then it also toggles this to find the same. It finds another solution, I guess, when it toggles it. But it can end up finding the same solution again because, for example, when it toggles -3 later, it's already toggled -1, -3 in this solution. But then it can toggle -1, -3 later, and it finds it again. So the way to do this is to not just ban or not just force a single variable, but ban the previous found solutions in a very clever way. We don't need memory. We don't need, because there could be millions of solutions and we don't want to store them all in memory. That's the beauty of the algorithm we're doing right now. Without storing these in memory, we're actually going to just block all the previously found solutions by using a stack here, and by simply now blocking not only not x, but now we're going to, prevent duplicates with y. And so now we can just add more clauses in there. We can just go in a for loop here even. And now we can just say int j is 0, j is less than I, j++. And that's it. We're just going to add to this inner, we're going to just add index j. So we just add these types of clauses, which says that bit has to be, or this variable value has to be true. Now it could be a negative that has to be true. We don't know what these are, but we don't really care. We are just saying that whatever this is, whether it's positive, negative, whatever variable it is, it has to be true. Whatever this one is, it has to be toggled. So we're saying this one has to be the original of the solution, and this one has to be toggled. And by doing it this way, we should very nicely rerun this, and we should see just what we want to see here. Okay, I needed to hit the enter key. Yeah, okay, it's perfect. We got 3 solutions. So that is how you do all 2sat. Here you go. There is a beautiful solution. We actually have achieved it using this very nice snippet of code. We did not store all the solutions in memory. We just can print them out. We could turn this into a generator somehow. We print out no solutions, or we just start printing solutions. And the next thing we can do here is try it on the big formula. Although I imagine it's just going to print forever here. So we can do it like that as well. Now we have to remember to comment this back in. Okay, so let's see what happens. There are a lot of solutions to this large Boolean formula here that I, of course, got from the Code Golf website. I wish I knew how many there were. One thing, and now the other thing you can see is that we are listing them in order. So every time the solutions come, it's absolute value, ascending order. They're coming in a nice way. So we know that 1 is true, 2 is true, 3 is true, -4 is false, -5 is false. We know these things. Now, the window is a little screwed up here, so you're not seeing this, but we can fix this very easily. Okay, so you're seeing solution after solution after solution. Now, how fast is this solver? Well, it's not too bad, obviously. It's maybe not the most perfectly efficient, and we can try to optimize that. Now, the other thing is if we stop printing these solutions, we could try to count them. If we're going to count them, we might want to make a counter variable, and wow, that was shouldn't have Control-C'd that. Okay, anyways, we'll just close this. I guess I crashed the program by Control-C'ing. Anyways, what we can do is now just maybe make a flag for printing and just say don't print. So don't print equals, well, just make it a bool. Okay, so don't print. Now then this is going to be awkward. If not, don't print. Okay, let's just call it print, so we don't have to do a double negative. It just confuses programmers to put in the double negative. So okay, if print, we print out the solution. But regardless of if we're going to print it or not, we can add to our count variable. And count, it'll initialize here to 0. Now, we don't initialize it to 1 or anything. We're just going to let the stack always dictate that there's a new solution. And then we can, of course, just see out the number of solutions at the end. And something like that should be a very nice routine. Now we don't need to print out number of no solutions anymore. You can just get rid of that because it can just print out 0 solutions. It's the same thing. So it's a more general message. So that's nice. So now we should be able to run this and maybe see that there are, of course we need to put that, turn off the print here. Okay, so there, we turned off the print. Yeah, this should probably be a size T. Okay, I mean, some nonsense is coming up with less than signed, unsigned mismatch. Okay, so now we're good to go. So I run this, I fix the window here, and what we can see is that the number of solutions 0, 1, and 3, which we know is right, it's not printing the solutions. But what we can see is the program is just running. And it's running, and it's running. And we see the memory here is growing. Now, there can be some reasons why it's... But again, it's growing by marginal amounts, hovering at about 1 megabyte of memory used here. Again, this is a debug build. We're not going to want to wait on this. I don't know how many solutions there are. Again, 60 variables, potentially 2 to the power 60 solutions. And remember, we're checking kind of inefficiently that we get an unsat before we stop going down. It's like a tree of solutions. So we have one solution that we know, but then we kind of go through a big tree of different possible solutions. But we have to get unsat for every branch that we don't go down in the tree. So it's not exactly the most efficient thing ever. You see the memory went back down. It's just because we're using lots of vectors and STL code here, stuff's allocating, but there's no memory leaks. Of course, I'm not using even the new keyword or global variables or anything. There's no way there could be a memory leak in this code. Okay, the only question then would be, okay, well, can we make a 64-bit release build? Can we get better here? Can we hope for something? And we're going to actually move on from this. We've got 2SAT working. We've got all 2SAT. We have counting 2SAT. We have really gone all out in getting really elegant, efficient 2SAT algorithm. I'm going to post this code on GitHub. Maybe people like this kind of algorithms and they like to play with this stuff. They like to see good, efficient, elegant implementations. We can do better, actually. This is not the most efficient, elegant, but it's decent, actually, and that's kind of what counts here. Uh-oh. Did we get a warning? We got a warning on compilation here, and yeah, I don't like that. Now, again, we're seeing the same output. Basically, this is like when you just run it in the background and you hope you get a solution, even if it takes the next, 10 years for it to come back. So that's kind of the bottom line. We've gotten to the point where it is counting solutions reasonably efficiently. Again, we see this very nice, clever algorithm for doing the all 2SAT. If you know of a more efficient way, tell me, because I don't know. All I know is there's supposedly a paper. We can even put it in the chat here. Where is this? It's Feder. If you guys know Feder, it has network flow and 2 satisfiability. So here is this paper. But again, it's a dense paper, and if you want to figure out where this is going to give you the clue for how to do this without doing this kind of algorithm that I do, where you just kind of block a solution. But I don't like running strongly connected components so many times. I feel there's definitely a better way to enumerate just using a dependency graph. What we should do is we should start printing graphs here. So I should get graph v's out, and we should make some dot files, and we should start looking at the graphs so we can talk about what is going on here. But since I promised that we're going to do assembly language, maybe we should start moving towards a self-modifying code model and actually doing that, because that is really kind of what's interesting right now. I don't know if people are more interested in looking at graph theory You can do that, but I think that's also really crucial and interesting. Or you can just take my word, or you can take the Code Golf Stack Exchange's word that these, 0 solutions. So this is no solutions, 1 solution. Well, we can even say 1 unique solution, 3 solutions, and many solutions. A great many, because it still hasn't completed. I don't know if I want to let this complete. Of course, I would like to know how many, but if there's like 2 to the power 50 solutions, then this code needs to be optimized to be truly efficient. I don't like it very much in terms of saying it's maximally efficient. This is not efficient because we don't need to build SCCs here. We can start combining code. Maybe we should do this after, though, because I think we should go right into self-modifying code. I think it's more fun. It's kind of an opinion. Should we micro-optimize code? Should we do a self-modifying code model and go right into the assembly language? These are questions. But let's do a self-modifying code virtualization first. We can start writing assembly language. Maybe that's what is the most interesting, but maybe it's too fast to start writing assembly if we can't actually use C++ to write this out one way. And writing assembly probably will use 64-bit. I don't know, 32-bit we can do as well. It'll be just more work to actually get it to work both ways. But the idea is that we're going to model this problem first. Now, as I say, I have this modeled in Python, and it's kind of complicated, to say the least, but it's kind of a fun task. So here we go. Self-mod VM2sat. So we're doing a virtual machine, which means we're somehow going to simulate this, right? And of course, we're going to return the same value we return for 2sat, a solution, a single solution. The counting and all the others, we're just going to assume that this is good enough right now for counting and all solutions. And as long as we have anything that does one single solution, like this, we can use it instead of calling 2sat here. So we call 2sat here, and we'll just swap those out with a lambda function very shortly. In fact, actually, why don't we just do that before we get into this? So, of course, we're going to have our solution vector here. That's the basis of the function. And then we're going to need to start having fun here. I mean, one thing we also know we're going to need is we're going to need to get the successor graph. So, I mean, perhaps we should generalize this in a different way, but it doesn't matter. We need the successors. We know that. We need the clauses. Same function prototype. And in fact, we want to take this function prototype and just say, well, hey, this should be able to take a function prototype too. So just f is our function prototype, right? Or it's going to be a standard function. And it's going to, what, be standard vector. So this is another nice generalization strategy. Oh man, messing up the templates here. So it returns this. Did I get that right? Yeah, except close template somewhere here. Yeah, that is a really messy thing to put there. Again, we should probably type def some of these things. Okay, but it should be able to call it now. So it should be able to call 2sat. So now any 2sat algorithm, not just the targen one, but again, we're probably going to base this off targen, but it's going to be completely different in how it actually works out. And so now we can just say 2sat, right? So this should work. A little test here should tell me if it does work. And it does work. Okay. And now go into the next phase here. The next phase is going to be this function, because now we can pass this function if it works. So we're going to virtualize it, and this is really crucial. Before you go off writing assembly language, you have to decide if it's worth your time. So the question is it worth the time? Because debugging assembly language, some people like it, and I kind of like it, but it's slow. It's just And I'd rather get this done quickly, and so that's kind of why I modeled it in Python first, but and that took a while. That was not easy. This is a totally different mindset, doing self-modifying code. So now we're actually doing self-modifying code. We're going to take this algorithm and we're going to say, hey, any graph algorithm with a directed graph, we're going to turn it into a control flow graph. So instead of actually it has a stack here. So it has a stack, but there's another stack, and that's the one here, the actual stack of our C++ program. 2 stacks. No, we want 1 stack, okay? That's going to be, of course, when we're simulating it, of course, there's going to be 2 stacks, but it doesn't matter because that's just a simulation. So the extra stack is for the simulation, not the actual code if we change it into assembly language. So if we can get our self-modifying code out of virtualization, there will just be 1 stack, and that's going to be the nice thing here. So let's do it. Let's immediately start solving this. We have the successors already. So now we're going to need to build what we're going to call it a code blueprint. So we want to build our code blueprint. That's basically the whole task here. Second, we want to write something that executes the virtual machine. Well, we know how that's going to work. We're going to have an instruction pointer equal to 0, just like the instruction pointer in assembly language. We're going to make an assembly language, our own assembly language with just a few instructions in it. So, and of course we're going to have like some instructions. So that'll be here. We're going to have a vector well, we are probably going to use a data structure here, or a union. Actually, a union is pretty nice. It's so fast, right? So we can just make a union, and we'll call it, VM instruct. So our virtual machine instruction. I'll put it here. And what is it going to have? Well, we're going to have 2 fields here. We're going to have one int opcode, and then we can have, actually maybe we shouldn't make it a union because, well, it really depends how we want to do it. There's lots of ways of doing it. But as we build opcodes, we're going to just start stuffing things into the union. And we can just say we have a vector of these instructions. And we just want to get this done quickly. So we're going to get this job done as fast as humanly possible. And this is not easy what we're doing here. You're going to see the mindset is going to be totally out of the ordinary, but it's totally instructive to actually taking directed graph problems in just general graph theory and converting them into a self-modifying control flow graph. Totally unique, because a control flow graph is a directed graph, but you can't necessarily just take any directed graph and say it's a control flow graph. There will be infinite loops. Again, you have to put some meaning onto the nodes, especially where there's branches or loops. You have to put meaning into it, and we're going to do just that. And it's going to be tricky because we have a stack, and a graph doesn't understand the concept of a stack, but we understand the concept of a stack. So we're going to make stacks work for us here. So the first thing we want to do is, in the tar-gen algorithm, the first thing it does is it actually calls strong connect for every node. So again, you can go to Wikipedia and look this algorithm up. It's very classical, very famous. This is a reasonably decent implementation, not perfect. There's things we can improve here, but it's good enough as a prototype. And that's all I did. That's why I'm using for each. For each is good for prototyping. I wouldn't necessarily want to say it's going to produce the fastest code. I don't think the compiler optimizes it always in a perfect way. But anyways, it works, and it's a nice prototype. So this strong connect calling by everything means we're going to want to have like a root node of the graph, which calls every other node. And so that's going to be a good starting place. So let's do that. Let's make we've got our instructions here, and we need like a call instruction. So perhaps we should make an enum opcodes, right? And the first one's going to be call. So, okay, call equals 0. There we go. So now we can actually make an instruction with this union, and its opcode call is going to take an address, and that's easy enough. So int address. So right now our union is not going to work out here because we need to like start putting structures in here. We can just put anonymous structures. Again, there's different ways of doing this. Like maybe not everybody might agree this is the best way. Maybe we should just put the arguments in the union. But I think this is kind of clear to read. So I'm just going to put it like this because I think it's clear to read. And we could just call this the call op. So if it's call, it's going to have opcode and address. And so now we can just go in a loop here. So the loop will go through... maybe I should stop using for each. I don't know why I enjoy using it. It just feels like it makes it kind of like a functional language in a way, and it's just kind of neat. Although I don't argue that that's the most efficient ever. It's probably not, but it leads to some compact code, and I don't think it's that unreadable. It's relatively straightforward to read. So that's the opinion here right now. So okay, now we're gonna go through what is this. Again, probably should be using some type defs to avoid really ugly looking stuff like this. But we're gonna have a pair of integers, of an integer and a vector. So we're going to go through each adjacency list in the graph. So every node in the graph, we're going to get all of its successor nodes as a list here, as a vector effectively in C. So we're going to go through like that, and we'll call this P. So now this is where we're going to start building instructions. So let's build our instructions. We're going to take instructions, and we're going to do something to push onto that array. And we can do it like this. We can do push back. Let's capture it. Again, why I shouldn't be using for each. There's probably lots of reasons. Because adding lots of functional calls. If the compiler was really, really clever, it would optimize all of this right to the iterator code. But I don't know. I don't know how clever the Microsoft's latest C compiler is. I hope it is that clever. So what do we want to push onto this array? Well, we're going to push call and some kind of an address. And well, what we're going to have a problem with is we don't have the address. So here's where the next really... This is where we're going to get really sharp right here. What we're going to pass is a lambda instead. We're virtualizing right now. We're not writing assembly, so we could just pass a lambda. Yes, it's kind of not really realistic. Maybe we should we're building like a blueprint of code because we're virtualizing. And again, we're going to build even a better blueprint in a second. This one's not exactly a blueprint, but the way we're going to do this is we're going to say, well, hey, this doesn't take an address that's an integer, like kind of the next instruction. Again, we don't have assembly code, so we can just say the index in the instructions vector. The index is enough to tell us where the next instruction will be, or where it's going to call. But what we'll do here is we'll actually make address a lambda. So here we go. Standard function int void, right? And there we go. Now we have our address. Now we're going to push in the back of it. Yeah, we want to push a VM instruction with a call op. So ooh, can we write an initializer for this one? Obviously we want like call, and then we want like some kind of a lambda function. Let's just make our lambda function, and we're gonna call it make node address. So we want to make a node address. We'll throw an extra parameter in here for now. So we'll call it X and Y, but basically we're going to find the base address of a node and we're going to add some value to it because we're going to need this a lot. If you think about it, as we're building a control flow graph, we're going to need to be able to make node addresses. And this can actually, Actually, this is going to return a lambda function, I suppose. One way of just one way of doing things here. Make node address, and this will say have x. Well, it'll be p dot first and 0. Okay, so it's going to be the first instruction. So that's why we put 0. 0 is going to be like the offset. So we can even just say offset here. So here we can actually, we're going to need to know the node addresses. It's like we're compiling it, you know? The node addresses are the jump instructions and labels in assembly language. They aren't something you know until you actually calculate how many bytes each instruction is and all this. So we don't know it yet, but we're going to know it eventually. We can just make a map here from int to int and call it node address. And eventually we're going to know those node addresses. And we'll even just fully specify this. We make a standard function. And this standard function will take a... well, it's going to return... We know what it's going to return. Int like this. So it's got to be, of course, the address here. So we can just say node address x plus y is being returned from this lambda, from the function. And of course, we need to return it as a lambda. So we'll just do it something like this. Now, the key here is we've captured this variable here. And so notice how we don't try to do this here. Like, the first thing anybody might wonder here is why this is not happening over here. And there's a good reason why it's not happening here. Because p dot first, well, we would need to capture p. And in general, we would be capturing a whole pair. And, you know, it's actually more elegant in this case to just call with p dot first and then capture this value only, just this integer. So, and if we don't capture this properly, of course this won't work because we don't know which, we're going to make, you know, a bunch of these different call instructions. So obviously each one's going to need to refer to the right thing here. So here we go. Capture x. We can capture it, a reference. We could capture a copy. It really doesn't matter. What does matter is we return our function here. Now I'm getting expected a semicolon, and I'm not seeing where the issue is yet. Must have screwed something up here. I'm not seeing it. Oh, of course, here. Just showing me on the wrong line. No, it's still complaining about it. Okay. Oh, well, why we don't have, so I might as well put that in too. Okay, so we're capturing stuff. I mean, actually, we might as well just capture a copy here. I don't know why I'm doing like that. And it definitely does not like what I'm doing here. Oh yeah. What am I doing here? You know, there. I don't like using auto, but we can just use auto here. So obviously this not necessarily the syntax we want to use here. Again, I can make another lambda that returns a lambda. It gets really, yeah, I guess so. I don't see why not, though. We can always make it a standard function, too, if we don't want to use auto. I'll capture that. What else do we need to capture here? Semi here. Aha, and now this make node address. Again, we're just making a little bit of a mess by using for each here. because you see we have to capture things all over the place. And lastly, we're going to need to, from type, okay, so it doesn't like this. Okay, it doesn't like this either. Yeah, we could make some constructors here. Yeah, that might be the best option here. I'm just trying to think what's the most elegant way that we can do this. I think this isn't bad. Seems kind of elegant. Because we could just say, you know, this dot call op opcode equals opcode. I think this is probably about as elegant as we're going to get for this. And there we go. So now we can actually construct, and now we don't really care. If it's not a call op, we can actually call this something else. If there's another op that's going to use the same thing, the same argument, it'll be okay. We'll just use the same thing. So we can actually change this to this kind of scenario. Now, is it going to like that or not? Okay, I guess it doesn't like the auto. Shouldn't have a problem with auto here. Opcode type. Well, type is... Yeah, okay, I guess it really... I don't always like using auto for this reason. It's, you know, when you know what something is, you know what something is. And this is like returning a... Okay. Yeah, well, this is why auto exists, right? So you don't have to go into this level of detail here. Okay, I think that's right. Yeah, okay. Still doesn't like it. Okay, the destructor. Okay, we're getting, oh, did oh, probably that's why it wasn't working. I forgot to return the value. Yeah, that's right. Okay, and attempt is, I think we need to make it virtual. Oh, no, that won't work in a union. What am I doing? All right, this is, yeah, these are the annoying things when going to C++. Okay, the destructor, this deleted function. Well, the other thing to do is make classes or something else. I forget why this is, but again, people don't really use unions much in C++. So this deleted destructor, there's a technical reason behind this, and okay, we're gonna have to fix this though. I guess it wants a copy constructor too, or maybe an empty constructor. Yeah, it wants a copy constructor. That's probably the issue. Okay, we're getting some warnings here. Maybe we should clear those out. Uh-huh. Okay. The problem is this should be a size T. I mean, this isn't a big deal. No, didn't fix it? Oh, wait. That was wrong. This should be a size T. Well, I mean, it's not wrong, but everything should be a size T here. Yeah, basically, because I'm doing the proper enumeration this way. Now, again, we could change this to iterators. We don't need to use indexes, but we can use either one. I mean, uh, the iterator might be more efficient. So, okay, no more warnings. Okay, look, so we fixed everything. That's not too bad. So, as much as this looked like it was going to be a real pain to do, I mean, okay. Let's just call this copy. We need to make the copy constructor, though. Definitely concerned. This can be quite tricky at sometimes, so I don't think we need the empty constructor because we don't actually want to allow this. This is a huge problem. If we don't want to make a no operation, well, I mean, that would be actually not a huge problem. We just make it a no op or something. So we're writing our assembly language virtual machine before we get our hands into the actual assembly. And here we go. This, oh, we're saying call op right now. Well, we actually have to have an opcode. Actually, I think we're going to need to make this a structure here. The more I think about it, obviously. Well, again, this is a kind of a design process. It's better to go through it and just kind of respect that it's something you do have to go through. So we just call this args. Totally just redesigned the whole thing. I'm hoping this copy constructor is legit here. Should actually be opcodes. Fine. And this will be args. Technically, in this case, yeah, we know it's an address. Okay, but as we generalize this, we're going to have to rewrite a little bit of this. Okay. Uh-oh. Now, the default constructor. Okay, again, there's so many like little tiny technical details here. Yeah, I don't know if I want to learn all these details about structures and unions here. This is wait, it's saying union still, but I've gotten rid of it from being a union here. Now it's just structure. Do we give up on trying to v2? Why does it keep saying it's a union? I don't understand. I've changed it to a class. You know, I feel like I'm doing everything by the book here. All right, I don't want to get caught up on this. We're going to get through this right now because I want this one done. Yeah, somehow putting the union in here. No. Oh, I see. Okay. Yeah, somehow I just make everything public, like it's a data structure. Okay, I mean, I don't want to get into all these like little details. You can go look them up, but actually, some of the stuff kind of, yeah. C++ has gotten complicated, and some of this stuff has gotten kind of discouraged to somehow program in this kind of style, sometimes you're supposed to use a lot of the modern constructs, not try to go back to data structures and whatnot. But let's just see if we can even get rid of this copy constructor. Yeah, as if we do it, in fact, we can get rid of the default, I think, too. Okay, so if we do it like this, we can put our constructor in. Now, though, if I put this union in here, okay, it works. Okay, great. We're going to be done with this. Uh-oh. Yeah, okay, we need to... Okay. Do this right. I'm just doing it too fast, that's why. Okay. Aha, now we're back like in a loop here or something, right? So yeah. Oh man, it's gonna punish me for every little thing I try to do here. Unless I put copy constructor too. Okay, so we do need to put the copy constructor, and that should be just fine. I mean, in fact, actually, we may want to just take the arguments and take it out. Anyways, the idea is we want to get onto this stuff. We want to get onto the fun stuff. We don't want to be stuck with some silly little design issues around getting the right data structure for the instructions. It's a simple data structure. It doesn't need to be complicated. We already have our control flow graph calling every node. Now we're going to start writing our node code. So one thing we want to do now is just say like the start of the topological part of the function is going to be at the length of the instructions. Python here. Size. So okay. Again, we can make that a size t. So now we've got the length of the instructions here. Now we're going to actually start adding instructions that are going to actually be a little more meaningful, but then we're going to go to the blueprint. So 2 instructions here. First instruction is going to be a data instruction. Now, we can actually use registers. There's like lots of choices here. There's so many choices. This is like mostly just going to be one example. When we go to assembly language, like things are going to really get more compact here. But we can put like data and, you know, like even null or something here. Basically, we need a value, like almost, I guess, basically we need an index value. Probably we'll just use, probably we'll use, actually, here's a nice value to use. The most clever value to use is going to be the successor's size. So now we've added, of course we can't do it like this, we have to use our constructor here. So we're adding this. So data is our next instruction. So call takes an address, and we've virtualized it even more by making it a lambda so that we don't have to deal with the compilation process. We could deal with compilation and put a real address in there. We're like, let's just wait and just do it later. We'll store all the addresses here using this node address array. So, okay, we figured that we have that already. We're going to need to fill the copy constructor, but now we've got another instruction here, data, and immediately we could write our virtual machine. That's very easy to write the virtual machine. What's hard is designing the code to run on it. It takes 2 minutes to write the virtual machine. Putting except for this data structure, this is a real pain in the neck sometimes if you if you want to use things like unions and stuff. Again, if you want to be like kind of efficient and not use like C++ ideas with inheritance, and again, actually that's the right way of doing things is to use inheritance for the different argument formats, not unions. I'm somewhat of a C programmer, so I like to use the C ideas, but it doesn't really work very nicely where C++ starts deleting destructors and doing strange things like that. But what we can do here is just say, okay, we're going to start adding more opcode argument pairs, and this time it'll take a size t, and the size t is going to be for the data, I guess we'll call it. And again, we can just set the opcode. We can set the arguments dot, and this is a single argument one, so oops. So since it's single argument, we can just say let's see. Yeah, this is going to be a bit tricky if we don't use because the problem is we need to know which opcode it is to actually implement this copy constructor, right? So, because we won't know which field to copy, and yeah, we don't want to kind of mess around with this stuff because we're unioning a function, all these pointers versus like this one's going to be a size t, just data, and this is going to make the copy constructor really painful to write. In C, this might be easier. Again, we should think about that right now because we do want to fix it immediately. Okay, so this data here is going to be index from strongly connected components. So we look at strongly connected components. We have a variable here called index. Well, we're just going to like move the EAX register this index. You know, we're just actually storing data as just useless code. It's just moving it into a register that we might blow away. But by doing this, we need less registers. The goal is going to be to use only one register. But if we use more registers, we wouldn't even need this data instruction. So, okay, the next piece of code we're going to write in our virtual machine is going to be a load instruction here. And, oh, no, sorry, not load. We're going to need a jump instruction, rather. This is like, it's called all the different nodes. Basically, the control flow graph is kind of like this ladder that calls all the nodes, and those nodes are connected in the original graph pattern. And then eventually it's going to return from all the functions, go through all that. And when it drops through, it should go to sat. It is satisfiable. So now we need a jump instruction. So again, these are all like unsurprising type of things that we're putting in here. Again, it'll just be identical to our call instruction, so we'll just call it jump. The only difference is going to be that it doesn't return anything, and maybe it should. Maybe we'll have to think about this actually, if this should be return or jump. But the problem is if it returned, well, we need to return sat or unsat or something. Right? Obviously, somehow we're going to have to indicate if it's satisfied or unsatisfied. There's several ways of doing it. Could use another data variable. The idea, though, is we want it to go back into our C code. So a jump instruction to some sat value is okay, though. So we can, just can have a special label here. Just say we have like a const int sat equals -1, and I think this probably is good enough that we do something like sat is -1 and unsat is -2. In other words, these are invalid instruction pointers. But when we do go to assembly language, we'll probably need to actually fix this to actually return something and just save the value in a variable. In fact, maybe we should just make a boolean variable that's set. We can, either way, we can just do that. So, and then we would just return here. So one way or another. But since we're not going to be able to call our virtual machine, we're going to do this differently than the assembly language. Because the virtual machine, like calling address 0, we could do something like that. But that's kind of silly because it's going to start with instruction pointer at address 0 in an empty stack rather than a stack that already has a value on it. So again, we're trying to be kind of close to the way hardware works. And so that's why I'm doing it in this manner. So maybe you can appreciate that. And that's, again, we've just added an instruction to our virtual machine, jump. I think it's going to take us around 13 instructions, and we will have the entire thing in some pretty complicated code. Now we're done with the instructions we can just emit. Now we need to write a blueprint for a node. So this is like really where you start writing self-modifying code. Right now you're saying, okay, great, you're simulating assembly language. No, we're going to self-modifying code, and it happens right now because now we're going to actually make another array of instructions, but these instructions are going to be lambdas because we can't even know the instruction we're adding fully because the arguments, we have to do a double layer of lambda functions here. Again, we're kind of skipping compilation in favor of just using some clever lambda function stuff. So we can actually just say standard function here, which returns a VM struct, VM instruction, and it takes an argument, which will be the integer x, the node. So you take a node and you return an instruction. So we're going to actually really make some complicated simulation code here, and we're going to call this the blueprint. So now we start constructing a blueprint. So we've got blueprint as an empty vector. Let's start dealing with this. And we're going to do a bunch of stuff at once. Now, there is no good self-modifying programming language. If there was, this code would look so beautiful. And we should write like a pseudocode, actually, to describe this beautiful code that we're writing. So the thing we're going to do here is write the blueprint, but we're going to need to make a bunch of labels. The only way to make a good label is to say something like here the node address location, is equal to the length of blueprint, which, we do it like this. And so now what we're going to have is a lot of these instructions. Everywhere we need a label, we're just going to say, I want the blueprint size. It's 0. Okay, fine. We have a 0 blueprint size. In fact, we haven't even started going through nodes yet. So what we're going to do at the end of this, and we should write that first, actually. We should just do that. So we're going to go through all the successors in the graph. So we're going to enumerate through the successors. We can do that again with the standard for each. And we say successor begin, successor end. In fact, we could probably do these at the same time. We could build the blueprint first, but for this start topo, I think we can't. So we'll have to kind of look into that. And what we need here is the instructions. We're going to need the blueprint, and we're going to just apply that blueprint. In fact, we're starting to get there now. Most of the rest of it's going to be discussing self-modifying virtualized code. Again, afterwards, we're going to get straight into real assembly language. So it's kind of a step-by-step process here. Now, why did I put that there? That's not right. So the blueprint is a vector of functions and instructions, and so that's what we want here. Okay, f, it's a function. So, oh, wait, sorry, no, we're going through instructions. No, what am I saying? We're going through successors. We wanted this. We're gonna have to do another for each loop to actually call those lambdas, yeah. All right. We're ready to call our lambdas. So we've got like a blueprint full of lambda functions that need to take an x value, and our x value is going to be p.first, right? It's going to be the label of the node. So we're going to pass the label of the node to each one of these values in the blueprint. But at the same time we're doing this, remember we said we need the node address? Well, the node address of p.first, the first thing we're going to do, is going to be equal to the length of instructions. So we say instructions dot size. So we've actually got our node address taken care of here, if we capture it, of course. So now we actually know the node address. The first node for this node in the graph, the first instruction rather, where it's going to be when we're going to insert them all in here, and we can actually do that using some clever STL trick here. This is actually kind of a beautiful trick we can use, because we can actually say we're going to want to actually call for each one, and we're going to want to extend the instructions. So instructions.insert, we know we already want to do that. Where? Well, we want to insert it at the back here at end. And what are we going to insert? Well, we're going to need to use standard transform. We need to apply all the lambdas. Is there a better way than standard transform? Well, if there is, you can let me know, because I don't know. The first thing that comes right to my mind is standard transform, because this is an excellent function. It takes, ooh, do we need a destination for this? Is there no way to first, last, first to destination func, huh? There should be a way to do this without, again, we can't obviously change the blueprint here. It returns out IT. I guess we need a temporary buffer, of course. We're going to need a temporary buffer for this. So, okay, but that's no problem. So we can actually take the blueprint.first, blueprint dot end. Okay. And I think we should say begin, not first. Okay. So we go from the blueprint first end, and we're going to have like a built blueprint. I don't know, we can call it. So our built blueprint can be a vector of, what's it going to be? Lambda functions. And actually, it's going to be a vector of what? VM structure. What's inside instruction? How did we define this? Yeah, VM structure. Okay, so because obviously the virtual machine instructions. Okay, and then here I'm going to take those virtual machine instructions, pass them in, so we have our temporary buffer there. And now we need another lambda function, which is going to actually just apply the function. So this is kind of really clever. We know that these are lambdas that are generating actual data instructions. And so what we can do here is return, the blueprint is going to have inside of it these functions. So that's going to be our parameter here, f. Okay. Oh, it doesn't like it still. Well, not yet. Not yet, but soon. Soon it will. Oh, isn't that a problem? Yeah, okay, so that we can't do this all in one line. That's just silly. What we can do is then say build blueprint.begin. Again, there's definitely seems to be more efficient ways of doing this, rather than building a whole nother extra vector is an intermediate variable. It seems kind of not ideal to me. Because again, we could just add them one by one as we build them without having to save an extra vector. Have to think about that one. I'm sure there's a better C++ way of doing that. But what we can do here is just say f of what? P.first. We'll just even say f of x. I like that. It looks really nice to just say int x and size t, right? Isn't what we're calling it? Okay. And there we go. Now we have done it. We've got the okay. There we go. So now look at that. We've transformed into this variable, into a vector of VM instructions, a vector of things which return VM instructions. And the reason, as I said, we need to do this is so that we can avoid dealing with the assembly language implications where the instruction addresses have to be calculated, etc., and so forth. When we build assembly language to do this, we're going to have to kind of build this blueprint with opcodes. It's going to be really messy. And again, if each node has the same size we can pre-compute. We know the offset of every instruction. We can write a math formula that calculates every address. But if, for example, the number of instructions per node was different, then, well, we'd have to decide if we want to pre-compute them all or what we want to do about that. So again, yes, there are ways of pre-computing, but if you're using the successor edges, then it won't work. But if you're just using a fixed node, which is what we're going to do, because emitting the successor edges isn't strictly necessary, we have the successors here, and if we do that, it will make our life more complicated. Although we could build the successors hard-coded. Why is another good reason we don't want to do that? Well, we may want to reuse our graph. And it doesn't matter if there's extra nodes. If we built 10,000 nodes, we could do a 10-node graph. And it's totally reusable without rebuilding the blueprints in entirety. We'd only need to rebuild some instructions which self-modified themselves. So that's actually a really clever reusability aspect. If you put the edges into the graph, it won't be reusable at all. It'll be better to just regenerate it than to actually try to reuse it. But this kind of graph you can really seriously reuse. So, okay, let's add some more instructions here. Now let's add our first instruction. We've just started here, but basically we're going to get x. We're going to get the node as our argument. So again, we could write this virtual machine too if we want. It's kind of a fun task here. Didn't remember to close that. If we want to write our virtual machine, we can just do it straight up front. So we've set the instruction pointer. Actually, we set that too early, didn't we? Because we don't really need it up here. The instruction pointer and the stack, those are the live things. Of course, the instructions as well. But we can, we've got our instruction pointer here, and we can just maybe make a while loop. While instruction pointer is not equal to sat, which is -1, an invalid instruction pointer in this context, and it's not equal to unsat. Again, this will be different when we go to assembly language, but so while it's not sat or unsat, we can just kind of go in a loop here. So we can say actually we're going to just make a switch statement, so this is nice. Switch instructions inst pointer. Again, it'll be a vector. It's a vector already, and we can just say opcode. So we switch on the opcode, and you can see how easy is this going to be to make. Well, very easy. Call, well, it's easy if we have a stack. So what's our stack going to be? Well, our stack is just going to be pointers, basically. We can even make them integers even, so actually we should make this a size t. We'll make the stack size t's as well, I guess. Again, it'll be a standard stack of size t. I mean, something like this, it's enough for a stack. It can just be some kind of data values. And remember, our data values are size t's as well, like whatever the pointer size is should be sufficient for this model. And so we call it s, and a call instruction. This is very easy. If we want to call something, s.push, instruction pointer +1. The returning instruction is the instruction after where you called, not the same instruction. You have to add 1, and then the new instruction pointer is going to be equal to instructions of at that location dot arguments dot address, and it's a lambda, so we call it right. And this should return, oh, it returns an int. Oh, that's okay. If it should return a size t because we're using it as technically, I mean, it's all technicality type stuff. It's not a huge deal. Yeah, technically this should be a size t everywhere, I suppose. Where else do I have that right now? This is an int because it comes from the graph. If it's a label in the graph, we're allowing it to be an int. But if it's actually an index into a vector, or which again the instruction pointer is, we want it to be a size t. And since we're going to push on the stack or instruction addresses, that's why it can be a size t. We won't use the stack for really much anything else because we're going to use self-modifying code to store all the data, which would be, again, you could use the stack. I mean, there's always going to be several different ways of doing it, but the problem with using the stack there is the stack's going to actually keep extra stuff on top of it, and we'll see. So there will be some issues with doing that. So, okay, we've got the call instruction implemented. What else do we have right now? We have a return instruction and we have a data instruction. Well, data is very easy. Again, another thing we'll need is like a register. So easy peasy, we just put register here. I guess, oh, well, don't use a fixed level. Let's just call it reg 0. So we're going to have just one register. And so if we see a data instruction, we can just say, okay, register 0 is going to equal to instructions ins pointer dot arguments dot data, right? So okay, that's the data instruction. It contains something in there. Okay, so there we go. That's all that's going to be inside of our register. Put my break statements in here. Okay, next we have to do the jump instruction. This one's very easy as well. This one, I think it's easier than call because we can just, it's call without the push. There we go, with an address. Okay, we're going to need more instructions, and we're going to get to those. So as soon as we implement, we'll implement the instruction. But you can see all the instructions, the virtual machine is going to be really, really simple. The only question is, are we using lambdas or something to avoid these address calculations? Kind of like compiling it on the fly. It's kind of an on-the-fly address calculating virtual machine to avoid having to do a compilation process. It's perfectly fine for modeling of a problem. So again, that's what we're doing here is modeling before we write the assembly code. So now we add our first blueprint instruction. And that instruction will be a data instruction. And that's basically the intuition here is that we're going to need an index. Again, we're going into Tarjan's algorithm here. And the first thing it does is it sets the index to the low link and to the index, and it increments the index, and it does set on stack equals to true, but we aren't going to concern ourselves. Again, the stack is the whole new concept that we're rewriting here. Without the double stack, without this extra on stack, we're going to rethink all of that with self-modifying code, and that's going to be the beautiful thing about this, and kind of part of the point of doing it, this exercise. So we're going to put a data instruction here. Again, now the blueprint is a lambda function already, so we're going to need lots of lambdas here. No problem. I mean, again, this is prototyping. Prototyping, you do what you have to do. So this is actually going to return a lambda. It's a lambda which is going to return a lambda. Oh, no, sorry, it's a lambda which returns a VM instruction. I was saying a lambda here. Okay, so what VM instruction are we going to return? Well, we're going to return the virtual machine instruction, which we construct with data, and we can put null or something again in here. Again, whatever we put, even -1. So this is the index here. We put the size. Which we should not have done. Actually, this is a mistake. Okay, actually here we can put -1 because we know the index is going to start at 0. Wait. Yeah. Okay, this actually is not used yet, but what we're going to put here is the start topo +1. Yeah, I realize I misaligned things here. That should not be the index. This is actually going to be the what we're going to call the topological sort pointer. So this is going to be the let's just spell that out. So, okay, that's to come. Again, this jump instruction to sat on success, we're going to end up making a jump chain. We can actually, again, we don't even need to do this, but for fun, we're going to build another using self-modifying code. We're going to build like a chain in reverse topological order, which assigns all the nodes. So we're going to fix all the SCCs, and then we're going to write something that just causes a reverse topological enumeration of them, which jumps to the next one, to the next one, to the next one. It's going to be a very clever way of doing things. So, okay, the next stage is coming into play here. Now, we are going to put in... Okay, this lambda is not being satisfied here. Why is it not liking this? Takes a VM instruction. Oh, int, yeah, okay, that's why. Okay, we don't use the integer here, but it doesn't matter because we're going to need it sometimes. So again, the blueprint is very, very general here, taking an integer, which it's not always going to need. It only needs it when this depends on the node itself, like if we're getting the successors, or maybe we're building a solution vector, or something. No, actually that doesn't, yeah, that depends maybe, well, we'll see. But of course, certain aspects will depend on which node it is, where we actually need that x value. Some instructions are just generic, so this is generic. Let's put our next generic instruction in, because we're going to need about 30 or 40 of these at least to get this code working. So the next one will be a new instruction here. What we're going to do is we're going to need some kind of index variable. Where is... Oh, you know, I missed it. That's what I missed. I know, I was saying it before. Okay. Did I only miss one? Yeah, I missed one. It can be the first instruction. So before we even do this, we should have added it. So we could just say index is going to be a label, right? So we're going to make a label here. Again, that we just do that by taking the size of instructions. So we have a real label here. And now we can just add another data instruction and we're done. So that was what I messed up. So we do want to store the index somewhere. And as I said, this should start at 0. So we want to start the index at 0. And in this code, we're just putting some garbage data. It really doesn't matter what we put. So -1, obviously an invalid value since we're going to increment the index. And, well, I mean, unless there's more than 4 billion nodes, which isn't allowed, or if it's 64-bit, there's not enough memory on the system to have that many nodes, so it's okay. Let's see. So next instruction. Again, we're always going to put the int x in here. The next is going to be a load instruction, and we haven't written one of those yet. So let's write load. What's load going to load? Well, it's going to take a something returning an integer, I guess. So yeah, this is like, yeah, actually this, as I said, should be size t. In this case, could be an integer. We could make this a size t as well. Although actually I think that's unsigned. So we're going to get like a -1 initialization will actually be not really -1 if we do it that way. We have to kind of make a decision on this, actually. It doesn't actually matter, though. We could actually put 0 in here, and we don't care, even though it looks like we're reusing index 0, though. It would be bad practice, though, because in general, if we're debugging, we don't want to see 0, because one of them actually has to be 0. Or we could use 0 and start at 1. The indexes don't have to start at 0, and anything is okay. FFFFFF will be our bad value. And here we're going to load. Now, what do I want to load? Well, what I want to load is the index. So So I just throw index in there and we're done. So this actually is a size t. Is this, yeah, okay. So again, index is an address. It's actually a address. So all load is going to take is a size t. So it's no different than data, actually. So never mind about needing a lambda here. We don't need one. And we're going to add the load instruction. So load is our third instruction. And we already have a constructor for it. Happy there. Somewhere needed to capture it. Again, it's 0. but just to be general, we make a label and we try to do things correct. So in case we want to change things later. So now we add a break, put a load in. Load is going to, oh, we didn't, okay, all of these are problematic because we need to put ins pointer plus plus. So we need to go to the next instruction, not on jump, but here we need to do it too. So there's really no difference between data and load except a subtle one. We're going to set the register. So our register is going to get instruction pointer, arguments, data. No, it won't, right? It's going to get something even more. It's going to get an indirect address. So we're writing our fourth instruction here, and it's going to be as simple as doing some indirect addressing here. So what we're going to do is get, this is actually a pointer. So index is pointing to index. So it needs to dereference that data. And then it needs to get the data at the data's data, right? So yeah, that's really confusing in a certain sense, but that's actually the instruction we want. We want to set the register to dereferencing this pointer, getting the data, and now go to the next instruction and preemptively put a break there. We know we're going to need it, right? And no, default can throw. For all we care, we don't want a default. If it hits a default case, that's a problem. So let's actually compile. All right, this is a problem. Okay, so I guess it needs to capture this. Okay, we've got a problem here. Okay, of course it's complaining about some things with copy constructors and other things. Yeah, I think because of the copy constructor, I'm not going to be able to use a union, and I should probably just go about making some classes already. Yeah, we should just do this with classes. Do it the right way, because otherwise fiddling with unions is just kind of annoying unless we're using C. But with C++ and where this stuff's happening, we don't want to go there. What's the other error, though? We're getting like a real error here. Okay, node adder should not be int to int. It should be int to size t. No problems there. Okay, that fixes one. Oh, there's another size t issue here. Oh, this is no. Yeah. Okay, I'm still getting some algorithm. It must be the transform statement. Ah, there's something wrong with the transform statement. I guess it's with this vector that I'm building here. Oh yeah, and actually, yeah, it does return the vector. Of course, that doesn't help me because I still need to call begin and end. So I look quickly at an example just for standard transform because I've using Python too much lately and I've forgotten the exact details behind. Oh yes, okay. Yeah, no problem here. Oh, I did I forget an argument? So it takes the input first and last, the output iterator first, and a unary op. Output iterator first. Wait, as soon as I'm saying that, I realize that I've got a problem, right? So, so this should work. Yeah, I think, if I'm not mistaken, this should work. Yeah, I think we're good. Okay. Yeah, okay, we're gonna fix this. I don't want to be stuck on this, so we're gonna fix all the you're not using C++ the way it's meant to be used stuff. So, okay, we have a virtual machine instruction, and the arguments, well, we're just gonna have maybe some derived classes here. So it'll be like a adder VM instruct. So every time we need a different arguments for certain instructions, like data and load will share the same. So we only need one. The data and load will only be like a data VM instruct, and then call and jump will be an address virtual machine instruct. So we won't need that many of these, and we can just derive this from VM instruct. Oh, or can we? Yeah, okay. And then we can actually put our constructor in here. All right, we're being much more C++ aware here. Okay. Again, I want to just do this quickly, though. I don't want to make it too complicated, but we're going to get rid of any sort of unions from the mix here. Oh wait, we didn't want to get rid of that so quickly. We want to first put the address into the data structure here. So I guess these will just be public stuff, so it's okay. We're gonna, as I say, keep it very, very simple. All right. Okay, now I think I think C++ will stop complaining that I'm doing strange things with unions that it doesn't like. Now I'm doing normal things with classes, which it usually very much does like. And just put this here. And then we get rid of all this stuff, and that's the end of the story here. I don't even think we need the destructor, constructor, anything. Okay. This one has the data member. And this will be very useful as we move on here to not get jammed up on this type of stuff. So, okay, data, adder, data, just fill in the blanks here. And then we're going to make sure it compiles. One thing we're going to have to do is cast instructions. Of course, they're really, or I don't know, but we'll have to do something so that we can let the virtual machine process the arguments. So casting seems like a easy way to do it, but well, it's a safe choice because we know it'll work. So yeah, here is where the casting comes into play. So we can say this is an adder VM instruct. Now, actually, we can just cast it directly. Just do it like this. All right, we'll do it the correct way. And then we just use the reference to member operator. So we just use this all over the place, and we're done. Jump instruction. Okay, this one as well. Actually, just copy and paste this part. And now I think we have actually final working code in this regard. Okay, just change that to the right class. So now when we want to add new instructions, we're going to do it properly, and we don't have to worry anymore about any... Oh, I just thought I had it, and... Okay. Oh, yeah. I somehow totally blew that up. That is one long, ugly-looking thing going on here. But it's okay. Oh no, we're still getting a warning? After all... and we're getting one of these like chain warnings here where it's... 153. Okay. Oh yeah, no problem. Yeah, you get 100 warnings for some of these types of C++ issues where the type system has to... Oh gosh, still... Yeah, these errors are just not fun to look at. Wait, why did I think this is x is an int? This is supposed to be an int as well. Oh, yes! There we are, it's done. Okay, yeah, that's the exciting news. Yeah, okay. 1 second. This only takes me 1 second. I have my coffee capsule here, coffee cup here, and I need a coffee because this is heck of a bit of work to do there. All right, and that's it. The coffee will automatically be made here. All right, so I mean, come on, developers and coffee. This is like hand in hand right there. You can't beat it. So let's get to the next step on this. We've actually got working code, no warnings, no issues. The only thing is we don't have a whole lot of blueprint yet. So we're building this blueprint up. We've got a data instruction, a load instruction. You're going to see what's going on just in a second. We're going to watch the design of this thing unfold. So we're going to start with our self-modifying code right now. Finally, right? I know it's like the backbone of this. It does take some work, whether you like it or not. I mean, you have to get through that part. So we're going to need a new instruction, and it's going to be called the store instruction. So let's add a store instruction. And what this instruction is going to do is it's going to take something, possibly in the register, and it's going to write it to a data in a memory address. So it, like load, loads only from data. So you're only allowed to use a load instruction on a pointer to a data. A store can only point to a data, but it can store anything. It'll store something from a lambda. So we'll have to actually add another VM instruction for it. I guess we'll call it store. So here's our store instruction. And this one's going to say, well, hey, I need a lambda which returns a value to store, and I need a lambda which tells me where to store it. So I need to know what and where to store it. So we can call it data. I mean, it's a data function. Uh-oh. Don't change the name. Yeah, you get all these problems. Okay, so now I'm going to take the address here. I'm going to take data. And the order here is kind of arbitrary. Well, it doesn't really matter. So we've got yet another. Now we could actually derive this from the even the address VM instruction. There's a what? Unscoped. Opcodes is unscoped. It doesn't like that. I don't know. It's not really. It's an IntelliSense error. I mean, it's not really an issue. So okay, so we've got our store instruction. Let's use it. Let's make a lambda here. As we always, we're going to put an int x in there, even if we don't use x. I guess we could just put int and fill it in that way. Now this one, it's going to write the index somewhere. Where is it going to write it? Well, we've got this node address location. So, I mean, we can just actually use our function we already have here. Now, this is starting to get messy, and there's no choice. It's going to be complicated. We've got make node address, and so we're going to make the node address. So we're going to write our own index, our own node's index. Easy enough. Make node address. And remember, this returns a lambda. So we're calling a function which returns a lambda in a lambda. That's why it's like a double virtualization here, just to get rid of all the addressing issues, so we can just build these addresses on the fly, and we don't have to go through the instructions and keep track of which instructions need an address injected. Why bother when we can actually use C++ lambdas to our advantage here? Again, there's different methods to do this. I'm not saying this is the only way. It's definitely not, but this isn't a bad way. So what we can say is we want to make, no, we don't want to make that one. We want to make the node address like this. X and node address location, which is 0. Okay, for each node, the offset from the beginning of the node. So the beginning of each node is here, and we can add some offset so we can access any instruction in it. But we'll just make the node address for that. And again, the thing is, we're going to need to make this a store VM instruction. Yeah, probably we should derive this one from the address one. I think that's better, because we don't want to make a mess of all that class code. I want the classes to be relatively simple here, closer to C style, because we're going to go to assembly language, and you don't really like to mix and match C++ and assembly. It's usually you would do it more with C, where it's easier to do. So what do we want to store? Well, we're going to need another lambda. And that other lambda is returning the registers sub-0. They just return reg 0, which somehow would need to be captured. Uh-oh. So now, actually, we should define register 0 before here. Just realizing we probably should put it up there. How else are we going to double capture it? Okay. Oh yeah, make node address too. It needs to be captured here. All right, so it's going to get ugly a little bit with all the captures, but we'll manage, you know what I mean? We'll manage to make this look relatively nice and relatively understandable. Using the word relatively there, but I mean, such is life here. Oh, I botched something here. Okay, there we go. Unbotch that. Okay, a little bit of a confusing instruction. because what we're doing is we're storing register 0. What's register 0? It's the index. We just loaded this index. Again, it's self-modifying code. It's an index in the immediate data of the self-modifying code. And now we've actually written it to our own node, which right now is a blueprint still, so we don't even have an X, but we're generating that over here, and we're applying it. And so now, okay, we've stored the index. Now we're going to do another one of these. We're just going to copy this, and that's it. The next one. Where are we going to put it? Well, we're going to put it at the low link loc. And where's low link loc? Well, to be decided later, right? For now, we can just specify it here. We need to declare it. We need to capture it. But we'll define it somewhere down here. So we're not actually going to use low link loc yet. We're getting there. That's what we're saying. So we've now defined 4 instructions in the blueprint. As far as I know, there's going to be about 20 more, and then we're done. Then we actually have a working self-modifying machine, and then we just need to go to assembly language. So it's getting somewhere here, slowly but surely. So let's do the next instruction here. Blueprint. Well, the next one actually can cut to the chase. The next one's going to increase the index, right? We've now saved the index. So we've actually done, in this algorithm right here, we've done this line of code basically. But we need to increment the index. So we've done this. We haven't dealt with the stack because the stack is something unique. The stack is something we're doing specially. But we need to increment index, and we need to save it for the next thing that's going to come through. So we are immediately just going to do another store instruction. I'm going to just copy and paste that for now. And what are we going to store? Well, we're going to store reg0 plus 1, index plus 1. Yes, we could make an add instruction. That's so easy in assembly language. What we're modeling is control flow and stack and registers, and not, we're trying to mostly not even registers, but stack and control flow. We need one register, and so we're going to leave it be with that. But basically, we're going to say that these Lambda instructions that only do data transfer or arithmetic are trivial to put in assembly language. So since we can do this so trivial in assembly language, like, okay, this isn't cheating. This is actually, we don't want to make a huge virtual machine. So it's okay. The Lambda can do like some simple data transfer type instructions. And so in here, we just need to make node address of what? Index, right? So, and actually, no, we don't. We need to just put index. But this needs to be a Lambda. So again, we just make it a Lambda. I think that's that's all we need to do. So now instead of having to calculate something based off of X, you see how these two used X. But now we don't need to use X. Actually, we just need to capture index. Actually, these values don't even change. I don't know why I'm capturing by reference for this. It's a fixed value, so... Uh-oh. Really doesn't like this? Oh, because I put it in the wrong one. Yeah, this is where... I'll tell you, it really gets pretty diabolical with doing this type of stuff. Okay, next instruction. Oh, you know what we didn't do? And we're getting there. We're almost done with the virtual machine. This one's so easy to do. Store. Well, a store instruction is going to do what? It's just changing a data value. So one thing you could do is you could just do a static assert here. We'll write this in a second. So we could assert that it is a data instruction. Uh-oh, it doesn't like that. what's the arguments here? Anyways, we'll do some kind of static assertion, and we'll just set instructions. Again, it's going to be very similar to load, right? So, but we need to set element. Wait a second. Okay. So we need to take the store instruction, and we need to take the data. And this time it's going to be what a store VM instruction. So we take data, but data is a lambda now. We said it's going to be a lambda. So we evaluate that lambda. Then we know that, no, we take address, sorry. We need to know what address we're modifying. Yeah, okay. And then we're going to assign that finally. And then we're going to, of course, still increment the instruction pointer, and we're going to break. Those are given. Everywhere is going to have this, except for call and jump type instructions, everything instruction pointer plus plus. So now I can take data and evaluate that lambda as well. Uh-oh. It's called address, right? So, okay. So does this make sense? Apparently not, because I'm missing a parenthesis. Uh-huh. No. Oh, yeah. Okay. So where I'm missing it is here. Then we need an extra star to... yeah, but we need... Actually, we don't need an extra star, because this is a pointer to data. This is a pointer to a data VM instruction, man. I'll tell you, this is just a... we're going to, of course, put an enter there. This is just a nasty line right here. So we'll break it up a little bit. Start cleaning up this code while we write it. Yeah, if the stuff's going off the line, we're going to format it better. Don't particularly like code that goes off the line too much. All right, so what we've got now is a store instruction, and as I said, we're going to need another instruction right now, and we're going to add it. It's going to be called pop. Everybody knows probably where this is going. We're starting to deal with control flow and stack. Remember, that's all we're going to model here. We've tried to keep everything else hidden behind either kind of this register, data, load, store concept. We try to keep all of the data transfer and arithmetic hidden behind that, because the hard part is the control flow and the stack specifically. Because we want to go to a self-modifying algorithm here. That's where we are going to struggle. And now pop is going to be very easy because it takes no arguments. That is going to be a VM instruct. That's easy too. We can actually add a constructor while we're at it. Better add a constructor. So this is a 0 argument instruction here. Well, but it has an opcode, of course. And we can just say opcode equals opcode, and we're done. And now we can easily, oh, that's somehow, yeah, except we'll need a default, well, or we could call the base constructor. Yeah, should we do it like that? Will that work? Yeah, it will. Oh no, it won't. What's the trick with this? I guess we can use this, yeah. Okay, so we'll just use the base constructor. Again, these are all like silly little C++ design decisions. There's no real right or wrong on this stuff. Or I can make a default constructor that does nothing. I like this because again, it starts making the lines long though. So, okay, so we've got our pop capability here. Pop is very easy. We can also write push while we're at it if we want, but we might as well wait till we get to it. So pop is just going to pop the stack, and I guess it can set it to the register to the top of the stack. So we could say s reg0 equals s.top, s.pop, instruction pointer plus plus break. That one is really short, actually. So too easy, right? So okay, so we've got our pop instruction. So we're going to put a pop right here. And this is going to return VM instruct pop. Okay, done. Next one. On to the next instruction of our blueprint. We're starting to fly here, actually. If you can see, we're going to get now the job done pretty quick. Now we're going to have a bunch of self-modifying code. Because what we need to do is we need to start setting up an actual control flow graph in the midst of having this stack that's kind of being shifted around to model the fact that there's a double stack implied kind of in the original tarjan algorithm. But we're just going to use a single stack, and so it's going to kind of get messy here. But this is what we need to do. We need, that didn't work, by the way. Why didn't it like this? What am I returning wrong here? Oh yeah, what am I doing? I forgot. This is going to be annoying. Okay. Forgot to put the int x there. Okay. I'll always remember to put an int x. Now we're going to start using self-modifying code. So what's that going to be? Well, we're going to call this a mod instruction, which actually is going to take an address and an instruction. So this starts to get more complicated. Maybe start with the store instruction. It's not like a store instruction in that we're actually going to change not a data instruction, but we're going to change some argument of an instruction, basically, like a jump instruction or just swap out an instruction. We could do, this is a very powerful instruction in the virtual machine. And as I say, it takes only 2 arguments. It's going to still take an address, but now instead of like data that it wants to store, it's going to take a function which returns a VM function, a VM instruct. Yeah. It's basically, yes, that diabolical here. But it will work. Does it take any arguments? No, it doesn't take any arguments. It's just gonna, all it's gonna need to do is this. Okay, so that's it. It's just a slightly different type for the data part here. And of course, we're going to need to actually write this here. So we've got a modify instruction. And the modify instruction also, it's very easy to write. The way we're going to do this one is very similar to the store instruction. It's going to be slightly different because we're going to set the whole instruction rather. Again, if we wanted to make it argument level, we could actually make store and modify instruction the same instruction if we want. There really kind of some details here that are kind of unimportant, whether we're changing, you know what I mean? This is more general than store. Yeah, I mean, again, when it comes to assembly language, we'll see the real differences here. For now, it's like not a particularly important difference. So we can just say, uh, actually, we'll just take this, I mean, we might as well start here anyways. So we'll just take this one and we will say that, the address uh, will actually equal the data now. Uh-oh, it doesn't like this. Yeah, of course it doesn't, because I'm casting it to something. We don't need, it's a VM instruction pointer. Already. So actually we don't need much here. Still doesn't like it. Size T. Oh, because this is not casted right. Okay, that's all it is. Nothing more complicated than just simply writing at that address whatever the data value was. And okay, I'm getting my coffee. 1 second. Then we're gonna go and we're gonna finish this. Finish the whole job. But not without a coffee. All right, so let's finish this job off here. Mod inst, we've got our modifying instruction. Now we're gonna actually start emitting that self-modifying code. We're gonna actually emit a bunch of it. So the first one, a lot of this is like previewing type code because we're gonna need to actually write the code. Why is this giving? Okay. We're going to need to write some of it. But basically what we're going to do now is use like this make node address. And we're going to say there's going to be a return location. The problem is we need something on the stack sometimes and not on the stack at other times. So what we're going to do is we're going to, as you see, pop the stack. That means we've already taken the node, the caller address of the node off the stack. So we're going to need to use it and put it somewhere. So clearly, this is going to, actually the address comes second here. Okay, so data comes first. Well, the data is going to be simple. It's register 0. So, oh, wow. Return reg 0, right? So, okay, that's our data. So we're taking what we just popped off the stack, the return address. We need the return address, but we're going to say maybe we're jumping to that address because we've already popped it, right? So, and sometimes we're not going to pop it. We're going to try to be clever about how we construct this. And that's the whole point. So the stack is going to keep track of components, but it also has your return address, but the stack may grow and then it won't have your return address, but we'll just let the stack be bigger than when it entered your function, because we won't pop nodes off until they find their strongly connected component. As simple as that. But at the same time, we're using it for control flow. We're using it for components. But that's fine because we can pop it off right here. Sometimes we're not going to pop it off. And we're going to do more self-modifying code to peak and not pop. And that's another instruction. We could write the last 3 instructions. They're very easy. So the complicated part, the instructions we're writing are so easy. The complicated part is actually writing this self-modifying code. This takes some real thinking and is not so trivial, right? So, okay, so this, some kind of return instruction, some kind of retloc that we're going to put later. So we're going to have our return location, and we're just going to add it to the blueprint. Oh. We're going to use the blueprint size to, oh gosh, we're getting some real errors here. Okay, so as soon as we add a label, we need to add, gosh, the code is getting complicated, and we're just getting started here. Okay, so we got that one. Okay, now we're going to need more. Gosh. Oh, yeah, I totally screwed that up, didn't I? It's supposed to be a jump instruction. Oh, gosh. Okay, so we want this to be a VM instruct. Again, this needs to return a VM instruct. I don't know. Now, it's going to be a jump instruct. We already have jump defined. That's an adder VM instruct. And we can just put our jump opcode, and we can put, reg0 here. And should that be good enough? Well, I got... do I have a problem here? Well, here's another problem, okay? The problem is register 0 when it modifies the instruction, and we're really getting deep into this right now. When it modifies the instruction, register 0 is going to be inserted here. But this instruction isn't executing. We're only modifying that instruction to be executed later. So we're going to want to put some kind of get value reg0 in here. Now that wait a second. No. Actually, no, because we have the register 0 value. I don't think it's going to change. Oh no, but the jump instruction takes a lambda. Sorry, that's what the problem is. The jump instruction takes a lambda. So this has to be a lambda here. Okay, we can just put it. Yeah, okay. I'm like overthinking that we need to put a get value. We can just use a lambda. That's okay. Another capture of reg0 here. That, I mean, I'll just tell you, that is complicated right there. Because that means that, as I say, we actually have to return an instruction, but that instruction has an argument which we've defined as returning another lambda, so we can do it on the fly without having to worry about addresses. It will work, though. As messy as that is, it will actually work. So we've defined our first self-modifying instruction, and we're on to the next one. So we're going to push the next instruction onto the stack. This one's going to deal with this kind of idea that everything has to be on the stack. So at some point in the algorithm, we're going to have to decide, did we get on the stack or not? Because if our return address is not on the stack already, like if there were no successors. What if there's no successors in the graph? In the graph, it's a dead end. If you hit a dead end, we still need to push the address on the stack so that we can pop it off in finding the component. We need to know when the component is done being enumerated. Now, it may not be there's going to always be different optimizations and ways we could do this. So we could always use the length of the stack and stuff, but we're going to use this model where we're going to take someplace and just check, did we actually get on the stack while we were calling our neighbor nodes or not? And of course, these are successor neighbors. We're a directed graph. We're not an undirected graph. And so what we can do is we're going to yet again add another instruction. Again, we're almost done with instructions here. We're going to add a conditional jump. And what we're going to do is, since conditional jump and jump could actually be like the same thing, since conditional jump, if always true or always false, is a jump or a no op instruction. But what we're going to do here is make this a relative jump. We don't have to. We could. There's flexibility always, but again, relative jumps are pretty useful because we can actually not have to compute things later. We can compute them right then and there, perhaps, or since we're doing a delta between two addresses. So we're going to make a relative jump. This is going to be easy to implement, like all the others. Actually, as I said, they're all easy. Probably mod instruction store are the most complicated to actually implement. Now, this one can actually be a data instruction. So I mean, it can be as simple as Well, actually, no, it's going to need a lambda, a bool lambda. It'll have to be special. No, it has to be special. We need that bool lambda. So what we can do is we can actually write this first. Why not? Just cast it to like we'll just call it JC, jump conditional virtual machine instruction. Because really, what else would take a boolean and return a lambda? It's a good enough name for it. Oh, it does. Of course, it doesn't know about it yet. So, but what we'll do is we'll take the condition. We'll call it condition. We'll evaluate it, and if it's true, then the instruction pointer plus equals the next thing, the offset. We'll just call it an offset for now. Else instruction pointer plus plus. Don't forget that one, right? You always want to increment the instruction pointer on a conditional jump, even if you don't jump. So I mean, this is the that's it. I think we're done. We just need to define that now. We need yet another instruction in this virtual machine model. Okay, so this won't be stored. This will be jump conditional, and jump conditional is going to take a lambda which returns a bool called condition, and it'll take us one that returns a size t, but we'll call it offset, not address, because why not? It's a bit more descriptive. And there we go. Uh-oh. Forgot about this. Always forget to rename the constructor, but it doesn't matter. There we are. So now we've got a conditional jump in the mix. Except we're still getting some trouble here. Did I forget? I must have forgotten a parenthesis. No? I must have forgotten a parenthesis. Yeah. No, this looks good. Yeah, I did. No, still looks good. Okay, well, we'll figure it out in a second. And did I forget to? I added it. Okay, well, we'll see what happens. Actually, we should be able to just keep compiling and just check that. Uh-oh, language feature problem. I never liked that. Oh, because offset is I forgot to call it. It's a function. Yeah, remember this is going to be a lambda. Oh, is it going to be a lambda? No, let's not make it a lambda. Okay, what am I doing here? This is not a lambda. Let's just make it an offset. We don't actually need a lambda necessarily for these offsets, I think. Or do we? No. No, it's already in a lambda, and these are relative offsets. So if all the nodes have the same relative offsets, we can actually not use a lambda here. And we can actually just use a size t for our offset. Actually quite convenient, so... Again, because we've already got so many different lambdas going on here, this doesn't depend on x. It depends on the labels, and the labels will already have been part of the blueprint. So because we don't have that dependency, we can just do this, and I think we're compiling. Yeah. Oh man, we're getting some warnings here, which we're gonna just fix really quick. Uh-oh, size t to int. Oh yeah, make node address is should be taking offset as a size t. Okay. Uh-oh. Yeah, I forgot about that static assert, didn't I? I don't have to use a static assert. I guess... Oh, I somehow screwed that up. Because I didn't put it here, too. Okay, now it should get down to the... Yeah, okay. So, as far as that static assert goes, that's easy enough to fix. It just needs a message, I see. And we could also, instead of throw, I think that's probably better. False, invalid opcode. Oh, wait, I don't want a static assertion. Yeah, I'm in the wrong mode right here. I forgot now the... Oh, there should be, yeah, assert. What library is it in? Assert is in... you need to have ndebug turned on? Okay. So we'll just assert false there. And here on the data instruction, this is going to be extremely useful or on store, that we actually check we're storing to a data instruction. So the way we can just do this, oops. First we have to check the address. So we can actually just save that. So adder. And then we can just check the opcode here. And it just has to look like that. Something like that should do the job. Now, so we need ndebug, and we need to include cassert. Yeah. Resolve all the details. Uh-oh, skipped by case label. Yeah, it's true, it is, but do we care? Well, we do, because we need to put a scope for it if we want to do it like this. It needs a scope. Hey, we can just do this. It's the simplest thing to do is to just scope it. Okay, so we scoped it, and we're getting too many arguments here. Yeah, I guess we're just supposed to assert a... yeah, static asserts one thing, but we can't... Obviously, this is a runtime assertion. We don't want a static assertion. This is just wrong instinct for some reason, but it doesn't matter. That was the right thing to do. So now we're ready to put in our conditional jump, self-modifying code. So now we're going to get really into it. This is where things start to get kind of interesting here, because there's not much left to go, actually. Surprisingly enough, in terms of the opcodes, we're almost done. We need to add about, I don't know how many instructions. It's 16, 17, 18. Oh, okay, maybe about 28 instructions. Now, maybe it won't be that easy, but they're all easy because it's just going to be like writing simple code like this the rest of the way through. We're going to just add all of the different self-modifying instructions, and we're going to be done with this. So let's do the next one. We're going to do something to deal with the fact that we need to know that the node got on the stack. So we're going to call this, we're going to make another location on stack loc. And here we're going to return a VM instruction. And actually it's going to be a so we did pop, we did the first modify instruction. So mod inst VM instruction. And what it's going to take is mod inst. Actually, well, passing the opcode isn't needed in these, cases where they already have a fixed opcode, but it doesn't matter. I mean, it's okay for now. These are like little C++ things still. And we need a lambda for the VM instruction that it's going to return, which is going to be another another lambda within a lambda, right? So you just kind of have to sometimes get used to writing tricky code like this. And we'll just kind of neaten it up as best we can. So this is going to return a JC VM instruction. Conditional jump is going to do a lambda function. Now, yeah, okay. Yeah, this also needs to be a lambda, remember, so. And what it can be is a function which is going to change. Basically, the way that you know if you're on the stack or not is if the stack changed. How do you know if the stack changed? Well, just check the stack pointer. But what is the stack pointer? Well, it's just the size of the stack. So all we have to do is have the, well, we're going to probably want to define the stack ahead with the register as well, because we're going to reference the stack here, mainly because we need a stack pointer, but instead of even defining one, we'll just take the length of it as being our stack pointer. It'll be sufficient for this. So what we can do is actually make a condition here saying, well, is the length of the stack now the same as it was before? So we can just say, now you're going to look at that and say, well, that doesn't seem to have a whole lot of meaning, right? And also we're going to need like an offset, right? What is this instruction taking? An offset. So we need an offset, and that offset is going to be the check the strongly connected component location. Again, we're going to see this very shortly in the on stack location. So where are these going to be? Well, they're going to be in the future. Again, because there's no good programming language for self-modifying code, which is something that should change. And hopefully an example like this starts to help that. Because this could be written in such an easier way. The only reason this is so difficult, it's maybe even easier in assembly language. Some people would say this is easier in assembly language. What are you doing? You're, what I mean, doing this complicated virtualization scheme. But remember, in assembly language, we're still going to have to make lots of offset computations. It's going to be mostly just applying the blueprint is going to be the hard part. So to see this modeled this way is really, really quite productive, actually. So, yeah. So there's a problem with this, though. S size equals S size. What we want is when this instruction, this JCVM instruction, is returned, we actually want the size to be captured here. And here too, oh yeah, that's why we needed it here. Yeah, this won't work. This won't work. So how can we capture the size here? Well, first off, we can make it a variable x, right? So now we capture s, and we pass a variable size t x. So if we're checking if it's on the stack, right? So if it's on the stack, it'll mean they're not, actually that'll mean they're not equal. So if it's not equal anymore, then it is on the stack. And the way we can actually do this, I mean, the problem is this would also need to be a lambda here. So, again, we could actually write another function to do this, but we could also do it something like this. But the problem is you're going to say, well, this doesn't return a lambda. And that's absolutely right. That is a big problem. And these needs to be declared first too. So we start declaring all these variables. Again, by the time these lambdas are called, these are all going to have their relative offsets. So there's no problem with that. Oh, we can't call it with x, can we? Oh, no, we can, but it's this x. That's integer x. It's not what we want. We want s dot size. And we want s to be trickled in here. So we put s in here. And of course, we want check scc loc. We want on stack loc. I think that is... Oh yeah, these actually, what am I doing here? These aren't on here either. So I think the design is starting to come about. Okay. Oh man. Still something here. Oh, this is a constructor. Why do I have a brace here? Codes bool unsigned long. Okay, and that is the problem. I need to return a lambda here. So again, this looks pretty nasty because the problem is we actually need to return a lambda, but we need to use a lambda to get the size captured here. So we're actually saying I need to capture the size while I execute this instruction, but I'm modifying the condition that's going to execute later. Again, and it might seem more abstract and more complicated than what's going to occur in assembly language. But again, if you can't do this, it's not really a good assembly language is not a good prototype. This is probably a better prototype. Again, there maybe even simplifying this or finding maybe a better even a better language to do this, like rather than a bunch of C code that's it's quite almost diabolically complicated, right? But it should be sufficient. So we need to capture x now. Okay, so we need to capture s as well. This is a heck of a lot of capturing going on here. All right. That's probably the most complicated instruction we'll write. I don't think we'll get one any worse than that. That's about as complicated as it gets. Okay, we need to return though. Now mod instruct is not happy about this either. Why? Oh, because no, I don't see it right now. Oh, because mod instruct takes an address. Did we put an address in here somewhere? Oh yeah. So it's going to be on stack loc, of course, because that's the displacement here on stack loc. Obviously, will end up being the address that we're going to modify. So I failed to provide one argument here. Tell me that worked. Now I have to count the parentheses here because this is just tricky stuff. Okay, I think we've got this now. Yeah, man, I'll tell you, that's a rough line of code right there. But it doesn't get much worse than there, because there we're changing like the condition for something where, you know what I mean? We're just being clever. I don't know if this can be done any more cleverly than I'm doing it right now. As I say, there's actually probably 1,000 different ways to do this. I mean, and it's very difficult to choose what I would say the one that has the least Kolmogorov complexity. The one which is maximally compressed, it's probably the best solution. Of course, the one that minimizes the amount of instructions in the part that goes through the edges, because edges are expensive on a graph algorithm. You want to do most of the work in node processing, not edge processing. Edge O of m, which is maximum n squared. So we want to cut the n squared stuff out. So ideally you do more work in the O of n part. And so when we get to this critical section, which is coming very shortly, that's going to be the hard stuff. So now we're on the next blueprint instruction. It's going to be yet another modification instruction, the same exact code, except this time we're going to change this pop that we've put here. We put a pop up here. This pop will change to a peak. But when it's going to change to a peak, exactly the same code. The nice thing about this is we don't have to change anything. We've got the code written. We just need to change on stack loc to what I'm taking out of my Python code. It's going to be, instead of on stack loc, it's going to be top operation stack loc. And you're just going to have to bear with me until we get to define these different labels, which is coming soon, as fast as we can. Yeah, we could have worked backwards. I'm almost wondering if it would have been smarter to work backwards. I mean, it took me a while to get this working in Python. This is really non-trivial code. And we're going to have another call loc. So yeah, maybe it would have been nice to see this develop the first time around, but there's a lot of times where you get quite stuck. And so yes, having it in Python, just translating it to C++, it is a little easier, but I'm going to keep explaining like some of the logic or the rationale for stuff as we go here. So, and it honestly gets easier as we go along. This is like of the most complicated self-modifying instructions where we're dealing with some of these types of instructions. No, I don't know why call loc is below stack loc. It should be here. So this is kind of the flow. Now we're going to go through the edges. And so what we're doing is we're just setting up certain parts of Tarjan's algorithm. So far, we've basically set up the returning and the stack. And that's kind of the hard part here. A lot of this stuff isn't that hard, but we have to be able to go through this loop. So we've set up that. Or we're about to set it up. We've set up the returning, and we've set up something about, you know, 2 places where it's going to decide if strong connect got called and added it to the stack or not. And so in this case, we don't really have a strong connect. I mean, this node function is what it is. And so that is effectively the whole thing is strong connect. But it's a slightly different model because of the way we use the stack here. And we don't even have an on stack variable. We simply won't need it. So there's top stack loc, and we're going to call loc is going to be what we're subtracting from it. So not check SCC. So call loc, and that means we're jumping maybe 1 instruction forward because call loc comes after this one. Just like in the other, there was also this displacement. We need to define it up here. Oh no, we did define it. So why is it complaining about this? Because I didn't put it here. Okay. So we've got that done. We're on to the next instruction. The next instruction is going to be, we're going to actually modify code we've already written. We're not modifying code that we haven't written yet. So that's a good thing, right? So here we go. We're going to modify to have a return instruction. So you're only allowed to call a node once, right? And that's, you know, from Tarjan. Obviously, when it visits something, it can never visit it again. So when you visit your own node, you're going to put a return instruction right here. So this is going to be a return instruction. So that's easy enough. Actually, we don't have a label for it, but we can just say something like node address loc +1. So actually, why am I even capturing anything? Do we need to? We're going to use node address loc plus. Yeah, we will need. We don't need to capture anything, I suppose, but we will need a mod inst. Yet another mod inst here. So return mod inst vm instruct. So now we're not modifying what potentially could be the argument, like the jump condition. Which, of course, in assembly language, it won't even be the jump instruction itself. It'll be like a compare instruction somewhere else that you'll modify. But this time, we're going to actually modify the whole instruction. So this would be like changing a move instruction to a return instruction in assembly language. So that's what we're going to modify here. And we need a lambda function, which is going to specify what instruction we're returning, and we're going to return a ret instruction. Now there we get to go. We get to immediately add another instruction that takes no arguments. And register 0 is what's returned, so you don't need to deal with that either. So actually we already have what we need. So we can actually just return vm instruct ret. And where are we going to put this? Wait a second. So there's a function. We are going to make node address. We're going to say this node address loc +1. That's what I was saying. So we can actually refer to node address loc +1 in this case. Although if we want the code to be totally modifiable in the future, like you might add an instruction between these two, then we shouldn't do that. We should actually add another label here. So this is questionable. We probably should add a label to this load instruction to say, hey, no, I want to modify that load instruction, not to load the index anymore, but just return. You're not allowed to call it more than once, and that's all there is to it. And let's capture this. And we need to capture the node address loc. Of course, that's 0 right now. But again, I've generalized the code so that you could even put some useless instructions before it, or you know what I mean. It's just nice to have things properly generalized. That's the bottom line. And of course, this is so diabolical that you'll never get it right on the first get-go. Oh, I didn't close things. Wait a second. I think. Okay, let's add the return instruction. Oh, we did already. We just didn't add the code for it. But this is very easy, so. And a return instruction, we can just do something like pop, right? So we're going to actually set the. Yeah, okay, so just do this. Instruction pointer is going to be s.top. S.top. Done. Break. Okay, and there's not many instructions left to add to the system now. I think we just need like a, well, we can add no op, that's nothing. Push and peek. And maybe some kind of generic data transfer functions. Yeah, I will probably need that as well, but that's about it. So there's the last remaining ones are going to be very simple. Okay, so we've done our 4 self-modifying instructions now. Now we're going to write some simpler code. First, we're going to write a data instruction. So now we're going into the loop. So we're going to first set a new label, counter loc. I can add it in here. We should try to add these in order. So counter location, this is going to be where we start our counter. So this is a very easy instruction, right? So what are we going to have here? A data instruction. So we can just return data VM instruct data. And what do we want here? Well, we want the number of successors. Again, we're going into the code right here where we enumerate all the successors. So we need a counter. I mean, I guess you could use iterators. I mean, there's always those different options, but we'll just use a counter here. So we'll set the counter to the length and we'll just subtract from it. Easy enough, right? I mean, we don't need to make it too complicated. We can just say successors sub x dot size. Set that in. And again, should we do -1? There's different arguments for and against everything, and then compare to -1 or compare to 0 and all these types of things. But what matters, since doing -1 could give -1, we'll give -1. I think we'll just leave it be like this. So this is finally our successors come into play, and they're going to come into play when we call to, we need to index it when we call the next node. So done, we've got our data instruction, which is got a lambda giving us a size. Now this is a fixed value. Of course, it never needs to change unless, of course, you were reinitializing from an old already built blueprint. You would need to go through and fix things that we've changed. Like this is a counter, it's going to change. So again, we're using self-modifying code, so we're going to change it when we go through the loop. So now we're going to define another, we're going to call it the loop edge location. Again, another label. These are all labels. And it's going to come after counterloc, so somehow we're building lots of variables here. Actually, low link loc. If we want to be really correct here, we can just say, the low link loc should go well before ret locus. So these ones should come first. All right, so the kind of different stages of this, and we can just make that clear. So now we've got the loop edge, and means that we load the data, but we are going to kind of be subtracting 1 from this counter, and we don't need to run that again, but we need to loop back. So we're putting a label for where it's going to loop back. Now we're going to check, finally, if it's on the stack or not. Or no, we're not. Right, we're going to check the counter is not 0, right? We are going to check if it's on the stack or not too. So we're going to do both. But the first thing we want to do is put a jump conditional instruction in here. This, of course, is going to be a JCVM instruct. Again, we're not doing so much indirection now because we've already satisfied some of this modifying instructions. So we're actually going to have less modifying instructions in the future, maybe like 3 more in the whole program. So it won't take that much more to get it working. And those were some of the hardest, as you can see. Those are pretty tricky instructions right there to model. And so now we're going to just have a conditional jumps. I mean, these, yeah, it may look like it'll look simpler in assembly, and probably in a certain regard it will, if you're good with assembly language. But for now, we're going to keep modeling this. And so we're going to say the lambda for the jump, it needs a lambda and an offset. So the condition. The offset, of course, we can already just write the offset. It's going to be, in this case, the on stack part, which we've already referenced. We're going to check if it's on the stack or not. So we'll use that on stack loc, and we're going to subtract the loop edge loc, our current location. Again, this is how you write a conditional jump, right? So the current location, which is being subtracted from the future location, and that's how we're going to write all the conditional jumps. Now, we might be a little bit off by 1 with the way assembly language works, because with the positive values, I think it already adds 1. I don't exactly remember. No, I think we're right. I think it's exactly like this. I don't think it adds 1 with positive values, because if you jump, oh no, it already adds the current instruction size, like adding 1. Yeah, because I think if you want to jump to an infinite loop, You have to jump back by 2 bytes if it's a 2-byte instruction. So maybe we're a little bit incongruent. In other words, we're off by 1 with the way assembly language works, but it's okay. I mean, this is a triviality. We could fix that by adding 1 and subtracting 1 in the virtual machine. Either way. So anyways, loop edge loc is going to need to be captured. On stack loc needs to be captured. And the condition here is just going to be return reg0. Since remember, the register is loaded when we have a data instruction. Load will load from an indirect address, but data also is like a load instruction, except it's direct addressing and not indirect addressing. So we can just say it's not equal to 0. And we'll probably want to capture that as well. And I'm just going to capture it by reference. Okay. So now we've presumably allowed things to start working here. No, we've messed up the. Yeah, it's going to be a somewhat of a nightmare to get all this in, but not too bad. We're getting there, you know. I mean, this is not the end of the world. What? Oh yeah, I forgot the X value. Okay, yeah, I'm gonna keep doing that. And next, we're gonna have a store instruction. So if it's not 0, we're gonna subtract 1. Done. I mean, you can see how writing self-modifying virtual machine is not trivial. It's taking a lot of time and effort in code. I mean, but nonetheless, it will work in the end. And it will be able to solve, 60 nodes and 99 edge or more. It'll be twice as many as the clauses. Actually, it'll be 120 nodes because X and not X, and more clauses because the edges are the number of clauses times 2, so 180 edges. And it'll be able to solve that in no time. Whereas if you wrote a silly algorithm using trying every brute force, it would take forever. You would never complete. Not even, maybe if you had a supercomputer, but beyond that, you're not going to complete that in this lifetime. 2 to the 60th, probably too slow even on a good processor. Okay, store instruction. The store instruction takes, how did we define it? Again, we have to kind of reference it. We find a data and an address. Okay, so the store instruction will take the data that's going to be stored and the address it's going to be stored at. Well, the address we're going to store is at the counter location, so we already know where that's going to be. So might as well just return that. And the data we're going to store is just the register 0 minus 1. Actually, wait, what am I doing here? This is not right. Make node address. Again, store takes an absolute address, not a relative address, because it would just be too annoying to use relative addresses for that. Again, we always have a choice, but we've decided conditional jumps, relative jumps, and everything else are going to be absolute addressing. When it comes to assembly language, this has become very important as well. So the store instruction is going to take another lambda. It's going to return reg 0 minus 1. That's the value we're going to store. Need to capture it. And we need X in here. Always forgetting to put X. We need to capture the counter loc. Let me do it first. What else do we need to capture? I don't call that a store VM. Instruct. I do. Oh, instruct, not struct. Okay. And we got it. Oh. No. Ha! And it still compiles. Okay, now we're only a few instructions away, finally. We're at least from getting this loop done, and then we're going to do the strongly connected components part. But actually, it's getting easier. Well, the only difficult instructions are the 3 modifying instructions coming up. Otherwise, it's pretty straightforward. So that we've done the store. Now we're going to do now we've gotten to top operations stack. So basically at this point, we're going to need another, but we already have what we want here. So we have it here. Here's our code, right? Here's our code. So this jump instruction, but now what we're going to do is instead of this complicated mess, we're just going to like put a dummy instruction. We just need any lambda in here. We don't really care. We just don't care. Just return true or something, right? I mean, this instruction's always going to be modified before it executes. So we can just say return true. Just make the C compiler happy because we have to put something there. So again, and now we can actually compute the offset. It doesn't matter. We could put, again, these are all going to be filled in later, but of course we need to do it the correct way. But the nice thing is, as I'm pointing out, is that we don't really need to do a whole lot here because we actually already have our code. And yeah, well, of course we need to. You know, almost we should just put 0 here. I'm not even sure it's... The thing is, in assembly language, we'll already have the offset pre-computed, and we won't change the whole instruction. Here, I'm not allowing it to change like one argument, just the lambda. It's changing all arguments. Again, it's just modeling, so there's not really a right or wrong answer to how we do things. So that's why the job needs to get done one way or another. How you go about some of these details isn't particularly important, as long as you have satisfied them. Now, one of the things we're going to satisfy here is the stack is going to be empty when it's over. So we do not want a stack that is still got nodes on it when it gets to the end. So basically what we can do here is, as we're building this strategy, you see how we started here with a pop instruction. This pop instruction at the front of the virtual machine here, and if I can find it, it's like already, yeah, here it is. So we do this pop instruction, and we should write some pseudocode for this. I really feel like if we wrote some pseudocode with a special language, we'll make a special language for self-modifying code. So it's like writing C code that no compiler knows how to compile, but that we can just read in 5 minutes and be like, oh, yeah, I get that algorithm. That's a nice self-modifying code algorithm. Very nice. But you know what I mean? And you maybe don't need this blueprint in this generator in the same way, because if the C language had some extensions that let you modify your own code, and we'll write those out. We'll write out a pseudocode for like, let's make extensions and let's like modify our own code in C in a way that's totally readable, and say like, why isn't there a self-modifying language? Why not? There are languages that do it, but they're like, you know, weird brain twister. I forgot, one of them's called Marble or something. I don't remember, but they're like meant to mess with your mind. But why can't we use C and write self-modifying code with some kind of self-referencing system and some special instructions for modifying control flow. I think we could easily make a C language that has self-modifying instructions. Nobody will write the compiler. That's another problem though. Let's make the language, and writing the compiler for it, that can come later. Because how cool would it be if we could start changing functions around and doing all sorts of really cool things with self-modifying code, and there was a C compiler. Then I wouldn't have to do all this. I'm only doing this because there is no C compiler that can do that. So, okay, we're going to write the next instruction here. So we've gotten to through this jump instruction. So basically what it's doing here is it's now looking at the top of the stack, and it's saying basically not even the top of the stack really, we're calling it top op stack, but really actually this has nothing to do with the top operation anymore, because we can just say, did the stack size change? If the size changed, then it's on the stack. If the size didn't change, then I'm not on the stack. So it's a very clever way of looking at the top of the stack without looking at the top of the stack, by taking the stack pointer, which, as I've said, is equivalent here to the size of the stack. So you actually, because you don't want to look at the size of the stack, because, or not the size, the last element of the stack, because it could have been the thing that happened before your program started or something like that, because we already popped off. And so you don't want to go off -1 off the edge of the stack. What if the stack was empty? Yes, in real assembly language, we know it's never going to be empty, but because it's always called from the OS or wherever. But you don't want to start looking at data that you didn't put on the stack. And so we have to guarantee that we never go past data we put on the stack. Hence, we use the size of the stack. So, okay, we're doing the next instruction here, which is now going to be a modify instruction. So we've already got this fake JCM, jump of conditional modification instruction, because it's modified here. It's a fake. It's a placeholder. We could even put a no-op here. This could potentially be a no-op instruction. I don't know why I filled it in. Again, it doesn't have to be. It can be a no-op, but it will be filled in later. But again, in assembly language, it'll be a little different because the condition only changes, not the offset. That's why I kind of like to make a hybrid of certain concepts, even though maybe it would be cleaner to do things in a pure way one way or another. But I'm actually staging for assembly language. I'm not just doing this for doing this. I'm staging this so we can write assembler. And so now we've got this mod inst coming again. I know this is the most complicated instruction, but basically, if you can get through this one, you can get through anything, right? So we write the modifying instruction. So for now, what instruction are we going to put? Well, we're going to put a peak. That's easy for once. We got an easy one. Return a VM instruct. So just a single argument instruct, and it's going to be a peak. So we're going to make it so that it peaks instead of pops. Because why? Well, it's not on the stack yet, and it's about to call the successor node. So keep me on the stack. Don't pop me off, You're telling the node you're about to call, you're saying, actually, now if it's going to have a return instruction here, remember we put a return instruction right here. So because we're putting a return instruction, this peak will not matter at all. We're already returning right here because we've already processed the node. Now you're going to pop it right back off the stack. No problem. That node's already been processed. We don't want to push ourselves on the stack necessarily when we're processing a node that doesn't need to be processed. It's already been visited. But otherwise, even if this pop is changing to a peak in an already visited one, well, it's dead code effectively. So in dead code, we can change to a peak. So there we go. We got our peak instruction, which doesn't exist, by the way. So let's add it. No arguments. Peak is just going to put the value into the register. Very easy. So we're going to say peak 9. And what we're going to do is go down here. And we're going to go and we're going to add peak. First off, we always want to, now I hope I didn't miss this anywhere. We want to increase the instruction pointer in break, of course. If I forget that anywhere, things are going to kind of blow up on this. But what we can just do is say reg0 equals s.top. We don't pop anything. It's just like pop, except you don't pop, right? So, in fact, we'll even make it a one-liner just to let this code not grow too much. I think we've almost done every instruction now. You can see how simple making a virtual machine is. I mean, who's ever made a virtual machine before? If you haven't made a virtual machine, this is kind of a fun little task. I mean, peek, pop, conditional jump with relative offsets, jump with absolute offset, a little special dummy data instruction. We could put no op. That would be the easiest, right? Let's do it. Let's do no op. That one's fun. Inst pointer ++ break. Again, we could actually use C++ to put these, maybe somehow virtualize them into these instructions. Rather than just virtualizing the data, we could actually virtualize the code as well. But for this purpose, I don't really feel it's majorly necessary. So if we want a no-op instruction, it's there. I guess we're gonna have one later. I don't know. Oh no, we're not gonna have one. We don't need. Actually, we won't need no-op, but whatever. We're gonna need 2 more instructions. Just for a heads up, we'll need just some arbitrary data transfer stuff that we'll let happen in assembly language, because that's very easy. There's no stack stuff. There's no control flow. When there's no stack, no control flow, it's easy. It's very fixed, simple assembly language code. It's just data transfer instructions. And we're also going to want a one more push. I mean, obviously we have a pop instruction. We're probably going to have a push, and we can't avoid it. Call is not the only place a push needs to occur. Push and func, we'll deal with them when we get to them. Just define them for now. So that's it. And we don't even really need no-op. It's just too easy to implement. And it's very useful in assembly language. So probably something we may even come back when we're doing the assembly to like check with this model if some idea in assembly will actually work. That's partly why I have this model, is we can then check ideas after this works. So, so somehow we're going to return this instruction here. It's going to take a peek. It's changing a pop to a peek. So we can actually use our make node address function, and wherever this pop is, and where exactly is it? Do we have a way to locate this? We need to put a location. We need a label here. Well, I mean, we should put labels everywhere. I cheated one time already on +1 here, but I figure it doesn't matter what the second instruction is. We're always going to force a return value here, +1. So it's kind of, again, there's always like some little detail that comes into play that makes it so you violate your own rules because, well, this detail doesn't fit neatly in the always put a label idea. So we're going to call this the peek ret loc. And we just check the current blueprint size, and we can define it up here. Oh man, code is getting long here. So peek ret loc comes really early on. So now we can actually make the offset here, and we just say make node adder of x and peek ret loc. And peek ret loc, again, this is an absolute address, and we can just put it in there. Of course, we need to pass x, and I think we have the whole thing. Of course, it never happens as easy as I want it to. Aha. There's our lambda function. Well, our function that returns a lambda function. Our lambda function which returns a lambda function. So anybody who likes functional programming will kind of like the diabolical stuff I'm doing, or will appreciate it. I don't know if you'll like it, but you'll appreciate it because, you know, that's about on the level there. Okay, so next instruction, is going to be a call instruction, right? So we're set up ourselves for this call because we've changed the pop to a peak or not. If we are already on the stack, we left a pop there. We don't want to be on the stack twice. Every node is allowed on the stack only once, except maybe temporarily where we're going to pop it right back off. So here we go. Blueprint push back call. So now we know we're going to have a call instruction. Well, actually, we're going to call it adder because there are two that use the same argument, so we kind of generalize that a little. So the adder VM instruction is going to be a call, and our call is going to take, and it's going to take, well, we're going to need to get the successor of, yeah. But we're going to need to use the register. We're going to need to do a little bit of a computation here. We're going to need to use, well, should we? Yeah, I'm trying to think the level. The problem here is the level of indirection we're going to need to use. It looks like we need to use a lambda within a lambda. I mean, basically, we could say make node address. Because what are we going to call? We're going to make a node address with, you know, node adder loc. Okay, that's fine. We know it's going to be element 0, or the 0 offset here. This make node adder loc, which is currently 0. So node adder loc. Okay. Now we're going to make, but not x, right? So x won't cut it here. But what will is if we take, and we have to think about this here, but we need to get the successor of x. We know already we want the successor of x. We know we're going to want to take an element that's in register 0. So register 0, but -1, because store stored -1, but it didn't update it. And obviously, if we took the length, right here, we took the length size. We didn't subtract 1 yet, and so it's going to be off the end of the bound. So we'll have to still subtract 1, even though we did it here. If we made store also do a load, yes, but it's kind of questionable whether we should make store change reg0 to reg0 -1 or not. I mean, we could do this as a minus equals 1. There's tricks that could be done here. For now, I'm just going to leave it like this, where we just take reg0 -1. So that's going to be the successor node that we're going to jump to in this scenario. And, oh yeah, actually we screwed this up then. Because actually the one where we modified the peak address needs to use the same thing. But we're gonna write a function for this because this is a bit tricky right here. Because the problem is the value of reg0 needs to be delayed. Remember, this register 0 shouldn't be evaluated when the blueprint is being made. And the blueprint is going to already... Oh, no, actually... No, will this... No, because the blueprint already is... This is a lambda still. This is lambda. Now, I'm trying to think right now if this is going to be a problem or not. Of course, we could put an extra lambda. The question is it necessary? Because we don't want to do it if it's not necessary. Of course, we can still call make node address. And I think that's how we'll do it. And we'll just do it -1. And then we'll use node. Yeah, something like this. Right? This should be right. Why is it... Why are we getting trouble for it? Oh yeah, well I didn't define this. And we need the successors. Oh, yeah, so I just didn't capture my... And we need the register 0. So the other problem we have is the same thing here. This needs to be the successor of x of reg0 minus 1. Now the big question, and this is just such a great question. No, but I don't see a problem right now because again, the delay should be happening already. I feel like we could make a function to do this, but I don't think so because again, the register 0 shouldn't need to be captured here. Yeah, no, it can't be captured, in fact. The only thing needing to be captured is x, but as far as I see, we're fine with x. I don't see an issue with any of this, that's for sure. I think this is good to go. I think it's on to the next step. Okay, so we've called our function, it did some stuff, maybe there was strongly connected components, maybe it pushed pop stuff, who knows what it did, but relative to our own node, it either popped us off or it peaked, because it knew already that if it didn't return immediately, that it shouldn't pop it off. We want it to stay on the stack. So, okay, it stays on the stack. Now, we need to have this check low link loc. And again, we're doing standard stuff here. We're not doing anything that nobody's heard of before, because what we can do is this check low link loc, which is going to come after loop edge loc, if I want to keep these in order, is going to just do this. We just go to the tarjan algorithm, and you see there's going to be two check low link locs. But we're going to combine all this code. We are combining the call. We're always calling, even if it's not one of these three conditions, the third condition being no code, else nothing. But it's going to do a condition, possibly another condition, and then maybe it does a condition call, a condition assignment. And there's really no more minimal way to write this code. This is really about as compact as tarjan gets. But we're going to actually do things a little bit different. We're going to have about the same complexity. Again, this is the critical section right here, because we're going through successors, and in a graph, successors are the expensive thing to go through, of the edges, actually not the successor, but the edges. So we're going through edges here. This should be as few instructions as possible, and we could even claim that our algorithm is better than the non-self-modifying code, even though we have to generate the code, and it probably won't be faster unless you had a graph that was billions of edges or something where you could actually measure it. But nonetheless, theoretically speaking, if you can minimize the number of instructions in this critical edge area, you're better. And so we're doing a call and a condition no matter what. But what we can do is, instead of comparing low link index like this, low link, or checking if it's on the stack or anything, well, if it's not on the stack, we change to a peak. So if it's on the stack already, and it's in this node structure, basically, we're going to call it, and we're going to have the peak happen. And what we can do is we can return from the function with register 0 having the low link. If it was on the stack already, we already have the code set up. It returns index. And if it's not, if it's already happened and it's not on the stack, meaning it's part of another component, well, we'll modify the index to be the length, to be something too big, the number of nodes in the graph. So we can actually return from strong connect one of three values, either the index, the low link, or the size of the graph, which is always going to be bigger. And now we can just have one condition here. So we're going to combine this code. We're going to make it a little simpler. Yes, sometimes people use a min macro for that, but I don't know. The way I wrote it there seems very straightforward. So we kind of come back to this. We're at check low link. And now we're going to have another conditional jump. So obviously we're going to jump if it's not going to do it. But we need to check the low link too. So we write our usual blueprint style lambda function. And now we call check low link. Actually, I'm not sure if we need to write a. No, we're not going to do that. We're not going to call check low link. We've got our lambda good enough already, right? So the thing is, we might need two registers because we need to compare the current rate. But what we can do is like write a quick hack for this one. And so actually I would make a function check low link, but I think we can just get away with returning our conditional jump instruction. So it's going to have that. And then if we don't need to change the low link, we can just go to counter loc. And what's counter loc? It's the next, yeah. So what we can do is just jump conditionally, and we can go to the next node. Counter loc is where we start the next node, right up here. So basically, if we're not changing the low link, we're already on to the next node. Well, the next edge, effectively. I shouldn't say node. That's not correct. The next edge, which, of course, relative to this node, it's just another. The edges are all just other nodes, but we're going to the next edge here already, and we can just do that. We don't have to, and that's why we save this label so we can make a relative jump. So easy enough. We're just gonna, of course, do a subtraction here. And now what we can do is make this conditional jump instruction, and basically we can just use reg0 here. Reg0 is not, no, less than, right? Or, well, actually, we're going to want to jump if it's greater than or equal. So if it's greater than or equal, if it's less than, if we have a better index or a better low link, we want to assign it. But if, and we can do this like by actually using instructions. It's a little hacky to not use another register. In assembly language, I would say just use register 1. Why do we have to use only one register? Well, and it does lead to these awkward consequences where we should be doing like some kind of load instruction, right? So we should do load here into register 1, but instead we're just kind of doing this on the fly. And we can just say node address of x. Actually, we could say make. No, actually, we don't need to do make node adder because we don't need a lambda here. We can just actually take the node address here. And we can add low link loc to that node address because that's where we're storing the low link. Remember, we did that already up here at the top. We stored the low link right here. So the low link is already been updated to index. And again, you have to just look at Tarjan's algorithm if you really want to appreciate how we're going about turning this into a self-modifying code algorithm, which is actually a graph with nodes that just each kind of modify themselves in the correct way. So we've gotten this far, and this is this correct? No. Almost. I think, well, of course we're going to need to capture reg0. We're going to need to capture counter loc and check low link loc. And low link loc. You can see all these captures coming in here. And do we have anything else to put in here? Uh-oh. Doesn't like my function here. Yeah, okay, this actually is a bad comparison because this should be sub 1. Again, it's a data instruction. Again, we should be using load. It's basically the load code down here. It's the load code with, yeah, hacked into existence here. It's a bit hacked together. Oh, and we're unfortunately going to need to, yeah. Somehow that's going to probably satisfy things. Okay. Oh man, I thought we had it. No. This has got to be right by now. Oh, I somehow messed something up here. Yeah, of course I did. So we need to do the usual stuff. I mean, again, that's why we're doing the load instruction, and yeah, I didn't use an array for the arguments. So what I'm talking about here. I think we got it. Yeah, on to the next instruction. Okay, so we're about to finish the loop. That's the good news here. And actually, I think it's going to be even simpler now. Yeah. Now, basically, we're going to need to store the low-link loc. That's the easy thing. I mean, at this point, we're done with any sort of tricky conditional comparisons. Now it's a very easy instruction. Return store, did I call it? Yeah, store VM instruct. And we put a store opcode. And we are going to put, what value are we going to store? Lambda. Man, you see, I've gotten used to writing Python, and it really messes with me lately. There's reg0. So we're going to put reg0 in here. And I think we need one more. We need to put the address, and we know that's going to be make address x low link loc. So again, we already have got that location because we set it before to its own index. But then if it finds another low link, again, this is how the strongly connected components algorithm works. It looks simply to find, basically it's doing like a depth first spanning tree. And after you have a depth first spanning tree, you can kind of look at where there's back edges and such. And it can, based on those back edges, figure out which is the root of the strongly connected component. In other words, the one that was earliest in the depth first search to choose. And that basically will allow it to make sure that the index in low link will be the same only for the one that doesn't have its low link change. So if the low link changes, we don't have a component, and we're going to make that our next instruction here. Well, we would if this worked, but we just have to fix the captures. It's a mess of captures here. I didn't think about this before I started implementing it in C. Again, I did it in Python, and in Python, most people would have a tricky time getting this done. I can show the Python code. In fact, we should take a look at it. It is really interesting, and basically, you have to use. Sometimes I had to use like a list of registers or stuff like this, because if it's not in a list in Python, you're not an immutable data type. But with C++, we've got like a little bit more expressibility with lambdas. Lambdas can have arbitrary code, not just one line of code. Plus, we have some we have ways of capturing local variables in a way that you don't have over in Python. So I mean, this. Well, there may be ways of using non-local and global, but with lambdas involved and stuff, it's pretty messy. So yeah, but it is very interesting trying to do something which uses like code that's kind of tricky. Like this, very tricky code, but doing it in Python, so can be done though. So we're done with the loop now, I think. So. Oh no, we got one more instruction, don't we? So now, I just said it, right? I just said the instruction we're going to want to do now is that if we change low link, we know there's never going to be a component. It's something, Tarjan's algorithm doesn't work that way. It does a comparison later and says, is my index the same as my low link? Well, by definition here, if it was greater than or equal, we went back, but by definition, if something was less and we change low link, index never changes. By definition, they're never going to be equal ever again. So it's as simple as saying, okay, we're going to want a mod inst VM instruct, and we're going to put in here mod inst, another lambda, and this lambda is going to contain the conditional jump instruction. And this time we're actually going to use a conditional jump, but we're just going to hard code true. So that makes it very easy. So this lambda returns a VM instruct, jump condition, and it's going to be the same return true silliness right here. Okay, so I mean, nothing to worry about there. Very straightforward. Now, what is it going to do? Well, it's going to use two locations as usual. We have to make a relative offset. We're going to use the low link location, because low link location is going to like practically be returning from the node's function, and check SCC loc, which is going to be where it's checking if there's an SCC. Because remember, we're modifying another instruction, so we're not relative to the instruction right now. This is a modifying instruction, but it's modifying a jump instruction somewhere else. So these arguments are relative to that instruction itself, and we'll write that one later. We haven't written it yet, so maybe a little hard to appreciate a little bit of this, but nonetheless, that is what we're returning from here. And then we need to say where we're modifying it, and that is an absolute address here. So we can just say make node address. It's modifying its own code, and it'd be the check SCC loc, right? I mean, this is very similar to code we already wrote up here. Very, very similar to this type of code, where it's just like making some decisions, and it's going to actually do something based on that. So, okay. Let's do the last instruction here so we can get on to the kind of last part where we start making the component. And again, you can kind of see the trickiness of this diabolical type code. Okay, the next part of the task, low link loc, check SCC loc. Yeah, we need the usual stuff. We're gonna need this make node address. X. Okay, and we want to like make the code more readable, if we can, right? I mean, this is not necessarily designed to be easy to read code. It's again the problem is we don't have a self-modifying code language that has truly readable, expressible code. It just seems like nobody ever wanted to make one. I would like to make one because it would be incredibly useful, in my opinion. So, because again, look at all the work I'm going through to get this done. It's just, but it's useful if you ever want to try to make such a language. You have to struggle through this aspect of things to get there. So, okay, correcting all these parentheses and braces. Okay, I mean, are we still compiling? Of course, this isn't going to work if we don't complete the virtual machine code. So we're almost done with the blueprint. We're getting really down to the last 10 instructions, and they're all very simple, 15 instructions, I guess. But I see only like 2 of them that are even complicated. Now it's going to get really simple. Some of them are just like placeholder instructions and other stuff. And that's really nice for us, so let's go. Blueprint, push back, and we're going to put now an instruction which is going to jump unconditionally. Again, we're kind of making jump instructions here, and in assembly language you have a choice between relative or not relative, but why do we need to, we can just make a lambda true. I mean, again, this is partly just prototyping. So when we do assembly language, we of course will do something different than this. We're not going to use jump if conditional with true. It's just pointless. But, well, I mean, actually there could be contexts where it's not, because we're doing self-modifying code. But in this case, we're going to just jump back. So easy instruction. Return jcvm instruct, jc, return true. Again, a false would be like a no operation instruction, but we already chose to just add a no op for the fun of it anyways. So, and where are we going to jump to? Well, we're jumping back up to the counter loc. So again, we want to go to the next node, and we haven't checked yet if it'll be zero, if the counter will be 0, but we let the check happen up there at the loop edge loc. Actually, if I said counter loc, that could be a it shouldn't be, yeah, it should be counter loc, because actually data loads the value and we need to load it into the register. Again, register 0 has the low link for, or the index or whatever the number of successors of in the graph, well, the number of nodes rather in the graph, if it called the function. So if it called one of its successors, we can't use the register. We need to reload it. So we go back up to counter loc. So we say counter loc minus next edge loc. And next edge loc, I think, where are we here? Next edge loc is going to be this instruction. Yeah, we needed to add it. Okay, and does this do it? And I think we're good to go on this one now too. We just need to add next edge loc up here, just so we have a basis label for our relative jump. So okay, so now we just jump back and say, okay, whether the low link changed or not, we're getting back up in the loop. So we have kind of like 2 back edges here, which is perfectly fine. I mean, we could have jumped forward, but why? I mean, there's nothing to do. Jump forward just to jump back, no point. So better to just put 2 back edges in. No harm on that. And we're still compiling. All right, so the next instruction that we're going to write is now another conditional jump instruction, because now we're out of the loop. Now this would be the next, this is going to be on stack loc, and this location was already specified here. So on stack loc is going to be the difference. No, wait. Where is it specified? It should, it should be specified on stack loc. Yeah, here, we jump to it from here. This is a different one. This is modifying the instruction there. No. Making sure everything is right here. Yeah, why is it using on stack loc here? Uh-oh. Okay, I think there's a mistake there. I see a mistake. Anyways, despite that, and it definitely looks like a mistake, I must have copied this. No, that definitely looks wrong. Obviously, this is deciding if it should modify to a peak. Yeah, we better fix that. That one's supposed to use call loc and top op stack loc. Uh-oh. It makes me nervous because I don't want to make any mistakes here, because this is very tricky code. But it feels like we copied this from somewhere. Yeah, from here. It's definitely not the same. Call loc and top op stack loc. Oh man, I just am realizing this is really not the type of bug you want in there, because of course if this doesn't work, debugging this is going to be a little bit tricky, to say the least. I mean, definitely, we do want this to work. So that's fine. Okay, so basically on stack loc is where we jump when reg 0 is, it becomes equal to 0. So So why is this not equal to 0 when it should be equal to 0? Yeah, the odds of making a mistake are kind of possible, but this should be equal to 0. Yeah, if it's equal to 0, that means there's no more nodes to go through or no more edges in the context. And at that point, we're going to go to this, Okay, call loc we can just move. We know call loc was over here. That's the call location. And when it returns, it'll be here at this check lonely loc. Okay, no problem then. I just forgot about the call loc because we didn't actually reference it. It's fine. So we're at onStackLoc now. Now onStackLoc is going to have basically a value already written into it. And now this is probably why I wanted to copy and paste something, but this onStackLoc, we write this jump instruction already. Let's get this instruction. We'll just fetch it because we know we're going to use it again. So what we can do is say, we know the instruction coming here. And we can just return it. But now, of course, we're going to just capture check SCCLoc and onStackLoc. But now this in here doesn't need to be so complicated, because inside of this code, I tell you, this is tough stuff right here, but we're going to get through it. It's going to be always true. So basically well, again, the idea is it's always going to fill this code in. Actually, we don't even need, again, this is all like a dummy instruction, and effectively we just don't need any of this. And so we can just return true or anything, false, it doesn't matter, or just put a no op instead of a Jace jump conditional instruction. None of it matters. Just getting the syntax right does matter. Now we can actually do something, because now we know if we're in the stack or not. So if it happened to have zero successor edges, or every successor was already part of a component or already analyzed, then we won't be on the stack. If we're not on the stack, we've already checked this instruction, which is true, really is checking if the stack length has changed, because we've already modified the code. So now if we are in fact on the stack, that's going to be a real interesting issue, but we're going to solve it very easily. Push. So what's push going to do? Well, push is going to take like a size t. We can just make it a data instruction. So we can just say data VM instruct. We don't need another class for this one. I think we will for func, but maybe the one last, maybe not. We'll see about it. It's going to, of course, have a lambda for that one, but push. And what are we going to push? Well, actually, this one's going to be a lambda, isn't it? Not what's data VM? We have to look. So we're going to need a lambda for this, because we're going to have to call make node address. We need to delay things. So yeah, let's just do address. I think that'll be sufficient. And we're going to push the call location +1, pretending it had called another node. So remember, the way a node can identify itself is by this call instruction +1, that return address being on the stack. So all we have to do now is say make node address. And we can say x, which somehow I need to put in here, and then we can just say call loc +1. In this case, call loc +1 is the best computation, because really when you call a function, you push the +1 instruction. I mean, we can look at the source for it down here. I mean, that's what call does. It pushes the instruction pointer +1. So, okay, so call loc +1. And Okay, so does this... Oh, no, that was misspelled. Make sure it's... wait, I got something wrong here. Okay, parenthesis. Does it work? Okay, now did we implement push? No, we didn't. So last one we did was no op, and we need to put no op, push, and func. Okay, so if we want to execute a function, we need some code for this. Right now it's a no op, push. Well, push is pretty easy, right? So with push, we're going to actually, again, we said it was an address instruction. So we can actually just say the address instruction's address, and it just pushes it onto the stack. So s dot push. And I think that's all it's going to do. Okay. Yeah. So that's push, which means we only have one instruction left to implement on the virtual machine. And actually we need to also tie up some loose ends here. So eventually we're going to have like some kind of solution, and we can kind of just say if instruction pointer equals unsat, then we could effectively return an empty vector, or we could even just the other option is just to clear the vector. We could just say solv.clear. I mean, these things don't matter too much, so we clear the vector. And actually, we're going to want to sort this. Do we make this a vector? Again, we're going to want to use the same code we used here. So what we used over in TwoSat was this type of thing. So actually, we want this solution v. Actually, we want it to be an unordered set at first, because we're going to be doing some checks for if something's in there or not, and you don't want a list for that, or you don't want a sequential structure. You want a hash table, so you can have fast O of 1 access. So the way we'll do that is just correcting this. We haven't used it yet, so we're going to get to this one. So the solution. And then we can just readapt this code. Actually, this is all we're going to use here. In fact, we'll just use the same code. There was no reason to even write that last if statement. And then we've actually tied up the loose end, basically. The only thing is we should say so if the instruction pointer got to this unsat loc that we haven't jumped to yet, but otherwise we're going to sort it and return it. And we're done. And that's the end of the function. There's nothing left to do. The only thing is to write this function. I'm trying to see how long until we're going to have to write it. I don't think it's particularly long time. All it's going to do is call the function at element 1. I mean, it's the same thing. We could just use this address data structure for this, and we could just be done with it like that. Just call a function which is the first argument, and that's it, and go to the next instruction. So, and this may change some stuff, but we'll deal with that through lambdas. I mean, we're just going to use, so we're done. The virtual machine is implemented. That's the whole thing. We could even make the virtual machine print stuff now by using this function instruction. We could actually make a new print instruction that starts printing data out, so we can watch what's going on if we need to debug this. And it's almost sure that probably I'll make a mistake somewhere along the line. This isn't the easiest thing to implement, as you can see. It's got that certain diabolical hardness to it, just because of the nature of self-modifying code. And but it won't be impossible to make it work. It will work with some work put into it. So we go to this check SCC loc, and again, this is another instruction we already dealt with before. We dealt with it here where we modified the instruction, so we can just copy it. So we've already made the code for this one. And the only difference is we're going to now, instead of here where we've changed the condition to true, this is like changing a no op to a jump. but instead we're just changing the conditional jump from true to false. It's the same as no up to jump. There's absolutely no difference, and it's a very easy instruction. It's a free one. I will take a free, easy instruction when doing this complicated code, that is for sure. You can't complain with easy. So the low link loc, as I said, is going to be near the returning from. So after we've dealt with the components and stuff, there will be the low link, which is just a data instruction storing the low link, because we're going to return it so that we can return the index here. Here we return the index, which is clever. This is very clever. We return the index, and here we're going to return the low link. But here we'll also return the size of how many nodes are in the graph, because we can do that after it's become part of a component, because it should never be called again. It should never affect any other low link anywhere. So we want to make sure that it's too big at that point. So these are the clever tricks we're using to accomplish this task here. Okay, well, we've got the what is this, the low link location here. We've already got the target, but we need to fill in the strongly connected component code. Now we've got a component. If this didn't change, it's a component. Even if there's only one node in the component, it's a component. Even if it only pushed itself to pop itself off now, I think we know what's coming very soon. Pop. In fact, that's going to be our next instruction, right? We're going to have another next node load because we need to make a loop here. So obviously we need to loop and pop all the, here's the Python coming into play again. Okay, so we take the size, there's our next node loop, and now we're going to just add a pop instruction. That one's easy. It doesn't have anything special going on there. Okay, we've got a pop instruction. And yeah, we should probably define our next node low. Actually, I think call loc was supposed to be here, something like that. Anyways, again, it's like I ran out of names, right? So I'm just putting every name I can come up with that sounds decent enough for all these labels, which we're calling location, loc. But again, you have to have a lot of labels. So okay, we popped the stack. We know there's a component, and it's going to end with the node, which is the root, our node, the current node. We'll know when it ends as well. So this is easy. Now we're going to modify another instruction, and this is interesting. This is the last difficult instruction. So anybody who's been bearing with this, and I know it's a little bit diabolical here, but this is the last tough instruction. It's another mod instruct, VM instruct, not an inster cut. Okay, so this one is going to now modify. So after it finishes all the strongly connected components, we're going to put them in reverse topological order, the nodes. It won't, forget the components. We're going to mark the components here and set a chain of jumps. And that chain of jumps we had here. We had it here. It jumps to sat already. So it's jumping to sat up at the top. It jumps to sat. But we're going to say, no. That's start topo plus 1 right here. Start topological plus 1. It's this jumping to sat. We're going to say, no. Start topo plus 1, jump to this node. And then we're going to change this start topo plus 1 to the next jump instruction. We're going to create like a nice chain of jumps just for fun. Actually, we could do this more efficiently without even doing this. But just to get practice at starting to see how to actually make a new control flow graph in topological order where the strongly connected components have actually been decomposed. They're already just reverse topological order sorted in, basically. including their own nodes of a component reverse topological sorted, which usually isn't, you know, particularly interesting because it doesn't matter what order you visit nodes in a single component in. But again, we're just kind of gonna start doing that. So okay, mod inst, and we're gonna actually change the jump instruction. So we're gonna use a jump instruction, and so we can just return. Jump is what type of instruction? Adder VM inst. Right? Jump. It's going to have some address. So what address are we going to go to? Well, it's going to be the register 0 values the return address, which is the call location plus 1. So what we can do is we can use a relative address. We know that if we take register 0, it's got the return address, which is actually where it made the call from. And we don't care if it was called from the very, very outside starting point of the Tarjan strongly connected component algorithm, this part up here, because we popped that off already. We don't count that. We have to wait for it to push its own address on, not those kind of calls that came from outside of the graph part. The actual parts representing the nodes of the graph, not these extra call instructions to make sure that we visit every node. So the visitation guarantee ones, we don't worry about that. What we do is we can say we want to subtract call loc plus 1. So obviously we're going to need to start capturing stuff a lot of times. And what are we going to change it to? Well, interestingly enough, we're going to change the Uh-oh, I messed something up here. Okay. So I need to put the actual instruction in here, and that's going to be the complicated thing. Also, this isn't complete yet because we need to put like another, what did I call it here? I called it node address set location. But we're going to need to add something to this. So if I take reg0 minus call loc, it gives me node adder loc. So I'm at 0. Node adder loc is the first part of the blueprint. So now I want to go to node adder set loc, which is going to be this place where we're actually going to construct the solution to our 2-sat problem. So, okay, we do something like that. Of course, we need a node setter loc, and it's going to be fairly towards the end. It's even going to be after the return location. Okay, so we've got that going for us here now. And now we're coming around to the fact that we want to... okay. Right, why? Okay, it doesn't like this because we didn't capture it. What we want to do, though, is say where we're setting it. And the truth is we want to actually need another register again. And instead of using another register, though, we're just going to say instructions of start topo. So start topo is an address already. Sub 1. Oh, no, not sub 1. I'm looking at my Python code now. Dot. Well, actually, we're going to need to cast this, aren't we? Because it's a data instruction. So we can just say data VM instruct. Again, it's just storing some data for us to pick off. So I think that's good. Uh-oh. Definitely is not sufficient. Well, we need to capture some stuff. Lots of captures here. Hmm. Oh, lots of captures. In fact, yeah, I put it in the wrong place. That was it. I mean, that's just, the code is getting that complicated that again, this is the last complicated instruction though, so I just have to, grind it. This is definitely grinding through a tough instruction here. So, just checking these lambdas here. No, it does need to capture it. I don't know what I'm saying here. It does need. Wait. Yeah. Actually, it looks good. I think this is strange. Ah, there. Just Visual Studio taking a long time? No. No. Something, I messed something up here. Okay, the mod instruction. Wait, the jump is supposed to take a lambda, right? So, in fact, that's really, you have to be careful because this register 0 needs to actually be set correctly here. Okay, I think we've got it. Yeah, this looks good. Oh, but wow. Wow. This actually, I mean, knew somewhere there was going to be, be differences in the capture arguments. Man, that is just a mess. Okay. Yes. Oh man, that was a painful one to write. I don't know why. Felt like the most painful ones, and there won't be any worse than that. So, the next couple are a little tricky, but not too bad. Not compared to that one, because now we're gonna just do some store instructions. Now we just need to store which is its root component, so we can check that it's not unsat, that there's not the x and minus x in the same component. So we're gonna do something about that right up front, and then we're going to have to store the index. We have to change the index of anything that's part of a component to be the length of the nodes in the graph, because we don't want it to ever change the low link for anything else. So we're kind of going to clean up all these little things here. So we've got three things to store. One is we need a new start topo pointer because it's changed. One is that we need a new index, so it shouldn't really use index anymore. It's supposed to be kind of obsolete, and we're going to need what's the other one? Actually, yeah, and the one we're going to do right now, which is namely that we want to change. Yeah, what we want to change is we want to change which component it's part of, because it won't know later. If we just create like a straight line of jumps, we aren't going to know which component you're a part of. So we won't be able to check the unsat case. So that's what we're going to do right now. We're going to add this first store instruction. Oh, what's the, yeah. Oh, so it takes a lambda. Yeah, okay. It takes a lambda and then a, takes two lambdas. So first is the data that it's going to store. And the data it's going to store here, actually, we don't need a lambda. We can just say make node address. So what it's going to store, it can just use any marker it wants, actually. It could use X. It really doesn't matter, does it? I suppose it doesn't matter. Anything based off of X. It could, it could be the call loc plus 1 of X. It could be making the node address like this of X and node adder loc, which is plus 0. So obviously that's the 0 spot. That's the start. And then, yeah, something like this. And where are we going to store that? Well, we're going to store it at the same place we were jumping to just a second ago. It's going to look exactly like that. So we can already say, okay, we're going to need all these captured. Okay, that probably has done the trick here. Uh-oh, no. Make node address. Okay, X needs to be in here. Okay, I think we got it. So that actually has done our first, first store instruction down. 2 to go. So we start making another lambda. We know we're going to be returning a store vm instruct. This time, the value we're going to store is going to be a little bit different. So this time we will use a lambda. And what we can do is use register 0 plus next topo loc. So eventually when it's in this jump chain, there's going to be a jump instruction, and that's next topo loc. Whereas node adder set loc is going to be a data instruction, so now, so we're actually storing at topo loc. So actually, we're not modifying the jump instruction. We're modifying what's pointing. We're going to modify something to point to the next jump instruction so that we can modify that. And the default will all of these be to jump to sat, just like the outer one jumps to sat by default. So again, we're trying to be kind of flexible. What if there was a value that wasn't needed in these types of situations? Well, actually, if there's a value not in any clause, we're not going to include it anyways. We just consider that not a variable, but nonetheless, we want to have this kind of stuff. Now, this is going to be the last instruction of the whole thing. So next topo loc is the end. It's going to be the jump instruction, and there won't be any more instructions. That'll be it. So we're almost there. Just define that one. So there's this minus call location plus 1. Again, we're doing everything relative to register 0, which was its stack location when it was making calls. And we even deliberately push that to make it consistent. So we can just use a relative address to deal with its own code situation. And then the thing we're going to store is going to be this, or that's the location. The location we're storing at, boom, there. Now just capturing. Ooh, this is getting long. And it still doesn't. Oh no, I think we got it. Nope, we definitely didn't get it. All right, it doesn't like one of the arguments here. Okay, and we know why. All right, so we've got a few instructions left. Here, let me tell you how many instructions are left. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 more, and most of them are, all of them are extremely simple. We're going to go fast for these ones. All of them. There's not a single one here that's difficult anymore. Fortunately, you know, by the time you get to the last 9, it's going to be easy. It's the stuff in the center that's always the hard stuff. You know, a little bit in the beginning and quite a bit at the end is usually easy, and it's the rest of that beginning center to in the whole middle part that's just quite tricky to implement. So here we go. We're going to now start playing with the blueprint a little bit more to add the last 9 instructions. The first one's going to be another store instruction. So there we go, store. And what are we going to store? We're going to still need some of these things, but we'll add them as we go here. Oh, no. Actually, what we're going to store, we just need x for. So x is going to give us what? We're going to store the length. No, we're going to store successors of x dot size. So that's what we're going to return here. So basically, we're just changing the index for this one. So the address will just be like make node address, but we can't use make node address. We have to use still our relative offset, and that's important. So we'll do something like return reg 0 plus, and we know node address loc. The first address of the function was that data. So the very beginning we did the data instruction for the index. We want to kill the index and make it some number greater so it'll never affect anything. It's off the stack and it's been processed. There's kind of like several states a node can be in. It can be on the stack. It can be off the stack and processed, or off the stack and not processed. And these are kind of like what we've cleverly kind of implemented in all of this code here. So, okay, now let's put some captures in, and I think we've got this one done, and we're down to 8 left. All right. Whew. 8 more functions and we're done. Okay, go to next node loc. Now we're going to go to the next node. We've obviously finished the loop here. We've changed the indexes. We played with the pointer to the next jump instruction. We've now changed the place that's storing some symbolic representative of which strongly connected component each one's in, so we can check if it's unsatisfied. Now, again, we could actually not do all this, and we could solve everything right here and now. It's true. You could short circuit and jump to unsat. There's a bunch of interesting things we could do right here and now. Although, yeah, I don't know. I kind of like the way we're going to end up doing this. So it's kind of a trade-off whether that's worth it or not. So go to next node loc. Obviously, the low link loc, we already have jumped to that up at the top. So this one's going to be like I believe it's going to be just a straight jump. So, okay. And actually, you can see almost every instruction now is going to have a label for it, because we don't have very many instructions left to put in here. So the... Okay. This is going to use a jump conditional. Okay. Well, since actually this is a post-check loop, I forgot. We don't check, we check in the beginning if it's a component, but if it is a component, this is going to be a post-check loop. So we will still need some kind of conditional jump that has a actual condition. So there is that aspect to things right now. Okay. So we're going to make a instruction here, and this is going to be, of course, a JC, a conditional jump, and that conditional jump is going to go to the next node loc that we defined a few instructions before. So next node loc right here. So we can just immediately say next node loc minus go to next. I mean, that's the whole point why we put the go to next node loc there. Just needed some label to call it. And then what we're going to do is we're going to use some kind of lambda function that's going to check, well, exactly what will it check? It can check that the register 0 is not the call loc +1 address for the current node. So the way we'll do that, and I do have to be careful here. I'm worried I'm making a couple mistakes that are going to really be annoying to fix, but we can fix it. It's always possible to put print statements and other stuff. If we need, obviously, it would be wonderful if this just works on the first try, but you don't always expect that to happen. That is not with code this tricky to program. But what we can do for this is put the lambda. So the condition is basically going to be the register 0 is not equal to the current node address. So node address of x plus call loc +1. So we know it knows its own address, basically. And if it's not equal to its own address has to be the first item on the stack. It's like the rule, because it either pushed itself because no nodes pushed anything on the stack, or it changed the pop instruction to a peak to make sure that the first time it would always make a peak and leave itself on the stack. So it's going to be on the stack one way or another, and it will be the last thing that comes off. And so hence we can just do it like this, And that's it. And then we just need to capture lots of stuff here, don't we? Like seriously, lots of stuff. Okay, I think we've got this instruction done. And fitting on the screen, fortunately. Yeah, we should capture X as well. Okay. Yeah. And that leads us to, I think we're at low link loc now. So now we're at low link loc. Yeah. And so we can just put a simple data instruction. Okay, and the data instruction, the low link can, just like the index for the current node, the low link can just start out with like no value. What did we use here? The same thing. -1, okay, I mean, whatever. See, that one is an easy instruction. We like those instructions, right? So, okay, next we're at ret loc. Now we're at the return location. So we're done. Effectively, it's returning the low link. Otherwise, it's been returning index, or, you know, the 3 different cases in the edge loop have all been handled. We didn't have to even do an on stack kind of explicitly. We've implicitly kind of made everything work by using self-modifying code. And so we're going to fall to this ret loc. And this can just be this is another instruction we fill in with self-modifying code. These are the easiest because we've already got self-modifying code modifying this instruction. So it's just going to be like a jump anywhere, or a no-op, or whatever you want. So, because it's going to be an invalid instruction until it's filled in, but it's always filled in before it gets here. So we'll just leave it as a adder VM instruct with a jump, with a lambda returning 0. I think it's sufficient. Oh. Man, oh man. Funny how that can happen. Okay. So how many instructions left? Well, only 5. We're down to the last 5. So now another data instruction, we can just copy this. And this is like the representative node can also be -1, an invalid index. Well, in this case, it's not an index. We've made it an address, but a -1 is an invalid address effectively as well, because you can't have an instruction at -1 unless there were lots of instructions, which can't really happen. Now, node adder set loc. Yeah, that's where we want node adder set loc. We already referenced this. So we already referenced relative to node adder set loc for changing the representative unique value for a component. As I said, we could have just used X there too. I don't know why I chose to use the address of where the start value is. It doesn't matter. Okay, so we've got node adder set loc. We're done with that one. Now we're going to need one last one. This check SCC, check same SCC loc. So I've defined this basically because we need to decide if it's unsat. And if it's unsat, we can just have a conditional jump here. So after node adder set loc, we're going to need what? Sat loc also. So we're going to put the last 2 locs in. Again, we're getting ready to just finish this up right here. And then we're going to test and see if it works. And what I really hope is that it works, obviously, on the first try. That is always the best. So we define these last 2. And okay. Yeah, this stuff's nice. I mean, it's a complicated model, and it's even more complicated to implement this crazy blueprint where we're filling in a blueprint for each node so that it's gonna, do the right thing. But again, in assembly language, this would be really, really cool. We may want to write the blueprint in assembly language, compile it, and then just kind of steal the actual binary bytecode data to save time. I mean, we can go to the processor manual, but it's easier to just have a dump that shows you all the bytes, and you don't need to think about all the encodings and all that. I mean, who wants to do that? It's kind of uh, not that fun to play with instruction encodings, even if we can. Um, some instruction encodings are fun to play with, but not for something as large scale as what this will be. So, okay, check same SCC loc. This one is just going to have a conditional jump. So we return a JCVM instruct. It's going to take JC, and where is it going to jump? Well, we know already that it's going to be satloc minus check same SCC loc. Because if they're in the same SCC, it's not sat, it's unsat. And in that case, we want to do something a little different, like jump to unsat. So the next instruction, we're just going to push here. We're gonna finish this off in 2 minutes because I'd like to see this working. After all this work, I mean, this is, you know what I mean? Who puts in this much work and you don't want to see a nice, good working result here? So I'm going to put in the rest of the work here, and we're going to make this work. I don't know if we're going to be able to get the assembly done right this minute, because that's also going to be a big chunk of work. But I would like to, actually. I should go for this, because we can actually get that done. Yeah, it's kind of a disappointment to get the whole huge model in here to simulate assembly language without actually getting your hands dirty and doing the assembly language. I mean, yeah. All right, so again, I'm kind of just filling everything in because I just want to see this fall right together. We're going to have a jump to unsat, right? That's very easy. Of course, we always use a lambda here. You can see how you eventually get good at this stuff. That's all I can say. Maybe for a lot of people it's not that easy, but over time you can start to get good at tracking all this parentheses and squiggly braces and just getting used to writing these kind of code. But yeah, even just as I said that, I have an extra there. So, okay. Then we're at satloc, and now we're going to use our special func instruction. I'm just sketching the code out now. And the func instruction we said was going to be what? I think it's taking the same form as an adder VM instruction, yeah. It just doesn't, it's like void. It's, you know what I mean? It doesn't really need to return anything because it's just going to update our solution data structure, and that's why we have it. Because the input to this, if you think about it, the stack, the instruction pointer, all this, none of this, the only real input is the successors, the graph. The only output is the solutions, and if it jumped to unsat or sat. That's it. There's no other input, there's no other output. We've done this very cleanly so that the only input and output is exactly what you want it to be. And that is kind of a nice way of doing it. We didn't actually make like extra input data structures. All of the data is self-contained within the assembly code. Literally the only thing we use is the successors to traverse through so that all the node code can be the same size. It's just we could even put the jumps to or the calls to each successor in the code, but it would make the code longer and jagged, and no real reason to do it, is what I thought, at least, though. I mean, okay, so we've jumped to unsat. We're going to have a func instruction here, and we're just going to, you know, have a nice little lambda there. And I think finally we get to the next topoloc, and this is our last instruction. And we can just copy this because it's just going to be jumping to sat instead of unsat, unless, of course, this becomes, it's not the last node. So this will only stay as sat, just like this would only stay as sat way at the top here. These are the same jumps. It's going to create a chain of jumps through where it's creating the strongly connected components. And at the end of that chain of jumps, it's going to jump to sat because we initialized everything to sat. And that's like the nice thing about all this. So all we need to do is just say jump to sat, and it's going to change all of them not to be sat, except for the very last one. Then it jumps to sat, and we're done. It will exit this loop, and it should return a solution. The only thing for this function, well, for the function, it's very easy. So we can just check that, you know, if, what is it, sol.find. Okay, so we're going to need to capture that. And we'll want to capture x too. Again, this is like a void function here, but what we can do is look for negative x. So x and negative x are only in the graph once. If they're not in the same component, the topological sort determines which one we're going to use and which we are. So if this is not equal to solution n, then insert x, right? So x is considered the reverse topological order. So that's the next potential solution. We don't care about the component anymore. We only cared about that to determine it's not unsat. If it's sat, we're going to just put this in the solution as long as there's no dependency between it and minus x. So again, we're going to have a directed acyclic graph, and you don't know when x and minus x will occur. And it's possible they could occur in reverse orders. If they're not in the same component, there's no loop, they're not contradicting each other. So fine, you just check that it is equal, it is equal to the end. So if it is equal to the end, we add it. Otherwise, if its complement is in there, we forget about it. We just don't do anything. And that's it. That's all this function has to do. Does it have to return a value? I guess it does have to return a value. That's silly. Yeah. Okay, and the last but not least, this conditional jump here. This conditional jump needs to just check that, what do we need to check? Okay, so what we're going to check here is that it's not in the same component. And the way we're going to check that it's not in the same component is by saying check same SCC, the function I called in Python. And I show you guys the Python code, but the node address of x. So we're going to capture x. And we'll just say node address of x is not equal to what's at instructions. Again, we're kind of using this little hacky thing of using the instructions in here. Maybe we should make a slightly more spelled out machine where we don't have to use instructions. Like, these are goals for the future of this, because in assembly language, all this is going to wash out, except it might be harder to build the blueprint because we have to kind of make some calculations. But again, a lot of this may just end up washing out in assembly language, where here it kind of looks like an ugly hack that we're not using multiple registers. Like, we should just use another register here, and that would be fine. So, but we are only doing this a couple times. There's only a couple places now. And yes, if I added another register, it would be easy to fix these last little things. It's not a big deal. But, okay, so the instructions of node address of minus x. And we're going to add node address set loc. because that was where we stored the representative node address of x. Now, again, as I say, we could almost have just used x, you know, so using node address x, well, it's what we stored up here somewhere. Somewhere there's a nice store instruction. I think it was here. No, it was here. So yeah, we store, no, yeah, this is it. Node address set loc. We store what we did, make node address of node address loc, which is the same thing I'm going to be doing here. So after we get the address at this location, we need to take data. Oh, wait a second. Yeah, because we use node address sub x. Now, technically we should add, technically we should do this. Because technically that's happening and it's not all that clear that this has to be 0. If we ever made it not 0, we put like some dummy code up above, everything would break if we don't. And I've probably forgotten this a couple times, and it's okay, but it is something to be thinking about, because that could be dangerous. So I think this is a data, yeah, of course it is. It's right here. It's a data VM. So we've got our data VM instruction, and we're just going to grab the data field. I think that's about it. Wow, so I mean, we're coming to the very end here, where we've literally done the whole job at this point. The odds of this working right now are probably very small. Probably I made some mistake. Yeah. Of course, I'm really worried. I mean, but it is fun to try, right? So all I have to do is now drop out all 2sat here. And again, I'm going to publish this code at some point, so probably I'm going to write a research paper first. So that's, but that's a bit more work to get there, because I have to think about things differently to do that. Okay. It won't work, right? It's going to crash out. Yeah. Oh, man. Well, how far did it get? Did it even get through the blueprint? Oh, it's in release build. We don't want a release build. We want a debug build. So we're going into the debug build now, and we're just going to see if we've managed to get this anywhere. Okay, it's crashing. Cannot seek value initialized vector iterator. All right, what did I do wrong here? I know what I did wrong here. I know what I did wrong. So what I did wrong here is I made this build blueprint, which is, it's an output iterator, and this is a tricky problem, because again, actually, I was thinking about that, specifying in the beginning. How is that going to work? I forgot the trick to this. There's a trick to this. This isn't that complicated, but again, there is some way. When we're using a transform, we're going to have to do something. Ah, man, it's been a while. Okay, sorry about that. Standard back inserter. That was what I wanted, yeah. Because we're not changing the blueprint, so we need the blueprint not to change, so we have to do it like this. Okay, so that's fine. Again, I still am not placing great odds on this. Okay, next bug. Tell me we got past that, right? Okay. Ooh. How far did we get here? We got x is -2. Ooh, that's not good. Reg 0 is 0. Okay. Okay. Oh, I was saying it before, and this is actually the only reason I think I made a mistake right now, is that I think we need a bit more capturing or delaying. Like in this case, reg 0 feels to me like wait a second. Yeah. Well, it's captured by reference, which is good. It had to be captured by reference. X doesn't. X can be captured by value. Yeah, I've tried to be kind of reasonable about my captures by reference or by value. Like stuff I know never changes. Of course, I'm just going to capture by value. And like this one is absolutely critical. But what's basically happening here is this. Yeah, how on earth could it be? If it was 0, it would have jumped, right? So, all right. This is where you just maybe decide to throw in some debugging. Might be the most helpful thing to do. What we can do is we can just start, spitting out the instruction pointer. And I mean, we could even make a nice little array of strings here. I mean, actually, wait. Well, I'll just do it this way. So we're going to make a string for each one. And since they're in an enum where they're nicely indexing this array that I'm potentially making, it'll be very easy to at least have some idea of what's going on. So we've got our opcode strings, and now we can just print that out, assuming it's a valid opcode. Of course, we have a throw instruction for that. Whatever, for now this is sufficient. All right, so that should give me more than what I have. I mean, I guess we have the address of the instruction. We have the opcode. Of course, if we need to see the arguments, we'll need to do something about that. If we want to print out the stack, we could as well. Again, it can be debugging. This is mostly about addresses, instructions, the stack too. So we'll see what happens. Okay, yeah, that's right. So it crashed during the blueprint, so obviously that did nothing for me. Oh, because, here's the problem. This is called during the blueprint, and obviously this needs to be delayed. I was saying this before. Ah, man. I had a feeling. I had a feeling. These things that I'm saying aren't arbitrary. If this needs to be delayed, the register is being accessed too early. This is a big problem. So, okay, so uh, yeah, we just add a lambda and we're done. Hmm. I mean, we can just call this lambda directly. It's kind of silly to do it this way, but this should work. Just need to make sure I capture everything. Okay. Now we're going to have the same problem right here. See? This call instruction? Exactly the same. We don't delay reg 0, so forget about it. It's not going to work. So I'm going to delay this here. And all right, I think that should do it. Yeah, we have to call it. Actually, we don't even need to call make node adder. I mean, we could just do it directly. This is silly. Trying to reuse code, but when it no longer needs to be a lambda, and well, we could generalize this. Wow. It crashed, but it printed out data and call. It's giving me bad function call. All right, we look into that. Yeah, this is weird. I mean, if we have the right type of instruction. Okay, we have a call, make node address. All right. Well, we can track this down. One moment, I need to get coffee. I think I need water again. have some beet juice. Ooh. My voice is like dying right now. I think I'm just dry, I hope. Okay. Yeah, I let my throat get too dry. Not always a smart thing to do. Okay, let's finish this task. We're going to figure out why this call isn't working one way or another. I mean, one thing we could do is just actually like take a look at it more deep into what's happening at the assembly language level. What happens when it tries to get the address here, and then it. Oh, okay. Wait a second. I think I see the problem. No, actually no, because I mean it should have an address here. I mean we can put a breakpoint here. Ah. Hmm. I mean, I see 151 instructions are in here, or yeah, I think that was what it said. Yeah, so address says unable to read memory here. Do we not assign it or something weird like that? I mean, by inheritance, we should be good. This should be a function which returns a size t. But wait a second, what we are calling here is make node address. Yeah, this is okay. I hope I don't get tied on this one. This should be easy. Make node address. It's a function returning a function. Okay, that's fine because we want. Let's just put a breakpoint on this and see what happens. Aha. Okay. And this, if we look here, we see in the address VM instruction, adder adder here is fine. It's fine. But we see address doesn't seem to get initialized here. Yeah. It's just not happening. Oh, wait. I don't know. You know what this feels like to me? It feels like the problem is I'm constructing this adder VM instruct kind of as kind of a stack object, and then it's copying into the vector. I mean, of course, we could use pointers. I think that would solve this whole issue, but we don't want to use dynamic memory. I mean, it's possible, but my opinion is the correct thing to do is to actually is to probably the way the copy constructor is working is it's actually adding a VM instruct, and it kind of casts away the adder VM struct, so it doesn't actually know how to make a copy of itself. Yeah, that's... If I had to guess right now, it's probably the copy constructor. All right, and it's a big topic online. I mean, of course, you just go look copy constructor inheritance in C++. One thing is we didn't make the virtual destructor. Which I think is a mistake here. Although I don't think this is the issue, but... Actually, it changed the error we're getting. Oh, wow. Wait a second. No, it's the same place. Yeah, the same error. So, okay, the next thing is to think about the copy constructor. I know, I think we need to use something like virtual inheritance or something else here. Kind of get that feeling. Of course, this depends on what C++ version we're compiling with, but I think... Oh. Yeah, I mean, obviously adding pointers would work here. I don't want to mess with pointers necessarily. It's not... I mean, it's not like we're going to lose anything here, but... Oh, but I mean, we are messing around a lot here. I'm trying to think the best thing we could do here. One thing is to look into the copy constructor. So, I mean, I suppose if we could get this to give me a const copy. Then it would be very easy. Oh, this is gonna get diabolical here, right? Because I might be going down the wrong design route here. Okay, we try something different. Yeah, as I said, this might be going down the wrong route. Of course, this didn't even work. It didn't even compile this, which is weird. Of course, it's not. Yeah, it's not even compiling the copy constructor. This is an annoying design thing here. Trying to know the C++ trick to get this to work. That's really the key thing here. Obviously, I want to use the same architecture I've been using here. I mean, it's very close to working right now. But I need a solution to this kind of problem where it's not going to add the right type of data structure onto the stack. Well, okay. I have kind of a new opinion. Oh, that's no, it doesn't work though. I mean, You know, actually, none of this will work. The more I'm thinking about it, it's not ever trying to make a copy of a specific type. It's always making a copy of the base type. So I think the thing to do here, well, I guess the best thing to do is to use pointers. I mean, the problem is the instructions array is taking a VM instructions. So this vector here, it's pre-allocating the right size for a VM instruction. Obviously, it doesn't know that it's going to need more data for these other instructions. So there's just like no way we're going to get that in there. So one thing we could do is make these pointers to instructions. Could even like use another wrapper, like a unique pointer or something like that. That would work. But here's the problem with doing it. The problem is if we do that, it's everywhere. We have to do this everywhere. We have to do it everywhere, including in these ones where we're returning a VM instruct for our modification instructions. Although I suppose I'm making a big deal out of something it really isn't. I mean, what other choice is there? Well, yeah, I suppose from an efficiency standpoint and everything, you can't just expect C++ to be fixing all these types of issues for you. When again, there is a problem. The size of the VM instruct data structure is already fixed in there, and it'll never work. So let's just throw unique pointer in here. Again, the key is to identify your error in assumptions with how C++ works, like I've done, and then you just go and you fix it. So I think it's memory. What header is this in? No. I guess it's just built in. I guess I don't even need to include anything. Yeah, it's here already. Okay, so we're done with getting that there. So we've got unique pointer. So now to go for the big thing here, we're going to just simply put unique pointer into the mix. And we're going to allow it to just manage that single unique reference. I have to think about this because, again, the problem is we're not only using it in the blueprint. That's easy. I mean, it's a good place to start testing it out. So the instructions in the blueprint, we're of course going to now just ooh, yeah, that could be. This could, again, there's some ownership issues with this. All right, I just want to see it, see what we're up against here. Okay, so that is going to create some issues because everywhere that we create these lambdas now, I think we need to use the make unique. Well, where is make unique? I should know where this is. Oh gosh. Oh, it's, yeah, it should be there. Standard. Does that work? Okay. Oh man, it's gonna be it's a long road though, isn't it? Yeah. It's a long road. You have to do this to like 50 instructions here. Okay. And even then, I feel like there still might be another. C++ isn't that forgiving with this type of stuff. Of course, the sooner you figure out that you have this type of error, the better. I kind of put this off, but now you can see I have to suffer the going through all the code and fixing every instruction. And even a VM instruct, which technically the copy constructor works for, it doesn't matter. At this point, everything has to be some kind of unique pointer. That unique pointer is just the easiest one because of the unique ownership, and we aren't really sharing these pointers, so there shouldn't be an issue with using unique pointer. That's why I mean, again, the ownership should always be really clear cut here. But here's where it gets complicated, is we're going to put a VM instruction in a VM instruction. Of course, we haven't defined it as a unique pointer yet, so we don't need to solve that quite yet. But it doesn't matter because we know none of these are going to work without doing all of these things. But there's not too many places beyond the blueprint where we need to get to this level. Oh, there is more actually. The instructions themselves too. The copying and pasting is annoying here. Yeah, this is just slow and annoying. I wish I had figured this out before. Totally a blunder to think that I could just store these off the stack. That was just really... Oh, these are the things that happen to you with C++ sometimes. I mean, again, it's kind of an amateur mistake, but I've been doing a lot of Python programming, so I'm not surprised that I've forgotten about this. At the same time, I mean, it really just depends what your language of focus is, because I've gone through these things before. It's not like the first time, but again, don't focus on these things for a long time, and it comes back to bite you. We're getting there. I mean, the last thing you want to see is that after all this work, it's still something else, you know? Of course, I don't expect a problem immediately with this because we're actually before this in the testing. I just, as a proof of concept that the compiler is going to accept this, I want to know for sure. I'm almost certain we're okay here. This is a common trick to fix this type of issue where you've got some kind of inheritance and you realize that, oh, you can't use stack copying because it simply doesn't know, it doesn't even have the amount of bytes needed to store these derived classes. Again, kind of like using the union would have been a better solution, but unfortunately that comes with its own range of problems in C++. So it's not like there's always a straightforward way to elegantly do these things quickly. Elegantly and quickly. Every programmer has their own solution to these types of issues. Not just one thing you can do, but... How many more do we have to go? Almost done, okay. Whew. And this is the worst of it, so... Having this one out of the way, then we can just focus on the few modification instructions where we have this stuff and the actual instructions, which are few as well. There's only a few places we actually reference that. Okay. I think that was it. Yeah. So now this is no longer a function here. It's a unique pointer, right? So, okay, this is completely understandable. Forgot about this case. It's easy. We just say like f.get, I think. Oh, no. Oh no, the function returning a unique pointer is the problem. It's not here, it's here we need to say .get. Yeah, but of course we don't want to do that because, but for a temporary, well, yeah, this is why you don't want to do it. It's just messy. Again, the same problem comes right back in, but we've undone one layer of the problem right now. And now we need to fix instructions. So instructions also should be a unique point up. So we make a unique pointer here. And then we're going to look at these unique pointers. And we're going to actually try to just do the same thing really quick. There's only like 3, 4 of these. Unfortunately, the modification instruction also contains instructions. So that's going to be the last case. But again, unique pointers should be sufficient here. It's not like we need to worry about shared pointers or ownership issues. That's kind of the big thing where you might have to make something more complicated, but here I don't think so. Now we can take out this get that we put in here. So now we can do this. Ooh, well, okay, these are not big issues actually. The next issues would be some referencing issues. Well, again though, they're going to be all over the place, but see how we do here. So, can we do that? Yeah, so now we can just change it to pointer addressing because you don't have to call get. This is like the shortcut method. Okay. And here's the modification instruction. I said this is going to be a problem too. Again, we can work around it, but it won't. The code won't work. So I mean, if we said something, well, we could make unique here. But actually, we don't even know what to. I mean, this is just silly to just fix it right up front. So the only fix is the modification instruction. Should not take just data VM. It needs to be a unique pointer. And I think that's the last one. Of course, it's not going to compile. There's going to be some complaints about that now. Where we construct it. We're going to have to go fix all those cases. But at that point, we should be done. At that point, it should stop the nonsense with the errors here. We should be okay. All right. Well, I mean, again, these are useless errors. I know, though, it's... okay. It's going to point us right in the right direction. Yeah, you see all these modification instructions where we need to actually return make unique. Let's see where else we have a modification instruction. There's only like 8 of these, so it'll be fast. We'll be able to get all of these solved, and then after we have all 8 of them solved, I think we're very close. There might be some dots needing to change to dash greater. There may also be some casts that are invalid now, and I have to be very careful. Where we're using address of and this type of stuff, I'm pretty sure we're going to run into, unfortunately, more issues with that. I've been thinking about it already, and I just know where things are heading here. But once we work these issues out, it should work quite nicely. And it should have a better architecture as well. So. No, that's not what I do. All right, I think there's the last one. No, there's one more. Okay. So we've got all of the modification instructions fixed. Okay. Still an issue here. Let's see where it is. Algorithm, binary equal. Here. Because the same thing here. It's not transferring unique pointer. See if that works. Should know how to do that. Uh-oh. Ooh. Yeah, this actually sometimes we need like maybe a copy, some kind of copy mechanism to go here. Where are we right now? Again, the problem here is we want to copy these unique pointers. And so we want to also transfer the ownership. Now, I forgot the trick with this. It's like a move or something like this. I forgot, like, yeah, there is a standard move, and there should be a way to do exactly that. Ah, okay. So M place back is the thing to do here, yeah. Or we can make a move iterator. I guess there's two options here. One is we can do this, standard make move iterator, I guess. So it's in yeah, that's how to do it. Oh man, oh man. Standard move. Okay. I guess we could use that. There's several ways of solving this. One way is to do this. So what do we want to move? We want to move this. And of course we're going to need a standard back inserter for instructions. And that should do the trick. Yes, wow. Wow, I think it'll crash. I'm pretty sure. Maybe not here. Seriously, it's... Oh, this is just messed up. This should work now. This is actually... Of course, I need to be very careful that we're moving things correctly. Oh, wait a second. I mentioned this before. Isn't this wrong? Now that we have this, remember, this is no longer something I can just say address and cast. I can't do that. It already is a pointer to that. Right? So if I said dot so I have to just be careful with this. Unfortunately, this might change a bunch of things, but if this is the last thing to fix, then okay, I'm okay with it. autocomplete's not done. I think I just need to call get here. I think it's done. We just call get and we cast that. Let's try it, because I think that's right. So we don't call address of, but we call get. Because get should return a pointer, as far as I remember. Yeah, pointer, yeah. So that's what we want. So we can't use address of anywhere, but that's actually very easy. We can just search for address of now and just take all those out. All right. Well, let's just see if it works. Like it stops crashing, and we are getting some. Yeah, we're getting traction now. It's gonna keep crashing because we've got work to do here. But okay, I mean, the good news about this is we have a design that's clean now. So I mean, this is a workable design pattern, and we are gonna get the model working now. The question is, how often have I used this address of here? And I just don't know. Like here. Here. And we just have to fix each one of these and it's over. This will work. Well, I mean, it will work up to the next probably mistake in the Lambda function, but it'll stop crashing so prematurely. Okay, there's only a few more of these. It's not that bad of a situation. Just make sure I don't have addressive instructions anymore and it's good. It'll give a compiler error if something else besides get is behind it. But that can't be there anywhere. Except, of course, in captures where, you know what I mean? I can't just search and replace because obviously the captures need to have it there. All right, that should be it. If it's just captures now, then we are good to go. And now this should fix the entire design issue. I don't anticipate any more problems with it. Maybe, but... Well, vector subscript out of range. That's a big improvement. It's not an issue with... This is totally different now. So now it's gotten up to instruction 14. It's done about 10 instructions. Again, it's crashing on a modification instruction. So the address and the data. Now, probably what I've done here is simply... Is this the... It's not even the first modification instruction. It's the second one it's croaking on right now. So it dies right... So we have the 3 stores, we have the pop, and it's dying on this instruction right here. Which seems a bit strange, doesn't it? I mean, that is all sorts of strange right here. So, So vector subscript out of range, and the vector is, I'd like to see the this pointer. Whoa, the position is like some number that's like, you know, a quadrillion even, so it's just some 64-bit number. It looks more like a pointer. Does not look like a position. So, why can't I find out what this is? Okay. Okay, so it's the instructions. Okay, okay. That actually is good. Easy enough. So what's happening here is it gets to the modification instruction, which is interesting because it's the second one. And obviously the address is out of bounds here. So it's calling address. And when it calls address, what will happen here? Okay, so we look at the code here, and it's going to call address, which is going to not have anything to do with this first argument. It should be the second argument, right? So it should be just this make node address. Yeah, okay, that's it. Okay. Actually, so it looks like we've got an uninitialized variable here. Like, if I look right now at the value, again, this is very tricky stuff right here. So we have here, where's the instruction that's making the problem? This one, yeah. So we have here on stack loc, it's 20. I mean, we know that that's good. But it wasn't 20 at this point because on stack loc was an uninitialized variable. You know why this is happening? Because we didn't pass it by reference, we passed it by value, right? So if I put this by reference, then when it calls the lambda, this one probably can be by value. Well, I don't see why not just pass them all by reference. Again, the problem is any that haven't occurred yet, and this is a big problem. We're going to see this over and over and over. I think just passing everything, again, we could just put a single ampersand in and just say, okay, everything's going by reference. But again, this one's already there, so it doesn't matter. Again, these, once they have a value, they're fixed. But they don't have values yet, so I have to be careful how I capture them. This is a problem as well. So the way to just test the theory is run it again, see if it stops crashing there. Yeah, it got one more instruction, right? So it's obvious that I think I'm almost 100% certain all the code we've done here is perfectly correct. And the only thing is we need to go through and we need to fix all of these little lambda capturing type issues. Again, it can be very tricky to get them all right. But again, we have a pretty good idea how to do it here. So I go put more ampersands in. It's going to keep executing more and more. Where else? This one. You see, again, if we know it came before, we don't need to do it. But it's a bit, you know, it's a bit tricky and dangerous to think you're going to catch all of these. So, like this one, I know. I know loop edge came before, so I don't need to do it. Counter loc came before. I don't need to do it. Okay, whatever. I mean, it's going to crash with probably high probability if we don't deal with the issue. Peak ret loc, it's there. Okay, check low link loc, it's there. Low link loc, of course. Let's just capture that. So I'm just capturing all these variables, so I don't need to worry about weird stuff happening, especially if I'm 100% sure the variable's coming after the current place where it's used. Comes before it, as I said, it's okay. We don't really care about that. So call loc, it came before it. Low link loc is okay, we've got this start topo, came before. Node enter set loc, it's coming after. Wow, it's a triple chaining here. Yeah, this is very, very tricky though. It's so easy to make an error here. Don't particularly like when you know what I mean, that just, it's a high risk if you can make an error so easily. So next topolo comes after as well. Yeah, I've got all these kind of high risk bugs to worry about. I don't know. Okay, I think okay, we're gonna have another one here, right? Yeah. Sat loc. Okay, that one needs to be captured correctly. Sat loc, and we've got like this, no, that's it. I see that's the only one. Man, these captures are tricky business right here. I mean, some people would just say, put all ampersands everywhere. Who cares if they're captured by reference? They're just integers. Well, I would say that's probably a good idea, right? So again, here we go. Oh yeah, you see, we did capture these. That's why it's working here. Again, we didn't need to capture them all like this. Like this one we don't need. We know it's already 0. We know it's already 0. But you do have to be careful with this copy by reference stuff. I mean, it's too easy to blunder it. Yeah, the lambda itself, the lambda maker, I'm capturing by reference, but I think we're good now. Uh-oh. Okay, I was overdoing that. Oops. Let's see if we got it now. No. Messed up another line here. No big deal. Yeah. I over did the capture variable stuff. Okay, let's. Wow. Well, I mean, good news is that it ran without crashing. Now, another assertion that we forgot to do here, and this is a very important assertion, and that one is that we should assert the length of the stack is equal to 0. Because we exit the loop not when the stack's empty. Obviously, that stack being empty, we could exit the loop when it's empty, but we exit the loop on sat or unsat, and it doesn't mean that the stack's empty. So a very, very, okay, and obviously we want to do this right. So a very good assertion here is to make sure that the stack actually emptied itself. And it didn't. So, I mean, a first thing that you're expecting to happen is that this is the type of mistake that gets made. Now, one thing we can say is that probably we want to go to the all2sat function, and we probably want to, actually we want to print We don't want to not print solutions. And this huge formula, we probably just don't want to test right now. Because it's giving a bunch of output, and you don't necessarily want to see all of that. I want to see, like, with, these very simple cases first, before we actually, All right, let's see what happens. Okay, so the stack didn't clean up. Now, did it get anywhere at all? No. It looks like it didn't. Well, this needs some serious debugging. This is like, huh. That is weird. Okay, I'm getting my coffee. That is strange. All right, one moment. I'll be right back. I need to use the restroom. All right, back to work here. Finish this job, right? This is the crucial part right here. Can we actually get this working or not? So, I hope so. So the stack is not empty. I mean, it's not even handling the single solution case. Now, my guess already is what's well, I have a Python solution of this working. So I mean, one easy thing is to compare the two. Are the nodes in the same order in all these things? I'm not exactly sure, because one's using a dictionary, a Python dictionary. Now this is using a C++ map. Are they going to be the keying in the same order? Obviously, the edges, I think I use a list, so it doesn't matter. That'll be in the right order. But that's the keys, maybe not. So one thing we can do is look at S. Oh, S is 4. Yeah, that just doesn't look that good. One thing we can do is we could put print statements into these instructions here. We can just use the func type to just add a bunch of printing of what the status is at any given point, so we can kind of see some maybe useful output to decide what's going on. Obviously, at some point, this is diverged from the way I had thought the code would be, so the problem is I don't think there's much wrong with this code. I think this code is 98% right by now, but there's probably like one or two tiny things, like it could be that, I needed to put a lambda somewhere that I didn't, or yeah, it's going to be something very similar to that. I mean, honestly, it's working quite well. It's executing quite a long time before it's not even, it's not even crashing. This app will run to completion, but it doesn't seem to find components. So, one place to look is the jump instruction dealing with the components. That's actually a good place to look. It could be that one of these captures just needed to be, and I screwed it up still. Okay, so let's just do some basic debugging here. One way we can do that is we can like add an instruction right here, for example, one that's not going to be overwritten, but at least the first time it calls it, like, okay, we can just put in here. Oh yeah, we need make unique now. And we can just make it a function was a data? No, it was an address, I think. No. So we've got our function, and what we need to do is write some kind of printing code here. And that'll just be like a cout statement, so just cout. And what do we want to cout? Well, maybe like X for starters. So it's just to make sure this works, I'm gonna send it through as a test. And I forgot that. Okay, that's why forgot the closing here. Okay, this is needing to return a value because we've just defined that this one returns like some kind of size t, so we can just return 0. So now if we execute, what we can see, oh, you guys can't see this, okay. That is a problem. Well, the capture window's got the wrong one right now, huh? So what we can see here is that this has -2 here, and we see it calls func, it prints the -2. We see here 46, -1. We see 2, and we see 1. Okay, so it's gone through all 4 nodes. I mean, there's something good about that, right? But then it seems to be jumping to sat, and it never seems to find a component, which is wrong. It should be finding a component with all 4 nodes. So we have to wonder how that's happening. When it falls back out, it should find the component. And this is a bit weird. But it's, the truth is this is going to be for some really nasty little technical issue here. Again, probably because I didn't use a capture where I needed to. Maybe even in a couple places. So another thing we can do is instead of just printing out what I was printing out there, we can actually print out a little bit more. We can print out X and then we'll print out like a space, and then we'll print out what we can do is we can use our make node address function to actually like start picking data pieces out. So we can just say, instructions at some value, and then we can just get that instructions. So like make node address of x, comma, low link loc. That's a good place. We want to see the low links. Maybe we want to print this later. We don't want to print it so early. But again, this is like the way you do debugging. You start writing your printing statements out, and we can print the index and the low link loc. That'll tell us a whole lot of information about where things are going wrong, because we want to know what is going on here. Obviously, there's some really strong ideas. It seems like the control flow part is not the problem. Probably the stack part or something with a comparison, a condition, is the problem here. And again, a lot of it seems to be already working here. I mean, this is going to be kind of annoying because you have to spend a lot of work to track down a very small issue, and then the whole thing's going to just work beautifully. And of course, that's the exciting part, though, is to see it work beautifully, because then you're ready to go for assembly language. You don't joke around at that point. You write the assembly code immediately, you compile it, you take the bytecode, and you write a generator. So you have to write a code generator, and this is something that really is part of a whole model for self-modifying code and for generated code. Very similar to having a, what's it called? Virtual machines that have that technology where they have on the fly code generation. So I mean, it's kind of a similar idea, just-in-time compilation, kind of like we're doing just-in-time compilation on a special code blueprint that we're going to emit real raw assembly language with, but we're actually modifying or modeling control flow graphs here, which modify themselves, which is pretty cool. So okay, make node address. Obviously all these things are going to need to come in. We don't care. This is a special debug statement, so it can have anything it needs. Okay, so we've taken some captures here. Gonna make the code look a little better here. And so we want the instruction at this address, and what we want is, we know it's a data instruction because it's the low link loc, and we just want to get the well, we need to cast it first. Alright, I know it still became a really long, disgusting line of code. Should probably make sure none of these are so bad. Oh, they are. Oh, they are. Starting to fix some of these horrible long lines here. Alright, yeah, that was really long. Alright, nothing going off the edge of the screen anymore, I guess. That one is. Do some reformatting here. This one, oh man, that is such a long line to reformat. It should be reformatted. Yeah, it's good to make your code readable. So no point in making these lines also long. This is even just the start of the reformatting. It needs a lot more. Definitely. Okay, I mean, it's better. Again, now I don't need to like scroll horizontally, which is particularly annoying thing to do. Okay, so I think I'm ready to solve this right now. I want to, again, if I just knew what location the things were going wrong, it would make it a lot easier. That's why I want to print out the low link loop. I want to know what's going on, because if the low link and the index and stuff are all looking correct, then probably one of the jump statements is just messed up. Again, it's also a question, is it even going into the SCC acceptance code or not? The other thing is we can go look at the main instruction. We don't need to just look at this one, but we can look at this one as well. So we can go to node adder loc. Need to capture it, but not by reference because it's defined already and it's never changing. Uh-oh. Okay, the problem is make node adder. We need to actually call it. We're just reusing a function without any particularly necessity of doing that. We could just, okay. Okay, now execute. Oh, that is really bad. Okay, now. I'm getting like pointer addresses here. Oh, because, yeah, no, actually I'm getting weird results here. I mean, obviously we don't use real pointers here. We're using indexes into the instruction array, so I don't understand why this could happen. It doesn't make sense. I mean, everything's protected in this function right here, so it's unclear to me what's going on. This is really unclear. I mean, because we can see that this this lambda function here is should already have the correct values here for things like low link low. By this time, yeah, it is weird. Okay, well, I mean, we can just check. You know, no need to assume stuff. Can just print this, rerun it, and just see if we actually have the right low link loc or not. Yeah, we do, 30. So 30 is the number of instructions in for the low link loc. The real question then is why am I getting a weird, like a pointer address here for data VM instruction. So low link loc. If we go to low link loc, we see that there is a data instruction with -1 that's going to be filled in. There's no... well, it's a unique pointer to an instruction, but then it has data. Oh wait, data is, no, it's a size t. I mean, there's no real reason that this should be happening. I cast it to a data. Ooh, this is, I mean, no wonder this stuff's not working. Something is up here. Something is up. Look at this. So. Okay, let's try this also while we're at it. Just keep printing stuff out to make sure that there's... But again, it's obviously returning a valid instruction address, or it would crash with a bad index, so I don't expect that to be the problem. Yeah, 111, whatever, 148. So all the Addresses seem legit to me. Oh, don't tell me. No. Hmm. So now we look at the store instructions, because like they could be the problem here. I mean, that's where the data ends up getting set. Right, so this is the most likely place where there's a bug. Let's just put a breakpoint and see one of these gets set and just see what's happening here. So we put a breakpoint, we step in, we keep stepping in. Oh, no, it didn't really help. Ah, this is being annoying. Add watch? No, it's being really annoying. Because it's multi-line code, it's not adding the watch. Okay. Oh, come on. I have to open Notepad to make a single line here. Copy, paste, put it in here, and hopefully this gives me some information. Okay, 0, but I mean, that's like not too bad. Seems to not be working here. Maybe I need, oh, refresh, yeah, 2. Aha! That's a bad value, if I've ever seen one. This is really weird. I mean, this is definitely screwed up. Because it's showing that we're seeing this like pointer value in here, but how did it get in there? Now, probably after this, it's correct again. 2. So this is happening on the next instruction. Oh, well, it is technically quote unquote uninitialized, but not really uninitialized. So I'm a little. Is that -1? Ah, yeah, okay. That strange value was -1, I suppose. Yeah, because I guess it's treating it as unsigned. Okay, well, okay. Then we just move the print statement to a more appropriate place, because obviously it's not telling us anything. So where is the print statement? And actually, this is good if it is in fact working. So now we take our print statement and we're going to drop it somewhere that's going to help us hopefully solve this problem much, much faster. One place would be like this, maybe. Check SCC loc. So I would say right after check SCC loop, just to see if anything actually is getting uh, identified as an SCC. Nothing. Nothing is being identified as an SCC. Okay, so now we want to put the instruction somewhere different. So nothing gets identified, which means that this jump statement is always true, which is definitely a problem. Let's check if it's an SCC. So obviously, uh, okay, there's some real problems right here. You see, one thing I see in the output is we see the instruction location 0 twice. So how on earth is something jumping back to 0? This is just bizarre. This is absolutely strange. Something is majorly wrong with here. I mean, when we do the call, it calls instruction pointer +1. Obviously, I've got some real mess with the capturing here. I should have been more careful to copy my original model more exactly, because it took a while to actually get all of that stuff working, and it was a lot easier in Python than it is in C++. I'm glad I did it there first, trust me. This is, not really a trivial thing we're doing here. This is pretty advanced stuff. Let's see. All right, I think we can solve this if we just print out what's going on. So as I said, I think we'll print it out then at low link low. No, we can't do it here exactly, but we can do it after. This will be sufficient. Let's see what's happening here. Okay. Now, I guess you guys can't see the window, but this is printing out everything. Oh, it printed out nothing again. Ooh. Well, isn't that interesting? Hmm. Well, I see 130. That's all I see right now. Okay, I mean, if we look at the addresses, and that's like what I'm doing right here. Yeah, I guess I have to fix this window. This doesn't want to. So, I mean, I'm looking at these addresses, and I mean, they're going up. So 0, 1, and then I see a data load store. And that means this is the first node. Again, what we have is we have data call. So, I mean, we have all the initial calls here, and it, of course, hits the first one. So now 7 must be the address of the first data. We see it's going through here, and we see at 22, we see a call. So now it goes from 1 to 2. It's going from the one node to the next node. Then we see here data, and then we see 59 call. We see it goes back to 7. Good. I mean, this looks like it's working, right? And then 8 return. Good. 7 is not allowed anymore. And again, its low link would update though here because the index of 7 is going to be less. So again, that means this is not going to be a component. Everything is looking great. Now, it makes its next call to its next node. Okay, 118. Now it's on to node number 3. Remember, there's 4 nodes here, and this is an unsat. So this looks good. So far, we look at this. This looks absolutely correct code. This is exactly what we want it to look like. It's calling what, back 44. Again, all of these link to each other, so it is going to find a contradictory component. Again, 44 already called, returns, it's updating low links, whatever. Gets to its next call. Call 81. The last node is on the table here. So okay, so 81, 96 calls 7. It returns. So here calls again. It returns. Then here finally we see it. This is the first node it jumps to 0. So, okay, so we know the problem already. Oh, after all that, we see the jump, and then we see it go to 0. And it should never go back to 0. It could go back to 2, because it was 0, 1 are guaranteed, and then it has to continue at 2. There's no way to go back to 0. So we know this jump statement is messed up. So we go here, and we say, okay, why is this jump statement 0? Don't we change the ret loc here? And okay, so there's this simple jump statement, and ret loc is referenced way up at the top. I mean, that was one of the first ones we did here. So here it is, modify instruction. Uh-oh. Make node address ret loc. Okay, ret loc's captured. I don't see a problem there. Reg 0 is captured. I mean, we're expecting 2 here, right? I mean, that would be the or are we expecting 2? No, we're not even expecting 2. I mean, we're expecting whatever was on the top of the stack here. Whether it peaked, it should have peaked at it. Yeah, so it should have peaked at the top of the stack here. Did it peak at the top of the stack? That's one thing we can ask. We can say, okay, it did, it peaked. It peaked before it modified the instructions. So how on earth it got a 0 here is a good question when it was peaking at the top of the stack. And we know, well, okay, in a circumstance like this, I think what we want to do is look at the stack. I mean, I would almost say that, you know, the easiest thing to do here is just to like, yeah, somebody might know how to, how are we going to print a vector of integers, right? Isn't the stack, well, I mean, okay, effectively, I think the stack is, well, we can just print this. We can just make like a little function that builds a string and we can print that. Or we can just print it one element at a time with strings and lines. It doesn't really matter. So where is the stack declared? The stack's declared here is stack of size t. Can we iterate a stack object? Because obviously we want to like look through it. I don't know if we can iterate a stack. We'll just take a look at the definition and find out what we can do. Yeah, can we print out all the elements of a stack? There's got to be some trick to do this. Huh. Don't tell me you have to like pop them out and push them back in. That is just gotta be a horrible option. Really? There's no easy way to print out the contents of a stack? So again, it's a wrapper to a container object, but there's a question. Okay, so people are saying you can't print a stack without writing an adapter. I mean, that's kind of unfortunate, huh? Okay, so I look on Stack Overflow, and there is a list of kind of hacks for this. Okay, I mean, the other thing we can do is just print the top of the stack. So, I mean, we don't have to go uh, trying to hack away the stack class. I mean, the other thing we could do is push them all off and pop them all off and push them back on in the right order. I mean, this is it's that's pretty lame. But again, we don't really care. We're just debugging here. I'm surprised for debugging purposes we can't print our stack out. Um, if there was a way to copy a stack, of course we could just pop them all off. That would probably be the efficient way to do it. Hmm. Yeah. I mean, some people use the stack. They used a recursive routine to do it. That's almost silly. Okay, there's a million solutions on Stack Overflow for how to do this. Anyways, I'm just gonna print the top of the stack. It's enough. Probably we can figure out from the size of the stack and the length of the stack, we can be able to figure out what's going on with it. So we'll print it in here. Every instruction, we can just say, okay, I want a space here, and then I want to know what's the size of S, another space, and then I want to know, S dot top. Now, if it's empty, this might crash, so let's see, just for fun anyways. We can always check if it's empty, it's easy. Yeah, okay, I mean, that's easy to fix though. So it did crash. So we just do something like that. We check if it's empty and we use -1. Otherwise, we just use the top, and that should be sufficient. Okay, so now I see the stack has length 1, and it pushed 2 onto it. Okay, here's where... Okay. Okay. No, I mean, it pops the 2 off the stack. But presumably it saved that 2 anyway. So, I mean, I don't get it. But again, we're not actually checking that one. And -1 is being printed because, that makes sense. I mean, it's empty stack. So the question then is, why did this jump back to 0 at 112? And we have to kind of look up above. Again, probably this is not working right now, is it? Oh, no, it is. Okay. Maybe if I don't close this window, it'll stay working. So the place we want to look is this peak, I think, here. No, where is it? I think it's this peak at 86. So we see the stack had length 3 and the top element was 134, which is fine because it was called from 133. It should have the next address on there. So it peaked at 134. Now it should have saved that 134. Okay, let's print out the register too. We're not done here. We're not done. We want to know what's in the value of that register. We'll just put that right here. So we're going to really debug, and hopefully we can just pin this down quickly now. What? Okay. Waiting for a return. Okay, so the register, yeah, we can see the values are in it now. So what I see here with 130 looks perfectly correct. This looks absolutely what you want, because obviously these are all in one component, and so the low link is going to be 0, yet its index is 3. So it's going to wait till it gets back to and then they're all going to be in the same component. It should be unstat. This should be easy. I don't understand why this is jumping to 0 here. That is a major problem. And that jump to 0 is weird because we know it comes off the stack here. So when it's peaking, it's supposed to peak, it sees 134. I mean, we see register 0 has the value 134. So register 0 is not being delayed. We know already what's happening here, because if it was being delayed, it would not be doing this. It must be being pasted in too early. We didn't use a lambda to somehow delay it somewhere. And as I said, I knew I made a mistake or two like this, and I was talking about it before, and should have fixed it on the fly because it's much, much more painful to fix right now. Yeah. So, yeah, okay, so we see the modifying instruction for retloc right here. Still don't exactly understand this because I mean, obviously we've got a mess of captures right here. Jump. So I see we're making a jump instruction. Oh, wait, I said this a long time. Oh man, it's just coming back. This needed to, oh gosh. And I even have, okay, this is nonsense. I can explain exactly why this is happening. The problem is when this jump instruction is pasted, it's pasting register 0, which is not going to be the right value. Because we don't want the jump instruction to modify this to return reg 0. We want it to modify it to return reg 0, which has not been kind of captured in this way, which is the reg 0 that is delayed. So this is too early, actually. And this is really confusing. This is the type of stuff that really gets people. And yeah. I wrote a little get val function in Python to do this. It's just a function, get val x, return lambda x. It's really just a capture function. And actually, the C++ kind of works similar here. And so we actually do need, of course, we don't need to write a function, named function. We can actually use another lambda here. So if I just capture reg 0, like this, and then, no. You see, here's what you don't do. What you don't do is capture. That's not how you solve this. How you solve this is actually, actually, it's the opposite of what I said. We don't want reg 0's value at that time when it's 0 when it exited the loop. We want reg 0's value now. Reg 0 has the right value, it just peaked it off the stack. So to do this, opposite logic, this is how we do it. We simply make a lambda, and we pass that lambda to reg 0. And then in here we can just actually access it. We can just say reg 0, something like this. And I think this will be sufficient to actually, I can get rid of this one, I think. Okay, let's see if that works. Oh no, because this needs to still return a lambda. That's if, man, oh man, this is. But now it's not returning one that it captures. It's returning a parameter that it got, which already has been it captured it basically instantaneously. Now probably we could do this by taking off the by reference capture here. So actually I'm thinking about this. In C++, we have some better options for doing this, don't we? So, well, by this point we can just, okay, whatever. I think it's going to make it further than it did before. Yes, it did. So already we can see that, look at that, -200. Now the assertion that's failing is that we have an empty stack, because the stack clearly is not empty. But we can see -110, 220, 130. But by the time it gets to -200, we have a component. And that actually should have been accepted. And, but I don't see what I want to see here. I see the jump, and then I see that it exited. So it jumped to sat. Again, I think it's the same bug again and again. I think exactly the same thing's going on. If I look where I used getVal in my Python version, it's exactly it. Okay, I mean, I used it 2 times, once here and once to change that jump instruction. So there were very good reasons why I used that, to say the least. Again, we're not... it's not about necessarily delaying always. Sometimes we want to accelerate. We don't want this. Again, as I say, we probably can just delete some of these. Again, what a mess. It's going to become very hard to understand if you, have to be very careful whether it was by reference or by value. It's very precise code. This is not code you can mess with so easily. So we want to look at the place where we're setting node attr setLoc. The last modification instruction. It's right here. And right here, we can see that this here is a jump instruction, but reg0 here just came off the stack, and we want that reg0. We do not want reg0 way later when it executes this. We don't know what reg0 is going to be. So we have to use the same exact logic. What we're going to do is we're going to return, we're going to actually, I mean, there's a variety of ways we could do this, but since we've got a lambda already, we could actually just call the lambda. I know, I feel like I did an unnecessary level of indirection the last time, but actually this lambda's... I know, I almost feel like we could just get away with this here. No. No, we can't. Okay, so let's not try that. Let's try, let's just do the usual parameter passing method. I like that method because you know for sure that you're calling some function here, and there's no way it can not work. So here's the end of this lambda. Pass reg0. We do want to capture its frozen value at the time that it evaluates the mod instruction. The mod instruction, yeah, which will have this jump in it. So at that time we want the reg0 value, and so here we can just return another lambda. Carefully here. Oh no, we can't do this, can we? Obviously, we don't get to control this lambda. I know, it's like, yeah, this is kind of crazy stuff. But again, this is how you do it. Like it or not, it works. So the outer lambda we don't control, like we last time, because this one has to be of the right function signature. It has to be a anonymous function. And so we need a lambda there. And so the simplest way to do it is basically like this, where we can just keep wrapping lambdas around stuff. We have to put an extra lambda here so that this immediately, instead of returning this lambda, which has the would capture the reg0, so that it's still using that reg0. We don't want that. Instead, we pass reg0 as an argument immediately cause it to not be captured, but its current value to be copied. And there probably is another trick to do this. As I said, I'm almost sure, but I don't feel the need to mess with it right now because this should work. Okay, did I get it right? Yeah, this is ridiculous, right? Yeah, this is the hardest line of code in the whole thing. No doubts on that. Okay, reg0 can't be captured. Let's not call this reg0. That's really a bad idea. I don't know, what did I do that up here? Yeah, I did, didn't I? Okay, let's just call it R0. Yeah. All right, something like this. Oh man, I thought I fixed all of this. Wait a second. Jump. This is an anonymous lambda with no parameters, and then this one has one parameter, but it doesn't really matter because we're immediately calling it so that it returns a, no argument lambda. How did I get this one to work? Okay, so this one, oh, actually I specified it right out here. Yeah, that's, okay, yeah, actually that makes more sense. Oops. Yeah, I knew something was getting funky over there. It's like a extra level of indirection going on. Okay. This is, it is one tricky line of code to write. So we want to capture, yeah, and we want to pass here. I guess we can still call it reg0, it really doesn't matter. But what we do need to do here is return an anonymous function, so we need to recapture it here. Do that. Really making this hard. I think we got this. Come on. Tell me we got this. Yes. Oh, and it still doesn't work, That is just... Hmm. It's weird because actually at this point, by the time it's evaluating the mod instance instruction, it's going to call this. Oh, wait a second. How come this one worked so well? I feel like I must have done something different here. So this actually, we see that not really a huge difference. We just have one capture out here, and then this kind of inner capture returns the value. And then we have this one where we just call it and get rid of it. Yeah, it's as simple as that, really. In my opinion, this is what should be done here, actually. One thing we could write a C out statement in here and just see what reg 0 is. See what is going on, because again, actually I've attempted now to really fix this. This actually should be a legitimate fix. I can see what the register. Oh, did I close it? My gosh, this is I closed it, didn't I? Okay, well, just run it again. I don't know, the window probably got messed up. The only thing I want to do is like kind of look at what happened with the stack and the usual stuff. Okay, the key thing to note here is that actually what it's doing right now is it's not accepting the components. So we're trying to fix code which isn't executing. So that's why it's jumping to sat, because it's just refusing a component when obviously we're printing it out and they are the same values. So somehow, probably yet another weird lambda situation, and we can immediately identify that if that's the case. So the problem is going to be, but this is a simple one. I don't know. I feel like we've probably done all of the different special indirections, I think. Yeah, I mean, this jump false had to have become jump true somehow, which is impossible. Okay, wait a second. We run it again. I mean, the best thing to do is just to keep running it. Take a look at the... So there's the debug console. And what we can see is that it jumps, and it jumps. And then it has the low link data, and that's it. Okay. And there's 4 items on the stack, and 97 is the top one. Again, actually, that's perfect. We wanted to accept a node, the strongly connected component with 4 nodes. That's it. I mean, it would be done if it would do that. And 0, and we see here -200, so it's obviously equal, so it should be accepting that this is the root of a component, and it should start popping them all off, marking them, getting ready to finish this task off. And it's, for some reason, not doing that. It's like literally getting confused right here. Well, this is the consequence of doing code in such a tricky way. Again, I'm trying to just solve this with eyeballs, but again, it just doesn't matter. Uh, it can be some little tiny subtle things that take some time to figure out. So, um, and I of course I want to see this work. It's beautiful when you see it work. Actually, it really is, because to solve some huge, two stat equation is always kind of, and perfectly the stack is empty at the end, everything, and the code is so ridiculous. It's pretty cool. Needless to say. So where did we go wrong here? Well, as I said, it's got to be this location right here. Um, I mean, this could be a cascade of different problems could be occurring here. Uh, Again, the register 0 had to be coming back correctly. Yeah, any number of things could have caused this. But the problem is, everything is greater than or equal to 0. So, I mean, that is how on earth this can happen beyond me right now. Because obviously, jump true. And here it should be set to jump. Oh, wait, did I not set it to jump false? Don't tell me. Oh, that would do it. What's the default here? Okay, let's find out. So here, where it's gonna check the SCC look. Oh, it's calling jump true. Uh-oh. It's supposed to call jump false. Ah. Well, everything has a good explanation in the end. It's supposed to default to false and toggle to true. Obviously, if it's always true, it's never going to process any components. Uh-oh, we're crashing. But is it working like a little better now? That's the big question, right? So, um, are we getting closer? Okay, I see it accepted. No, it didn't accept the component. Negative 220, negative 110, and then what is it doing? Aha. Uh-oh. Oh, this looks like bad news. Another small error here. It's crashing in vector subscript out of range. I think. Wow. So we know it's right after the pop. Now it should not have accepted this, or should it have? Oh no, it should have. This is not negative 110. This is the one. It should be accepting this. Things are working perfectly. Oh, this is great news. Okay. Finally, we're accepting a component. Yeah, I mean, you can see a little bug in here is just, I don't care how sharp you are at looking, this is really not pretty code to look at. So again, after doing this long exercise, we get to the next step where we're going to write like some better pseudocode. We're going to find a way to say, isn't there a better way to look at this without such a horribly hard to read type of algorithm going on here? I mean, and there should be a better way to represent this. But again, I don't think we have a compiler for such a language, but maybe we can make such a language even if we can't compile it. So let's look at why this. So we go to the pop instruction, and then we go to this modify instruction, and actually it's surprise, surprise. Well, reg 0 is 134. Node adder set loc is 215. So 32 minus 15 plus 134. So 134, do we see a call at 133? Yeah, we do. Okay, so that's actually, it looks right, doesn't it? But how many instructions are in the instruction array? This looks really concerning because there's 155. So no, 151, it sounds reasonable actually. That's like, this is the final node in the instruction array, and actually this sounds totally like what you would expect. So um, let me go back to this pop mod area. So again, this looks to be right. Oh wait, this is the wrong place. This pop mod. Okay, so start topo. Well, I mean, that's fine. We don't need to care about that. Okay, so start topo. What is it set to? 5. Ah, that must be the issue. So one thing we can do is just add a watch here. So okay, I almost rather look at hex to see why isn't it working? Oh, this is really annoying. Now it doesn't want to show me hexadecimal. Okay, that's just weird. Okay. Oh, that looks uninitialized. Or we've set something else wrong. Okay. Start topo is instructions.size. Yeah, but that's right. You can't have a problem with this. I mean, start topo plus 1 is here. I mean, I'm pretty sure this is absolutely right. I'm pretty sure this is absolutely right. So is this, if we look at this, is this the first time through the loop or not? So again, here, 220. So here it's jumping. Here it's even trying to call another one. Of course, the stack is not going to get more than 4 items. It gets 5 and immediately returns. And then, yeah, we see the conditional jumps. Then we see a pop. Ah, we do see a mod instruction. Okay. Okay. And then we see the stores and we see a jump conditional and then the next pop and mod instruction. And what we should realize here is that something went wrong right in here. Right in one of these store instructions, because we know that it should have updated start topo. And it did, but it updated it to not a reasonable looking value. CCCCD1D says, obviously we've made a mistake here. So one of these instructions is going to be doing that. And, okay, is it the same problem? Don't tell me. But not convincingly so, is it? Because the only reason we needed it was for the mod inst, not for the store instructions. That the mod inst, it returns another instruction. So because an instruction returns an instructions, we need lambdas within lambdas within lambdas. It is that bad. But we don't need that here. We don't need to go to that level. So it should have a store instruction at start topo, and we actually see that does occur. So what's register 0? We can see register 0 is 97, which was at the top of the stack. Perfectly reasonable value. So why would it write the wrong value though? I mean, this is weird, right? Oh, wait a second. Call loc is 15. Oh, next topo loc never set. Huh. Oh man, really? Of of course it's not set, but it's why isn't it set? Did I just forget to set it? Okay, okay, this is easy. Okay, easy, but again, how many more of these quote unquote easy problems are there to solve, right? Okay, so next topoloc is supposed to be this last one, where it's jumping to sat. All right, so we're getting closer and closer and closer. It is starting to work. We're validating it by eyeball that, really it's starting to work. Okay, now this looks even more promising. Okay, the stack didn't empty. Wait a second. It ran for a long time. Oh, it actually, the first, did it? Oh. Okay. I think we've actually gotten quite close now, because I don't see. It seems like this has already gotten past the first one. Yeah, it has. It's gotten to the second example. Now, I don't know what happened on the first one, but I can tell you that it has definitely gotten to the one solution case. So we're no longer stuck on the unsat one, it seems. And it did have an empty stack. This one, though, is not emptying its stack. Something is wrong here. Oh, this can be tricky. Now, we can see that some of these nodes, we see the jump chain at the end. You see how there's like all these different jump, 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 jump. So we do see that half of the nodes ended up in the jump chain. But again, all of the nodes have to end up in the jump chain no matter what, because we aren't checking for unsat until that time anyways. So how a bunch of nodes manage to stay on the stack, this is not really good. Hmm. Okay, one more place where I want to look for the indirection mistake is going to be. Hmm, no, I don't really see any good place. I feel like we've properly delayed and accelerated all the values now. Now it starts to feel like we've done everything right. Uh, and obviously not, because it's the stack is getting too full here. Okay, I want to maybe see what nodes are, what order it visits the nodes. So we can actually kind of go back to our printing function. At this point, maybe more important than watching all the instructions. So this, again, this is like a hybrid of debugging. We kind of want to like look at what's going on here, but at the same time, we want to like look at what's going on when certain key parts of the code are executing, rather than be distracted by too much noise here. So somewhere we have our print statement here, and that print statement's gonna allow us to maybe get some intuition into what's going on. So instead of doing it right when we return, let's do this when we accept a component, and we accept a component after this check SCC right here. So right before the loop part of this. So the other place we're going to want to put this is we're going to want to put this right at the front. Maybe after we call store here, before we peek at the stack. I think that would be perfectly fine because we've updated the index, so there is something to look at here. And now we can just run it and see what happens. And now we should just see, yeah, okay. Look, number of solutions 0. That's great. So, and the stack was empty at the end. And it accepted, there's only one we see twice, and that's the component that was accepted. That's perfect. I mean, that's exactly what we want here. We see -4, 3, -1, 2, -4. It found a component. That's great. That's exactly what we want. And then we see -3, 4, -2, 1. And unfortunately, it didn't unwind, right? So the problem really is that this also probably is a component. I think, no, maybe, yeah. Yeah, it should be. Well, we can always take a look at the Boolean equation. Yeah, one of these. Obviously, the solution to the equation. We can check. Print the other way here. Let's just see. Okay. Oh, it's printing. It's with false. It's not going to print the solution. Okay, now we will see the solution. And when we have the solution now, okay, we see -1, 2, 3, -4. Okay, there we go. -1, 2, 3, -4 is the actual solution of the Boolean equation. So we can go back to the other one. In fact, we can even just do both of them. We don't need to do one or the other. We can do both. And so we see -1, 2, 3, -4 here. So so we have to kind of wonder what's going on here. Obviously, there's 8 nodes in the graph. So we can look at this. -3. Well, actually, it was at -4. And -4, again, would have a link to... Yeah. Well, if this is -4, then this has to be 3. And if this is -3, then this has to be 4. So, again, it's already, -4 is already gone, so it's not getting it from -4. It's getting it because it just decided to start with -3. So let's see, if -3 is true, what would it link to? So if -3 was false, or rather if -3 is true, then 2 would have to be true. In other words, if 3 is false, 2 would have to be true. And also, well, we might want to look at the graph. Actually, we might want to look at... Actually, we can, can't we? So we've got... where's the... Go into debug mode, and let's just look at the successors and decide what's going on here. The successors are... No, they're buried here. Actually, we just changed the watch. So if we look at the successors, there's 8 of them. Yeah, and I'm making too much of a mystery about it. And if we look at the -3 here, we see there's 2 of them, and it goes to 2 and 4. Okay, so it does hit 4. And 4, if we go to 4, is going to hit -2. It goes to -2. And again, the question is why it didn't find something here. So it goes to -2. Actually, yeah, it's really interesting. So another place we should make these print statement. Yeah, let's just speed this up. Speed this along. We really want to just get this finished. It's been a long time, and it should be working by now. So clearly, what we're going to look at is right before it leaves the routine, right before it jumps out here. So right before the return location. I just want to know what happened. I don't know if they're all separate components or what's going on there, but again, they all have to have dependencies on the other component, which always has to come first. So it's impossible those will be part of the solution, but we don't know how many components or what's going on with them. Okay, so here we see what's happening. We have 7, 6, 5, 4, but we're seeing 1 coming into play here. So already we know the problem. So we see 1, 7, 7, but then we see 1, 7, 4. Now keep in mind 4 is not allowed because 4 is already... no, 4 could be allowed. Okay, but we don't really care. That one actually should be allowed though, shouldn't it? Because -4, but -3 has not yet come off. So if 7's low link is 4, okay, I mean this, but 1, once 1 came in here, 1 was a index that was already accepted. So there's no way we can have 1. So these, again, this is very tricky. There's no doubt about it, but the evidence points to a store instruction being incorrect here, namely the store instruction that's supposed to set the size here. Okay, now we're on to something here. That's all I can say. Now we're on to something. Yeah, this is weird. Oh, wait a second. I don't think this is right. Successor of X? Wait a second. Oh my gosh. We don't need X at all. We want all the size of all the keys in the dictionary. This had nothing to do with that. Oh gosh, that would definitely explain why we're getting this behavior. Okay. How many more bugs? Please tell me we're getting there now. Yeah! All right. This looks promising. All right. No crashes. All right, finally. Okay, this was the moment we were all waiting for. I didn't put a drum roll in, but we should have had a drum roll. This was definitely, tricky stuff here, and we actually got it working. That's amazing. Truly amazing here. We'll leave that one in. We can delete all the rests of these couts. Kind of like our copy and paste line here. Yeah, well, you can, again, actually, I feel like this is kind of instructive for people who want to learn more about troubleshooting and debugging, because this is something I've become good at over the years. And again, something this diabolically difficult, most people would just give up and not bother. But look at what happened. All of this code came together. Of course, I admit I already had the code in Python, and it's sitting in the background, and I'm using it as a reference. But again, I managed to get that done in a day as well. So it was diabolically hard. It was very tricky, but it was very interesting to get this job done. So we can run it again, and we should be able to see like some nicer output here. So, okay, so what we see is exactly what we want to see. We see that this is giving solutions exactly like the very simple two-sat formula. And now we can actually let this run forever, right? And it shouldn't cause any I mean, hey, I'm not promising anything here, but it's finding solutions. All right, there we go. It's a 60 variable. Now, I'm not going to say the speed here is anything to be proud of necessarily compared to the other version. And we could even try to make a faster offline version by integrating all the two-sat and everything together. There are some things we could do here, but this is definitely, well, honestly, I think it's impressive. The stack is empty at the end. We used all self-modifying code. There's no input except the graph. Successors in the graph, really, just because we didn't want to put those into the code. And there's no output except the solution and either a true or false sat unsat. Now we are ready to put this in assembly language. I mean, that was it. This little virtual machine toy here has gotten us to the point that all we need to do is just take all this code here, translate the blueprint and maybe this initial instruction assignments. We need to translate them into actual assembly instructions. And since there will be some encoding, we'll probably just write an assembly file and compile it and just look at the listing where it shows you the byte opcodes and the actual instructions side by side. And we can just quickly tweak it if we want to, modify that code. But probably we can just use it directly and we can just say, okay, here's all the bytes. And then we're going to use a little bit of mathematics with offsets, and we're going to fix everything up so that it, works appropriately. Oh, the window screwed up again. It's really, that's like the, wait a second. The right window here. So you can see it's printing out endless solutions to this equation that probably has millions of solutions, and I don't know, it could have billions of solutions or trillions, and may be time of the remainder of the universe to get an algorithm that isn't optimized enough to ever give you the count of solutions. The count is P-sharp complete. So if you know what P-sharp complete is, it's a problem that's harder than NP complete hardness to count all the solutions. It's just nobody knows anything about doing such a thing. There are some algorithms using where you introduce a certain constant k and you can bound it by n to the k, given certain properties and things like that. There are some ways. I think it's like n to the power of 1.2 or 1.3. But when you think about n to the power of 1.2 or 1.3, that sounds pretty good, right? It's still exponential, but it's, it seems only a little exponential. But as soon as n is about 500, go put 500 to the 1.3 in Google, and you'll see that, wow, you have a lot of problems. So again, length of time of the universe type of stuff, and and once you put 5,000 or 10,000 nodes, yeah, forget about it. So if you have a big SAT equation, you're not solving it with an algorithm that's exponential. It's just not happening. Maybe 1.00001, but nobody has any algorithms close to that. So it's not like, you know what I mean? You're going to get much. And even that 1.0001, it grows too fast when your number n is big enough. So, yeah. So yeah, this is going to be my first demo. I need to have dinner. I'm exhausted, to be honest, by this big coding session where we actually implemented it. This is pretty cool. This code is going to get posted on GitHub sooner or later because, again, this is a pretty neat system. How many lines? Wow, 450 lines of code. Okay, 450 lines of code, and it took some hours, but very, very tricky code. So this is not code you just kind of relax and just write out of nowhere. This really took careful effort and kind of careful debugging to actually figure out. So, uh, anyways, thanks for those of you who actually came and watched this demo. I think there would be a video like saved around about it. Yeah, I don't know if people are interested in this kind of stuff, but I like to do these really hard algorithmic problems, like these problems that have a lot of either graph theory or math and stuff where just nobody else is just going to go there. And so to me, it's interesting to know because often people like to see stuff that it's just nobody would ever touch that stuff because it's just too diabolical, too difficult, whatever. But I'm like, well, but I like to go there. So even if nobody else in the world likes to do it, this is what I like to do, and there's something kind of cool about it. So again, sometimes you have to get your hands dirty and you have to do the really hard, difficult problems. Uh, Even if it takes a lot of thinking power, even if it stresses you out a bit, even if it makes you really tired, taxes you. So that's kind of like my strategy, my thought about this. Do the really hard stuff, get really in there and figure out these kind of complicated problems. And see if you can take that complicated mess, simplify it, rewrite it. Again, as I say, we need to write pseudocode for this because this isn't really uh, maybe it's elegant in a certain way, but again, it's kind of so unreadable that we can't decide if this is optimized properly or not. Maybe we can eliminate some more instructions. We can make this code more efficient. But unless I can write like a C-like pseudocode with self-modifying code being kind of built into C with some kind of meta language, which we're going to do next, possibly, or we're going to do the assembly, but we're going to kind of do all these different things, and we're going to really get deep into this to see if we can do something really cool with the self-modifying code, something that maybe can involve real complexity theory, where we're actually trying to come up with an algorithm that uses self-modifying code to do something that's never been done before, which is to do something where there actually is a true complexity result. Of course, that's that's shooting for the moon right there, but there's no way to shoot for the moon without to do stuff like this and go in and do the really hard problems of showing how different problems can be represented this way. Probably strongly connected components in 2SAT is too simple. We might want to do dominators. We might want to do more complicated algorithms, sure. But this is a great start, I think. So anyways, and it's also cool that we have this working in C. Yeah, we should put some profiling code in here and time this and see how long it takes to do with the more efficient version in this version. That's coming up next. We're also probably going to do some graph V's, and we're going to just like generate some dot files and just look at the graphs and decide. I think it's much more fun to look at these graphs and decide, like, is there any strategy for going about counting the solutions using self-modifying code? Can we break the PNP problem? Can we do something cool? Can we find a one-way trapdoor function? It's great questions, very hard questions. They're not trivial. To do something with self-modifying code is going to require some kind of modifications that are beyond just the control flow of the graph. You're going to actually have to be modifying the code in the different nodes in a way that you get some kind of complexity maze that nobody's ever been able to think about or analyze before because it's typically thought of as too complex. But if you can't find such a weird complexity maze, you're not going to get anything out of it because you can always model it as in polynomial time as just non-self-modifying code. So we have to use the self-modifying code in a way that the modifications are modifying the modification instructions, and it's just going to be, it's like to the point where your mind is going to be blown to try to come up with something. But if you do, it could be really a fundamentally new idea, and it could be like absolutely change the way of thinking about mathematics and code in general. So cool. Thanks guys for joining the stream, and I will probably be back tomorrow with the rest of hopefully finishing all of these different tasks off. So yeah, hope you guys enjoyed. Hope you guys learned something, and I will see you guys next time. All right, take care.